Hello, everyone. Welcome to the workshop. My name is Michael Ray, and this is the 7th International Workshop on Egocentric Perception, Interaction, and Computing, or EPIC. Over the past few minutes, we've seen how the field of egocentric and first-person vision has evolved. And though this list is by no means exhaustive, we no longer have to tape cameras to people in order to make them wearable. Due to the field bridging both vision and robotics, egocentric vision has seen a huge surge in popularity in recent years, with many applications in human understanding, life logging, or social interaction, and many others. This has also been seen with the commercial products that have been made available, from GoPros to Google Glass, as well as the HoloLens, further allowing for new and exciting research. So first off, I'd like to thank my fellow organizers, who can be seen below, for all their efforts to make this workshop possible. So we have an exciting program for you today, including the EPIC Challenges release in just a few minutes. And then we have our 2 invited keynotes for the morning, some accepted paper presentations, and then some invited talks from the main conference, as well as some keynotes in the afternoon and evening. So first, I'd like to thank all of our reviewers for the workshop. In some cases, they had quite a short time, so thanks to all of them for the hard effort and the work that they put in. So a bit more about the morning session. Like I said, we have the EPIC Challenges release in just a few minutes. And then we have our keynote speakers from Bernard and Federica. So they should be really exciting. And then before lunch, we'll have our 4 talks from our accepted papers. So the first 2 from full papers and then 2 from some extended abstracts. And then we'll break for lunch just before 1 o'clock. And then in the afternoon session, we'll have invited talks from the main conference. And these are grouped into 3 or 4 per session. And then we'll have some Q&As after each session. And then we'll round off the day with invited keynotes from Richard Newcomb and Jitendra Malik. So again, stick around for this. It should be really exciting. So now I'll hand over to Dima, and we'll start off with the release of the EPIC Challenges.
I need to find the mute button. Good morning. Right. I assume you can see my screen. Right. We're here to tell you more about the new edition of EPIC Kitchens. That's EPIC Kitchens 100. If you've been with us in the live webinar on the 1st of July, then you know that today our main intention is to release 5 leaderboards, which I'll tell you more about, and my fellow researchers in the team. This is a joint effort led by the University of Bristol with the University of Catania. And it is really lots of effort, but it had been encouraged by the amount of interest since the first release of EPIC Kitchens. So when we released EPIC Kitchens, we really hoped people would use it and that people would find different ways to use it for different problems, and that indeed had been the case. We were pleased when the University of Bristol download team told us that we're not only the most viewed and downloaded dataset in our servers, but that importantly, it had been downloaded by so many countries. Of course, different amounts by different countries, depending on their size and research interest. But still, we're talking about more than 2,000 unique downloads from many countries. That probably had been the reason why we felt encouraged to extend and rescale the dataset into what we now call EPIC Kitchens 100. So just a quick recap for those who might not have been with us in the live webinar. The difference between the first release and the extended release is primarily the number of hours, and that's why we kind of are appending the name. So the first version is now referred to as EPIC Kitchens 55, and the extended version as EPIC Kitchens 100. This has extended the number of kitchens, the number of videos. It still is as unscripted and in people's actual kitchens as with the initial intention. But there is a significant increase in the number of action segments due to the new style of collecting annotations to ensure they are denser and more complete. This has resulted in a natural increase in the number of action classes. So this is basically classes we have not collected before. And that shows that regardless of how many hours you collect, there are still more things along the long tail that people will do and that we need to prepare computer vision models for. We have remodeled and rethought about our verb classes and noun classes based on the initial feedback we've got. So you'll see a new list of verb classes and noun classes with the release. And importantly, we have introduced a clear validation split to avoid any issues, and 5 challenges, 3 of which are new. So this is the natural long tail distribution of instances in our dataset. So we have, as I said, 97 verb classes. These are not verb instances. So this is after the verbs have been grouped into minimally overlapping verb classes. And the y-axis is log scaled. And the difference between the shaded and the solid colors is the part of the videos that come from the first set of videos and the new set of videos. You can see here that there are completely new classes being introduced with the additional footage. We also have introduced these super classes for verbs that group things like take, remove, scoop, lift into this retrieval action, etc., which people might find useful to maybe produce more interesting understanding of the goals of these actions. Similarly, the nouns are the same, and as usual, there are far more nouns than verbs. And again, we have remodeled these. We currently have 300 nouns, and we've grouped them and released these subcategories that group things like the tap, the fridge, the oven, etc., into appliances. On the 1st of July, already with the researchers now, we've released the data. That's the videos and the full annotations of the train and val splits, and an archive paper that describes the data collection, the improved annotations pipeline, and all the baselines for the challenges. Today, and as promised, pending lots of work that we've done and trying to get everything on time, we're releasing 5 leaderboards on CodeAllow. And I'll hand over to Johnny, who will tell you first about the data collection.
Yeah. Sorry, I'm Abigail. I've got control of the slides now. So I'm just going to quickly talk about the data collection, of how we collected the data for the extension in Epic Kitchens 100. So we gave a series of participants GoPro Hero 7s. So this includes camera stabilization that wasn't present in the Epic Kitchens in 2018. We then asked participants to record all their kitchen activities over 2 consecutive days. This produced unscripted natural actions. So this data collection has occurred 2 years after the collection of data in 2018, Epic Kitchens 55. And what we got back was full HD video plus audio. And we've also got gyroscope and accelerometer data, which has been captured by the GoPro. On the right, we have an example of the setup that was seen for the data collection. In total, Epic Kitchens 100 contains 37 participants, of which the extension in 2020 contained collection from 21 participants. Of these 21 participants, 16 had recorded data in both 2018 for Epic Kitchens 55 and for the extension in 2020. 8 of the returning participants have recorded in their original home, so they have stayed in the same location for collection data in 2018 as well as in 2020. And I'll show you a couple of these videos comparing both the data from the Epic Kitchens 55 and the extension in Epic Kitchens 100. Eight of the returning participants, however, have moved homes, and therefore we have data collected from them in a new environment. So we have data from 2018 and 2020 captured by the same participant in different environments. And I'll show you a couple of videos comparing these participants. In addition, 5 participants, we collected data from 5 participants who were completely new to the data set. So these weren't present in the original data set. In total, we have 37 participants, 100 hours of footage across 700 videos. And I'll pass you back to Dima.
Right, so we'll tell you about the challenges that are currently open. I'll start a little bit about an idea we've put out called the supervision level scale that we've integrated into the challenges. I guess you'll need a bit more time to look at it if you want to participate, but this is just an overview of the objective. And then I'll hand over to talk about the 5 benchmarks. The notion of this SLS, the supervision level scale, is to have one leaderboard that allows you to compare across various ways of using the data, whether you want to use it with weak supervision, whether you want to attend few-shot learning, use only temporal or spatiotemporal, or different pre-training strategies. Currently, particularly for the first bit, the weak supervision or the few-shot, people have completely different leaderboards. And that kind of results in the divergence and split between the people interested in solving a particular task. SLS is an objective to request participants to self-declare the supervision level of their method, but then put the results all on the same leaderboard. And we've integrated it into our 5 leaderboards. It is suitable for anonymous submission. So it says what data you've used, but doesn't say anything about the novelty of the method. Thus, we propose a discrete, incremental, and 3-dimensional scale that explains the levels of supervision. And you can read the report that we've put online on that. So what are these levels of supervision? The first is pre-training, all the way from random initialization through various relevant or less relevant pre-training public data sets, as well as the more recent trend to use self-supervision to utilize bigger unlabeled data sets. And then we've set a benchmark for people who train on private data. This is based on our previous experience with the data set, where people have utilized data not publicly available, giving them a clear advantage. So this is the first dimension of the scale. The second is the training labels. So this combines whether you're using weak supervision, strong supervision, temporal only, or spatiotemporal. The third dimension is how much of the training data have you used? Again, all the way from 0-shot, few-shot, something called the efficient learning, which is you have a sample of the training data, through to training only on the training split, on the train and val, or on additional data. So accordingly, a method on the same leaderboard can declare using this discrete scale which level of supervision they've done on these 3 pre-training, training labels, and training data. And then hopefully when we look at these, we can look, for example, on the training labels, people who've used different levels of supervision, and compare how this has impacted the metric. As you'll see from details, we're still gonna award the best, most elaborate method that uses as much as it needs and achieves the best performance. They rank 1 in the challenges. But this is a chance for researchers to defend their methods and say, my method might not perform top 1, but it has significantly used less data or a different approach, and thus should be given its appropriate credit. And I'll hand over to Will to tell you about the first leaderboard, which is the action recognition leaderboard.
Hi, so I'm Will, and I've been running the Action Recognition Challenge since we first launched it back at ECCV in 2018. So the challenge is to take a trimmed video clip denoted by a start and a stop time, and to build a model that can observe that clip and then classify the action within. So where we deviate slightly from other action recognition challenges, is that we ask you to predict 2 things. So 1, the verb describing the action, and the noun, the object that you're interacting with. So practically those are 2 separate classes that your model will have to produce. So back in Epic Kitchens 55, we had this set of data set splits. We had 1 training set and 2 test sets. So the 2 test sets were the scene test set, where it was composed of clips taken from kitchens that had been present in the training set, and the unseen kitchens test set, where the kitchens had not neither the kitchens nor participants had been seen in the training set. So now in Epic Kitchens 100, we've slightly simplified things. We have like a more traditional data set split. We have a train, validation, and just a single test set now. But because this is a superset of Epic Kitchens 55, it helps to understand where the data now lives in regards to these new splits. So in training, we still keep all the training videos from Epic Kitchens 55. And then we have an additional 37,500 action segments from the new data. In validation, we have the previous test sets. However, we kind of had to split the unseen kitchens test set for certain reasons. So part of that does actually go into the training set. But mostly the test videos are now the validation videos, which are publicly available with labels. And then finally, our new test set is composed entirely of videos that we recorded in 2020, and that has 13,000 action segments in. So to drill down into performance on methods, rather than having these two sets that we had previously, we now actually evaluate models on different subsets of the test set. So we have a set of action segments which are taken from unseen participants. So these are new kitchens and new people. So this allows us to test the generalization capabilities of models. And we also have a new notion called the tail classes. And this measures how well models can perform on these classes that have less frequent or have a fewer number of instances. So to understand the tail classes, we need to have a look at the distribution of classes in the training set. So here we're looking at verbs. We've got a log scale on the y-axis. And it actually transpires that the first 11 classes account for 80% of the training data. So these are, quite easy for your model to do well on. However, the remaining 86 classes only actually have 20% of the training data. And it's these that we refer to as the tail classes. So it's the set of classes with the smallest number of instances that account for 20% of the data. And you can refer to the paper for like the specific formulation for how we decide these. So these are much harder to do well on, and we want people to try and push performance on these classes because it's really important that we do well on these. So we run a bunch of baselines. We have TSN, TRN, TBN, TSM, and slow fast. And here we're looking at the performance of these models on top one accuracy, which is our main metric in evaluating action recognition. And this is on actions. So this is the tuple containing the verb and the noun class. We can see that TSM and slow fast lead the pack here on the overall performance. And then if we have a look at performance on just the action segments that come from unseen participants, we see the same trends hold true. So TSM and slow fast are still doing well. However, interestingly, when we have a look at performance on the tail classes, we see a slightly different trend. So TBN, the temporal binding network, has jumped from third place to first place. So models that do well overall aren't necessarily those that are going to do best on the tail classes, which is quite interesting. So this challenge is now released. You can submit your results to it and evaluate performance on the test set. And we look forward to seeing all your submissions. Thank you very much.
Okay. Okay, good morning. All right, so I'm gonna tell you about two challenges. So the first one is the action detection challenge. This is a new challenge that we are proposing with the release of Epic Kitchens 100. So the task can be defined as follows. Let's consider an input video. This can be a short video, so a couple of minutes or a very long one, like half an hour, 40 minutes. The goal is to create a model which can process this video and retrieve the list of all actions occurring in the video. And this is going to be a list of elements. Each element is a tuple containing 4 different things. So we have the starting time in seconds, the end time in seconds, and the verb and the noun. So this is what a foreground action may look like. So this is one of the actions which we need to retrieve. This can be a very short action, like in this case, or a longer one. And this is an example of a background action. So the background actions are likely not to contain any object manipulations, but for instance, in this case, there is this walking action, which is a background action because walking is not in our taxonomy and it's not an object manipulation. As evaluation measures, we use the standard mean average precision, which is usually used for detection tasks. And we compute mean average precision at different IOU overlap thresholds, ranging from 0.1 to 0.5. Methods are ranked by the average MAP, which is the average of these 5 numbers computed considering the different overlap thresholds. As a baseline, we considered a standard 2-stage approaches. So first, we trained a temporal segment network on Epic Kitchens 100 to obtain a feature extractor. Then we use this feature extractor to extract per frame features from the given input video. After that, we trained boundary matching networks on these pre-extracted features on Epic Kitchens 100. And we use boundary matching networks to obtain action proposals in all videos. And after that, we use slow-fast networks trained on Epic Kitchens 100, which is one of the best performing methods in our action recognition benchmark, to turn the action proposals into detections. As with the other challenges, we have released the leaderboard that you can now access. And in the leaderboard, as well in the paper, we report the results of this baseline, which we called in the leaderboard Epic BMN Slow Fast. And as we can see, the results are quite low. So for instance, we have about 6% with an overlap threshold of 0.1, and this number gets even lower with an overlap threshold 0.5, and the average is about 4% for actions. So we believe this is a challenging data set because a reasonable baseline is not performing very well, and this is probably because the videos have different lengths and the actions can be very dense. And the other challenge I'm going to talk about is the action anticipation challenge. This is defined in a very similar way as the challenge in the last set of challenges. And so the task can be defined as follows. We consider an input video with a labeled action, which is this segment highlighted in red. So we know when the action starts. This is the TS timestamp, and when it ends. And the goal is to predict the occurrence of this action by observing a video preceding this action by 1 second, which is what we call the anticipation time. So we will observe, our model will observe only the yellow segment, and we can set the observation time, which is the length of the segment, to whatever we like. So we can go back towards the beginning of the video, but we cannot change the anticipation time. So we cannot look in between the end of the observation segment and the beginning of the action, because we want to make sure that we are actually anticipating future actions and not performing another task such as early prediction. So this will be the input to our model, but we want to understand not what is happening in this video, but what will happen in the future. So we want to create a model which processes this video and recognize, for instance, in this case, take plate. And this is the unobserved action, which will not be seen at test time by the method. So in evaluating this task, we need to reason on why anticipation is different from recognition. So the task is similar because it is a classification task, but differently from a recognition task. In this case, we can have multiple possible futures. So if we observe a segment like this one, and we ask ourselves what's going to happen in 1 second, maybe we can find out that some actions are likely to happen, like the one shown in the slides, while instead others cannot happen because of scene changes or because the future action is not coherent with what we observed. So we have, for a given observation, we have multiple possible correct future answers. But still, we have to consider that the way we sample a data set is that we consider pairs of past segments and future segments, and so we attach a given segment only a label. This label is correct for sure, but other labels might be assigned to this segment, and we don't know which labels are. So when we evaluate, we should take this into account. So what we speculate is that we cannot actually measure a precision in this case, because measuring a precision would be similar to asking ourselves if the predictions of our model are all correct. But what we can measure is a recall. So we do it this way. We consider an action anticipation correct if the ground truth label is among the top 5 predicted actions. So for instance, if we predicted as top 5 actions A, C, D, and F, and the ground truth is D, then this is going to be a correct prediction because the ground truth is in the list of the top 5 predictions. Similarly, if the predictions are B, D, A, and G, and the ground truth is E, we're going to say that this is a mistake. We compute this mean top 5 recall by first computing top 5 recall per class, and then we average the result to obtain a single measure. And the goal here is to counterbalance the long tail distribution by first computing per class metric and then averaging. Similarly to action recognition, we evaluate on all instances, unseen participants, and tail classes. As a baseline, we considered rolling LSTM, which has public code available and was one of the best performing methods in the previous iterations of the challenges. And in the leaderboard, we report the result for the fusion method as well as the single branches, which are RGB, flow, and object. And we also report a chance baseline, which predicts actions according to the frequencies observed in the training set. And as we can see here, using this new metric, we have also in this case, we have improvement with the fusion method performing at about 11%. So you can access the leaderboard now and start submitting your results. And that's all. Thank you.
All right, hello everyone. I'll give a brief introduction to the multi-instance retrieval challenge. And this is a new challenge for Epic Kitchens 100. And different to the other challenges that we're releasing for the dataset, this uses the transcribed narration instead of the verb noun classes, which make the action class for the other challenges. So whereas in action recognition, you might have separate chicken, instead we use the original transcribed narration, such as debone chicken thighs. And when you think of this challenge, you can see it as similar to the video retrieval challenges from other data sets, such as MSR-VTT, in that we've given a video and we want to retrieve a corresponding textual item, or vice versa, given a text item, we want to return the corresponding video. However, we do differ slightly, hence the name multi-instance retrieval, in that we're trying to find multiple relevant items from the other modality. So if we're given this video on the left, then we want to retrieve all relevant captions on the right. And in this case, it's a kind of a much more difficult challenge than potentially the before case where we're only trying to find the specific caption. But this kind of brings up a new question of relevancy and how do we determine whether or not two items are relevant to each other? And we do this using the verb and noun classes that we parsed out for the data set. So on the left, you can see two different captions. One is cutting a pizza using a cutter, and the other is slicing a pizza. And what we first do is we get the verbs and nouns from these two captions. Well, in this case, it's captions, but we can do the same for videos as well, given what they were labeled with. So you can see here we've got cutting and slicing as the verbs, and then pizza and cutter for the nouns. And then we get the verb classes, and and then we use the intersection over union in order to determine what's whether or not these are relevant. And in this case, because these both belong to the same verb class, then we get a verb relevancy score of 1. But the nouns, we have a slightly different story in that one caption has pizza and cutter, and the other one just has pizza as its nouns. And then when we look at the noun classes again, we have 2 different noun classes for one caption. When we put this into the intersection over union formula this time, we actually get an IOU score of 0.5. And to get the final relevancy score between 2 items, we do the average intersection between the verb and the noun classes. So in this case, we get an overall IOU score of 0.75, or average IOU score of 0.75. And this is what we define as the relevancy score between these 2 captions. So with our relevancy score between 2 items, we can now look at how we do the evaluation. And this is done using a normalized discounted cumulative gain metric. And we use this metric because of the continuous values between 0 and 1 based on relevancy. And this is the main metric that we use for the challenge, although we do use mean average precision as well, but I'll discuss that a bit later. So ideally, we want to, given this video on the left, we want to return n captions in decreasing orders of relevance. So we have the most relevant captions at the start, and then we have the least relevant captions at the end. And this would give us a perfect score. However, in practice, this might not be the case. And you can see here that if we have some irrelevant captions returning quite high, this will lead to a score going down. So as some results, we used the JPOS method and the multi-layer perception from our previous work that was in ICCV. And you can see here that the disentangling the captions into verbs and nouns, or disentangling the 2 spaces into verbs and nouns, still gives a slight boost in performance over trying to learn a space for actions alone. And then we also show here the chance baseline on NDCG. And we perform these results on both video to text retrieval and then text to video retrieval, as well as having the average. So like I said, both video to text and text to video retrieval is part of the challenge. And as access to the narrations are required for the challenge, we actually have a slightly different test split setup. So we use the standard training set that all the other challenges or the action recognition challenge uses. However, for the test set, we actually use a validation split. So because I said these narrations are required for the challenge. However, because all of the validation set has been released, we should stress that a relevancy between videos and text should not be used in the test set for this challenge. And then more information can be found in the paper and in supplementary material or on the challenge website. So this is what kind of the leaderboard looks like, and it's open now. So we're really excited to see what your submissions look like. And as you can see, we have the 2 methods here, the JPOS and the MLP. And then we also have this mean average precision metric, which simply just assumes that the relevancy is 0 or 1. So we, instead of using the full range, we just set the threshold to 1, so only consider those as relevant. And the main metric that we're using is the average normalized discounted gain. So that's what we're going to be using to ranking the methods. Thank you.
There we go. Hi, I'm going to present the unsupervised domain adaptation challenge for action recognition. So this utilizes the data from collected in 2018, so from Epic Kitchens 55, and the same participants where data has been collected 2 years later in 2020, which is the extension for Epic Kitchens 100. We've noticed between these 2 sets of data, there is a domain shift. We have the source domain as the data collected in 2018, and the target data as the data collected in 2020, 2 years later by the same participants. To visualize this kind of domain shift between the two sets of data, we have trained a model purely on the data from 2018 and extracted features from both the source and the target. The UMAP visualization of these features shows that they're not overlapping, indicating that there is some domain bias when training a model on data in the past and then evaluating on future data. One explanation for this domain bias is that the same participant has moved home and therefore recorded in a different environment. However, even for participants who have stayed in the same environment, there is still this domain shift. This could be due to the different activities performed, or it could be due to the different camera setup when collecting data in the future. So given our labeled source domain from data collected in 2018 and unlabeled data from data in 2020, we want to maximize performance on the data collected in 2020, our target domain. Notice that we cannot use labeled data from the target domain. This is to kind of overcome this expensive annotation requirement when collecting additional data in the future. For our challenge, we utilize the 16 participants who have recorded data both in 2018 and in the extension in 2020. So we define two splits for training. One is the source domain, which is labeled from data from 12 participants in 2018, and a target split, which is completely unlabeled, and it's from the same participants, but data collected 2 years later in 2020. So the aim of this challenge is to maximize performance on a set of different videos from the target domain from the same 12 participants. However, it's unclear, as the target domain is unlabeled, how we would do hyperparameter tuning or to just validate models for performance. Therefore, we've withheld 4 participants so you can hyperparameter tune models for the challenge. So we have 2 validation splits. So you can train on the labeled source val split, as well as unlabeled data from the target val split. And then you can evaluate the performance on target val to select hyperparameters. Once you've got your hyperparameters, you can use these to retrain a model on the training splits, and that model can then be used to evaluate on the target test and submit the results for the challenge. The baselines have used extracted features. So this is a model trained on the source domain, a temporal binding network on the source domain, and then we have a series of baselines from Chen et al.'s paper in ECCV2020 on temporal attentive alignment, where we have one purely trained on only source data, their domain adaptation method, which utilizes unlabeled target data, and a model which is trained on target labeled data. This is just to compare an upper bound. So this is what the results we've got here. So we see the worst performing model is when we train only on source data. With an unsupervised domain adaptation method, we have a slight improvement on the target domain performance. However, compared to our upper bound, as if we had target label data available, which is not available in the challenge, but this is just for an idea of an upper bound, we can see that we are far away from saturating this data set. So there's a very big scope for improvement of methods for this challenge. The leaderboard is up, and we have our 2 baseline models, the source only one and the domain adaptation, already on there. So we show the performance on the target domain, but we also show the performance on the source domain. This is only just for reference to see how well models do on the source domain. As we can see that they are very similar between the 2 baselines. However, the challenge will be evaluated on the top one action target performance, which we can see the unsupervised domain adaptation method is currently outperforming the source only. Thank you very much.
Thanks. Okay. Right. So a quick notion on the 2021 challenges, rules and dates before we give the chance to ask questions. Leaderboards are open. You can register with an institution email. So please don't use your personal email to register. We accept one registration per team. That is to kind of set the bar. Remember that you have the validation set out there to optimize and train as many times as you want. This is why we set a maximum limit on the number of submissions to the test leaderboard on which you're not supposed to be optimizing your method. That is still a generous maximum of 50 between now and the end of the challenge, which is in May, as well as a daily limit of 1, and that is just to kind of manage the CodaLab leaderboards. There is a JSON file structure for submission, not for the retrieval. The retrieval uses a pickle file, but do look at the challenge to understand. We do check registrations manually. That really helps us later once we know who's registered. So please, once you click submit, don't expect an immediate entry. That might take up to 2 days for us to accept your initial registration. The challenges are open for very long, from now until the 28th of May, 2021, with winners announced alongside CVPR, fingers crossed, subject to the workshop being accepted or around that time, either virtually or in person, depending how optimistic, pessimistic you feel about the situation at the moment. There is a main email address for inquiries. If you've used it before, you know that we try to reply to this as fast as possible. But please remember that we're doing all this work voluntarily, alongside all the other research we're trying to achieve. We do not compete in the challenges, and please do not take turns to try to submit multiple people from different institutions of the same team. Any attempts to cheat will result in an indefinite ban, because really it's our time that is on the line. We are also interested in other ideas related to how Epic Kitchens 100 can be used. And we're very grateful to how people have been using it for many ideas we haven't considered. If you're interested in running your own challenge alongside Epic Kitchens, please get in touch. We can arrange that for the next round of challenge leaderboards. And I'll hand over to Hazel, who will run the Q&A.
Yeah, thanks everyone. So if you have any questions, please post in the Q&A. If you're a panelist, I don't think you're able to do that, so just post them in the chat and we can answer your questions. I'll kick off with a few while we're waiting for people to type. So I guess this one's for Dima. So since there's like lots of challenges all related to the same sort of thing, so there's different action challenges, do you anticipate there'll be models that can sort of do something multitask-like and compete well in all the many different challenges?
That's very interesting. That's one of kind of the reason we wanted to set the concept of one data set, multiple leaderboards or multiple challenges, because I think unless we do that, then we can't achieve the ultimate video understanding we're after. It might run the risk of us doing a little bit too much. Right? We're introducing this concept of you can also do few short and weekly supervised per challenge, etc. I think we're kind of opening the floor for people's imagination, trying to break the notion of one data set, one task, which has been, I believe, hindering the progress of the community in general. But again, there are some linked ones, like the unsupervised domain adaptation for action recognition. It is an action recognition with a twist, let's say. There are things that are completely not classification, like the retrieval. We're really kind of keeping an eye on what people use, what people utilize, and seeing how things go, while the data set stands as a labeled dense data set for people within or outside these challenge leaderboards. Oh
yeah, also it'd be interesting to see what everyone does with the different levels of supervision and challenges.
Yes, we welcome also any input or ideas on that if people when people look at the report.
Okay, so next question is for Johnny about the domain adaptation. So what do you think the main reason for the difference in the domain gap is? Do you think it's people changing kitchens in between, or is it something else?
So I believe it's something else. I think it has something to do with the different cameras to be used. but as well as the kind of different activities, people are interacting with different objects in the future, different cuisines being used, and perhaps even a different way of describing the similar actions. So right now it's still a little bit unclear, and we've still got to focus on a bit more exactly to pin down what the domain shift is. However, there's a combination of different factors that it's likely to be. But from we've seen that it's not just the environmental shift. There's different play within the same participants who have stayed that we've noticed, and the performance on the target domain is very similar to participants who have moved, as well as participants who have stayed in the same environment in the target domain.
Interesting. Next question is for Antonino on the action detection task. So what would you say the difference is between action detection on EPIC are to action detection on other existing data sets?
So when we compared EPIC kitchens with other data sets, and you can find a table for comparison in our paper, so we noticed that our data set is denser. That's probably because of the actions we are targeting. So we are targeting interactions with objects, which can be very short. So rather than having high-level actions, we have all these tiny short actions. Also, as it resulted from already labeling EPIC Kitchens 55, defining the boundaries for these actions is not very easy. So that's also why we used these thresholds ranging from 0.1 to 0.5, while instead most other datasets are using a threshold of up to 0.9, because it's not very clear when an action starts and ends. So I think that having many actions in one video, so a lot of actions and very short actions, makes this difference. Actually, we had some let's say some trouble with the baseline, because the baseline assumes that like the features for a video are resized with interpolation to a tensor, and this way you have different resolutions for videos of different lengths. And this is probably because that method has been optimized on dataset with videos of similar lengths. So I think these are differences which make the dataset interesting for this task.
Thanks. So is there like a noticeable performance difference on the size of the videos? Because I know in EPIC they vary quite a bit.
Yeah, I would say so. Given the results that we have currently on the leaderboard, I would say that's something that affects performance.
Okay, so next a question to Will. So you've been running the action detection challenge for 2 years already. So what conclusions do you have about that challenge?
That's a good question. I think one thing that we've seen is that pre-training seems to help. So most of the top ranking methods tend to use heavy pre-training. So and also large model ensembles tend to do very well as well. So we've seen people use object features, just taking lots of different models that have been supervised in different ways, extracting features from the videos and combining all of those to really sort of bump up performance. So I think we'll continue to see that style of thing, perhaps increasingly so. So we also released some automatic annotations. So we have mask RCNN masks and hand object detection. So I think it will be interesting to see how the community use them, and I'm sure we'll definitely see people leveraging them for action recognition.
Thanks. And I guess the same question to Antonino about the action anticipation challenge. That's been running a few years already. Is there sort of general trends you see in the methods there and what you think will happen in the future?
Yeah, I mean, that's a good question as well. Yeah, we have seen methods improving over the baselines in the last challenges. So
I think you're getting cut off a little bit.
Yeah, maybe it was a network issue. I think
Yeah, but maybe
Can
just
you hear me well
repeat
now?
that again.
Yeah, sure. So we have seen when testing the baselines, we have seen little difference between the old dataset and the new dataset. So I'm not anticipating that having a lot of more annotations is going to make a big difference. Of course, having more data is always useful, but this is probably not the case for anticipation at the current stage. And well, I think we'll see what will happen. We also changed the metrics, so this is probably going to help assessing better the results, because what we noticed with the old metrics is that there was a bias because of long tail distribution. So methods could achieve very good performance by just predicting the most frequent actions. This is because we were using top 5. So I think I'm also excited to see results of the old methods on the new leaderboards, mainly for the new metric, and see what happens.
Great. So another question, I guess Giovanni can take this one. So have you seen a rise in the EPIC community since the dataset's been released?
Yeah, I think there is a really big interest to have common datasets and bigger datasets with well-defined challenges. And the first EPIC challenges were opening this way of thinking and new challenges, and working all together as a community to define also the metrics to evaluate and how to evaluate the problems. This second release will give us opportunities also to understand which are the new ideas or on this new datasets. We have more challenges, and as we can see with Dima already told, this dataset is going to be used for many other things. We don't really know what is going to happen in the next future. The good thing is that is appreciated by the community. As Dima told, this is a voluntary work. It's a big effort, and we'll say that it's not simple, not only collecting data as all of us knows, but also labeling data and so on. So let's see what happens in the future. But for sure, EPIC Kitchens opened a new way of co-working also on new datasets to open new challenges and see what results we can have in the future computer vision community.
And another question for Dima. So you said that there was opportunity for people to create new challenges on the EPIC Kitchens. Are there any others you've got in the pipelines currently or are thinking about?
Yeah, we've just survived putting this up, so I think kind of our brains are currently empty. I think there are a few things we want to revisit. So we have the object detection challenge that we had in the first round. We have not manually annotated additional object bounding boxes due to a number of things that we've discovered. We're now looking at how else we can look at this. Interestingly, the majority of people who've used those use them for object tracking, so video object segmentation. So that seems to be an obvious one, but not an easy one to set up in terms of annotations, etc. And we are in collaborations with a number of interested parties to see how we can set this up, but it will take a little bit of a while. We were considering at some point what we call like a pentathon, where people attempt all these 5 challenges in one go. And at some point we were kind of very excited. We realized there's some of these are very, very early stages. So the unsupervised domain adaptation, this will form the first real video baseline for unsupervised domain adaptation. So we found that these are at different, let's say, levels of maturity in the research community. So we want to observe how they progress. There is a real interest in, I have a real interest in weekly supervised, but that currently is integrated within the leaderboards. The question is if there are enough takers or interested parties, then we can set their own kind of set of winners. If we have enough people who are interested in few shot or in weekly supervised, and we have a number of submissions, then we're open to announcing winners on this less supervision. At the end of the day, we have to think about how we can scale either scale by less labeled data or by less data altogether. Otherwise, the community, if we assume that the objective is to collect hundreds of thousands of hours before we can produce any useful applications in assistive technologies or in robot imitation learning, then we will be halting the progress because of understanding footage from wearable computing. So it is our, let's say, duty to people who will benefit from the outcome of this research, because eventually perception is entry. Like you achieve something and you can utilize the perception you've gathered to produce some application. So basically computer vision by itself, especially in wearable, is not the application. The application is how you can utilize the outcome. So if we are to achieve these outcomes, we have to think about how we can leverage data sets of this sort to achieve impact. And maybe, let's say, looking at less supervision within Epic Kitchen is currently our way forward. But again, we're open to what many others might have seen that we might have not observed on the data set. Even without the vision, I noticed that there is a very recent work that has looked purely at our narrations as evidence of human understanding or human behavior. So I think we look forward to seeing how the data set will be used.
Great. Thank you, everyone. I think it's time for our first keynote now. So we're delighted to have Bernard Garnham, who's currently an associate professor at KAUST, where he leads the Image and Video Understanding Lab. He's also an adjunct senior research scientist at the Advanced Sciences Digital Center of Illinois and Singapore, where he's PI on the semantic analysis of video project. He completed his PhD at the University of Illinois in Urbana-Champaign with a focus on modeling dynamic textures from video for synthesis, compression, and activity recognition. So he's got a wealth of experience in topics in video understanding, notably with the creation of the activity data set. And we're looking forward to his talk today. So I'll hand over to him now.
All right, thank you, Hazel, for the kind introduction. Let me start sharing my slides. All right, there we go. Okay, so let me first thank Dima, Giovanni, and all the rest of the organizers for all their efforts on EPIC. And really, on behalf of the community as a whole, we really commend you for all these humongous efforts that you've been putting into EPIC, the challenge, and the data set. Coming from ActivityNet, I do appreciate all the efforts you've been putting into this. And not to be cheesy, really, EPIC Workshop is becoming quite epic. So I'm really happy to be here and to be presenting to you. So today, my talk is going to be focused on richer video representations, particularly two elements of that. The pre-training, and Dima and the organizers have showed that how important different levels of supervision are. I'll specifically be talking about self-supervision for the video representations and showing a really exciting result that we just very recently got. And the other one is about enriching video representations using context, specifically through graphical convolutional networks, and how we can make use of GCNs for various tasks that have to do with untrimmed video, and especially those tasks that have to do with temporal localization of particular attributes. So video grounding, temporal action localization, and so forth. All right, so these two recent works that I'll be talking about really came up from lessons learned over the last 5 years of us hosting the ActivityNet Challenge. I think even last year, 2019, EPIC was part of the workshop then. And over the last 5 years, I mean, we've been hosting this challenge with a variety of quite a good number of participants and submissions from all around. It's in addition to the guest tasks that we host, so kinetics, Ava, and sometimes EPIC and other data sets, other tasks. We also have temporal action localization tasks on the ActivityNet dataset, and dense captioning task on the ActivityNet dataset also. So the two work that I'm going to be focusing on today are going to be based on lessons learned that we have accumulated over the last 5 years of this challenge. So just to remind everybody, and I think it was already presented about what activity localization is about. Well, you have an untrimmed video and you want to be able to localize the beginning and end of the interval in which this activity actually happens. Okay, so the input is a video, the output is an interval, start and ending time, and the class label of the activity. Okay, so how have things evolved? Well, in terms of the pure metric, this average mean AP over various IOU thresholds, TIOU thresholds, it's increasing. It's increased since 2016, which is a good sign. However, I mean, a single scalar metric can't really sum up performance and how the trend is going. If you do a deep dive into the winners of the last few ActivityNet temporal action localization tasks, and this is a analysis that we use usually to understand where the errors are for each of these winners. You see, I know this plot is a little bit dense, but you see that on the x-axis you have the top predictions that you produce as the output of your detector. The G here could be 1,000, so it could be the top 1,000 ranking predictions, then the next 1,000, the third 1,000, and so forth. And then for each of these top prediction bins, you figure out what is the percentage of errors that are accumulating in each of these in all of these predictions. You see that among all the types of errors that could happen, the wrong label error doesn't happen much. That's the one in blue, and which means that classification is, we're doing a good job at classifying the particular interval, but the red piece of the plot is very, very large. And even for this year's winner, which is the last plot on the right, it's very, very large, which indicates the errors that we accumulate when we try to localize these activities. I mean, the beginning and ending of these boundaries. Of course, I mean, what people might say, oh, it's because the ground truth itself has some kind of error or mistakes in determining these boundaries, but we've done quite a bit of work on the data set itself and on the analysis, and we can confirm that that's not the main reason why these errors are occurring. The main reason these localization errors are occurring are we're not able to find these boundaries, and the main issue here is the video encoding. And we'll see in the first work that I'm going to be talking about, video encoding is very important. So, and how you start out with a good video representation that could help you find the boundaries better. So that's kind of the first observation that we've had over the last 5 years. And kind of the way to improve this observation or improve this issue or resolve this issue is to use self-supervised learning for video and a specific pretext task that we call cross-modal deep clustering. And we'll talk about that in a bit. Now, the other lesson learned from the last 5 years is the effect of context on detection. So I think it was mentioned about this feature anticipation of for video in the EPIC dataset. So what we did in ActivityNet was we ran a human subject study where we gave the humans, we showed them the videos up until a certain context frame. These are indicated in red here. And then we asked them, for example, looking into the future or looking into the past, can you determine what's going to happen next in terms of the ActivityNet classes? And so the size of the context, that means how far away the last frame that the annotator sees before or after the actual action is varied. So we call that context size. And so if you look at kind of the results that we got from the human annotators, we saw that there are 32% of ground truth activities in ActivityNet can be reliably recognized by human annotators, even though they're at 6 context sizes or units from the actual activity, meaning people can use context quite a bit to determine what's coming up in the future or in the past. And then there's the context sizes of 5 and so forth. Context size 0 means that these are activity instances that are whose context is very different from them. For example, at scene shots, at scene shot boundaries or whatnot, where the context is very different from the activity itself, and therefore knowing the context doesn't help you in determining what the action is. So you see a good portion of these ground truth activities can be recognized from far away reasonably. So what about methods that we build to try to detect these types of activities? Well, this is the winner of the ActivityNet Challenge this year from June, and as you can see, we're plotting the average mean AP for the different bins of activities in the ground truth. And as you can see, the ones that actually the mean AP is the highest at the places where at the activity instances that don't need context. And as we look at the activity instances that can be recognized by human annotators with more context, we see that the mean AP actually monotonically decreases. This is a bad sign. It means that these detectors are not able to exploit temporal context well. And so that's the second observation. And what we're going to be talking about later on is using GCNs or graph convolutional networks to try to encourage and enrich the video representation to allow for context and more temporal context. Okay, so the next work, the first work that we're going to talk about, I want to remind you relates to the first observation about pre-training and how making or providing better video encoders for the community. We're not going to be talking about particular architectures. So of course you can have your slow fast, you can have your R2+1D. This work is agnostic to the actual network architecture used. We do use a particular architecture, but it's just for convenience. We're going to show that with a specific type of self-supervised learning pretext task, we can build video and audio encoders that actually do very, very well on downstream tasks, even though they're not using any actual labels. But you have to reach a scale, at a certain scale of pre-training data set, you will reach this kind of interesting result. All right, let's dive in. So I don't want to bore you with reasoning why we're interested in self-supervision. The kind of overarching goal is to make use of all the data that's out there that's not annotated. So imagine, YouTube and other popular video platforms where you have hundreds of hours of video being uploaded every minute. Imagine all that plethora of video that's accessible, but it's not annotated really. Instagram is another example also of this. So we can't go about annotating videos, beyond what we have right now, I guess. Well, if we wanted to annotate 100 times more than ActivityNet or Epic or whatnot, that'll be very expensive and time consuming. So is there another way out? Well, the goal is to design a particular pretext task that one can learn from video by just looking at the video and the audio. Here we're going to use multimodalities. We'll talk about some prior work that only looked at one single modality. So how do you design a pretext task that can actually learn some from the correlation between video and audio that can transfer over to downstream tasks? For example, action recognition, even audio event classification. And can we really come up with a self-supervised pre-training model that outperforms fully supervised pre-training on large scale data sets like kinetics? And that's the most exciting result. The answer is yes here. All right, so there's been quite a bit of work on SSL or self-supervised learning, more so in the image domain than the video domain, but there's been quite a bit of work on SSL in the video domain. Most of the pretext tasks that have been proposed have been either in predicting future features, like in ECCV2020, or using contrastive learning to predict whether two chunks should be similar or not from each other. That's in terms of using just the video itself, just one stream, one modality. But there's been quite a bit of work on incorporating multiple modalities together and leveraging the correlations between these modalities to be able to analyze or produce encoders for both the various modalities. So usually the modalities of interest that people have used are video and audio, for example. But there's been recent work also on using video and text through instructional videos, the how-to 100 million that was produced. So in these cases, the pretext task here would be usually some kind of a contrastive learning task to figure out whether the video or the audio streams are synchronized or if they match, and similarly, the video and the text can be done that way. So having said that, this is kind of it's not a thorough or a complete landscape of the related work, but a lot of the major methods are in here. So, so the idea that we based our method on was on deep clustering. So deep clustering is a self-supervised learning method that was originally produced for images, where you, instead of looking at instances and determining whether they're synchronized or not, or tuples of instances, you look at clustering, how these things cluster in the training set. So given some input images, you have initial instantiation of your ConvNet. The features of the output are clustered. They produce pseudo labels that define a classification task, which you use to update your ConvNet, and then you do that over and over and over again in an iterative fashion. Okay, so what we're proposing here is a cross-modal version of deep clustering. Which means that imagine you have multiple modalities, for example, here in this case, video and audio, but it could apply to video and text and more than 2 modalities at a time. So there's different ways of actually doing deep clustering for various modalities. And one way to do that is by simply saying, well, they're all independent. The video and the audio stream are independent. And as you see here, you have an encoder for the video on the left and an encoder for the audio on the right. And so what you do is you just cluster each of the different modality features independently and then train them independently. Now, obviously, that doesn't exploit the correlations between video and audio, because videos that look very similar tend to have similar audio and vice versa. It's not generally the case. It's not always the case, but generally it's a good assumption. So that's one way of doing it, and assuming everything is independent. This is obviously not the best way to do it. But if you wanted to combine these different modalities together, how could you do it? Well, we've envisioned 3 ways of doing this. One is the multi-head deep clustering, which is each of individual modality here is producing its own clusters, but each modality is being asked to, so you're going to use the features of the video, for example, to classify which cluster the video belongs in terms of the video modality and the audio modality together. So it has 2 different heads predicted from one modality. The other one is CDC, which is concatenation deep clustering, which is basically simply done as it's as simple as concatenating the video feature and the audio feature together, and then doing deep clustering on that concatenated feature. And then once you cluster that, generate pseudo labels that can be used to backpropagate through both encoders. And then the last one, which is the one that actually works the best for us, is the cross-modality one, whereby you take the clustering of the video features to create pseudo labels used to update the audio encoder only. And then you do the same thing for audio clusters to update the video encoder. And that ended up working the best. And we have some intuitions on why that is. So that's called XTC. So in this project, really, I mean, to show that this type of SSL pretext task works so well, you really need to do a massive amount of experiments, and especially at the scale in which you can show that your method can actually improve upon fully supervised pre-training, right? So, the method that we just described, it doesn't use contrastive learning particularly. So basically, it's very easily scalable to large data sets without much change in methodology. There's some, issues with contrastive learning in terms of picking which negatives to use, especially when the data becomes larger. So it's still a research there's still some research need to be done to get it to scale to very large pre-training data set sizes. However, with deep clustering, with this XDC, really nothing special has to be done, really. You're just doing clustering using k-means, updating both the audio and video encoders, and then you do that iteratively. So to do these types of experiments, we need various pre-training data sets. We will have the Kinetics 400 data set, where we're only going to be using the videos there, videos and audios. We're not going to be using the labels. So whenever I talk about SSL, the pretext task, this XDC pretext text, we never use the labels of the pre-training data set if they are available. All right. So we'll be using the Kinetics 400 one, which is a relatively small 250,000 video data set. There's an audio set one, which is 2 million in total, and we subset, we generate a random subset from it to give it the same size as Kinetics. Also, we have the Instagram 65 million, which is based on weekly labeled hashtags from Instagram. And then there's a 65 million random data set, which is totally uncurated, basically 65 million random videos on Instagram that have audio. And the downstream tasks that we're going to be focusing on are action recognition in HMDB and UCF 101, and then audio event classification on ESC and DCase. All right. So the first result that comes out is, well, how do you compare the SDC, MDC, CDC, and XDC with each other and with respect to training from scratch? Obviously, it does better than scratch. That's great. But it does better than random initialization on the particular downstream tasks. What about in relation to each other? Well, XDC is the winner here, and we have an intuition of why that is. It's better than CDC, where you concatenate the audio and video, because in XDC, you're saying that videos that look similar should have similar audio, and videos that sound similar should have similar video. However, with the CDC, you're saying that videos that have similar audio and video should be clustered together. And that way your clusters are really compact, and there's not that much diversity within clusters. So this could be a reason why it's underperforming. With MDC, the issue there is in training. So training different modalities together jointly, and this is what MDC does because it uses multiple heads, is tricky because each modality learns at a different rate. And so you have to be, you have to figure out what kind of trade-off to use in training them. So one might be faster than the other. And so you have to do a good job at varying that. And that is dataset dependent also. So we're guessing that that's the reason why MDC underperforms. And of course, SDC doesn't use the correlation whatsoever, so it doesn't benefit from that. Now, regarding the XDC and fully supervised pre-training, which is pre-training on kinetics using the actual labels, it's doing worse. And the reason why is that XDC was pre-trained on kinetics video. So those 250,000 videos that were used for pre-training XDC without the labels, they were used with the labels to do the supervised pre-training. But we'll see in the next slides that as you increase the size of the pre-training data set, so going from 250,000, the kinetics size pre-training to something bigger. So here, the ones in blue are basically what we just talked about. So you see that the kinetics supervised pre-training does better than XDC pre-training on kinetics videos alone without the labels. But if you compare that to pre-training using XDC on progressively larger data sets, so 250,000, 2 million, 65 million, you see that there's a consistent improvement. And actually, we reach a point where we do better than supervised pre-training with kinetics. And so this is the kind of exciting result here that, with self-supervision you could actually outperform supervised pre-training on very large data sets. Kinetics is a large data set that's fully supervised, fully annotated, sorry. Now, having said that, what about the two versions of Instagram for 65 million, the random one and the kinetics one? The kinetics version was based on hashtags related to kinetics labels. So one might say that, okay, you're a little bit cheating here because you're using labels that are similar to the hashtags in Instagram when collecting data set. Although we know that hashtags are not necessarily representative of what's in the content of the video. So we curated we put together a random subset of 65 million videos, same size as the Instagram Kinetics data set, but now totally random. There's no use of hashtags here. Just make sure that the video has audio and of a certain size, and that's all kind of the restrictions that we have. So we see as we increase the size of the pre-training data, the delta, the performance difference using the different types of Instagram data sets, the one that's uncurated and the other one that's weakly curated, you see that, you know, as the pre-training size increases, you see that the delta decreases, and in some cases actually it outperforms the kinetics version. So this just goes to say that with enough scale, we expect XTC to actually, even on fully randomly sampled videos out there, it should outperform, eventually outperform even the weakly curated, very weakly curated Instagram Kinetics data set, which is actually an exciting one. So if you have the computational resources to do this, and you have access to that many videos from your data set without needing any kind of labels whatsoever, you should be able to improve upon, of course, fully supervised pre-training and this very weakly supervised pre-training also. So going forward and showing all of these experiments in the context of state-of-the-art. So there are some SSL methods out there before, like AVTS and DBC that we saw in the related work part. We want to compare all of them together. And I mean, if they all use the same pre-training data set, which is the 240,000 videos from Kinetics, we see that XCC is better, but marginally better than AVTS. However, as you increase the data set, again, as you increase the data set of the pre-training that we have, so audio set is 2 million videos. It's about 4 times bigger than Kinetics, sorry, 8 times bigger than Kinetics. You see that the gap between the different self-supervision pretext stacks or models improve. And the reason why that is because we assume because it's very, or the intuition here is that it's very easy to scale XTC, as opposed to maybe some contrastive learning method that requires you to pick the negatives in a smarter way, maybe, or using curriculum learning, maybe. So it's easier to scale XTC to such sizes. And if you go even beyond that to the Instagram ones, we see even a bigger push. By the way, these numbers are different from what we saw before because the setting is done in a different way. So we want to make sure that all the methods use the same setting. And so the numbers are a little bit better. But as you see, if you compare the XTC pre-trained on Instagram Kinetics or Instagram Random, they're both better than fully supervised pre-training using Kinetics, and of course better than fully supervised ImageNet pre-training. So it's quite exciting, the result that we've reached to, and we hope that this pre-training can be used in other tasks. And I'll just mention that you know, this type of pre-training was used with our with the detector that we'll talk about later, and it did by just simply switching out the frozen video encoder with XTC, it actually added a 1% improvement on the temporal action localization performance. So we're hoping that the community can embrace these pre-trained models and features and use them for a variety of tasks. Oh yeah, I forgot about this one. I mean, of course, it also improves not only the video only tasks, but it also improves audio tasks. So the audio event localization classification tasks on DCase and on ESC. I don't know if I'll be able to sound these videos out, but I don't know if you hear the audio, but these are kind of the clusters that you get when you cluster the audio features and the video features. So you see that over here, without, I don't know if the audio is playing, but over here these are video clusters, meaning that the videos themselves look similar, the video features look similar, but the audio, if you actually play it, the audio is quite different. Same thing with these over here too. And so on the other side, the audio clusters are basically videos or video chunks that look similar, but they sound similar, but they look quite different. And so you see here, I don't know if you heard the bagpipe in the background, and then you have more bagpipes over there, And same thing over here with the football commentary. All right. As opposed to the hockey commentary. Although they look very different, they were clustered together with the, and this is basically clustering based on just the features that come out of the different encoders. All right, so having said that, we get to the second observation, which is about making use of temporal context and the fact that we're in need of methods that actually make use of this temporal context. And this is work based on a paper that we published in CVPR this year, it follows up on a well-known issue that we have with untrimmed video, the fact that we use clip encoders. That means we take a clip encoder, like let's say a slow fast R2+1D or whatever encoder that's your favorite, and you apply it on clips within the video. All right, so you don't apply it on the whole video, right? So you apply it on a clip, and therefore the feature used to, or the output of this clip encoder only really represents that clip, that few second clip or a few frame clip. And therefore, it doesn't make use of context beyond the extremities of this clip. And so what needs to be done afterwards to process this kind of context is to imagine that these clips are in a graph of some sort, and then encourage them to talk to each other, to interact, to aggregate their features to generate a different level of feature representation. That can be done in a multiplicity of ways. For example, people have seen that non-local blocks can be used here. Transformers can also be used, self-attention. They're very synonymous to each other in terms of the operations that they perform. However, they're notoriously known to be expensive because you need to basically connect all the nodes in the input to be able to aggregate one output feature, and that's expensive. Is there any other way to look at videos as a graph and not need to do this type of end-to-end, n is the number of nodes, end-to-end kind of correlations? Now, one thing that one has to keep in mind is that usually what we usually know is that we want to go deeper with representations so that we can produce better or richer representations, right? So this is usually what we do. So this is why you see a ResNet 100 plus layers. We rarely see any encoder that has more than a few transformer layers or non-local block layers, non-local block layers. And the reason is computationally and training these things is finicky because with all the parameters that are there, and it's not impossible. I'm guessing somebody could come in and show that it is possible, but it's not the kind of straightforward. And you rarely see 100. You don't see at all. I don't know of any encoder that has that uses non-local blocks at 100 layers in composition. However, are there any other tools at our disposal that we can make use of to be able to combine these different nodes together in order to aggregate information? And instead of considering these clips as nodes in a graph and then completely connecting them, so every pair of nodes is connected, which is usually what's done in transformers and in non-local block, are there any other ways? Well, there is a way. There's the GCN operators, these graph convolutional network operators that aggregate information from between a node and its neighbor, similar in the way that CNNs do it, but the neighbors and CNNs are spatial neighbors. They don't change. Here, depending on the graph structure, you could have 4 neighbors or 3 or so forth. So the number of neighbors per node is different, and these neighbors actually could change. And so you aggregate information from your neighbors through a similar kind of update rule that CNNs use. However, I mean, and here's the kind of the overall update rule that usually is used. I know it looks nasty, but it's if you think about it, it's like a generalization of what's happening in the CNN world also. So it's basically, it says that the new feature here at the output of the layer K is a combination of the previous feature of that node with an aggregation of the node with its neighbors. And this neighborhood here defines the neighborhood of the node I at layer K-1. As you might see that this neighborhood is indexed by K-1. So it is a neighborhood that could change from layer to layer. It's actually and it's a function of I. So it changes with respect to the node and the layer itself. And for example, one way to create this neighborhood is through k-nearest neighbors on the features of the previous layer. So basically, and this is where it's very different from CNNs, your neighborhood could change from one layer to another. And therefore, you could learn which neighbors you want to combine with each other to be able to get a better representation for your eventual task. That's similar to what transformers are doing and non-local block, but they're combining everything with everything. So here, the neighborhood is smaller, much smaller in size, and so therefore it's manageable. So as you can see, and this is a paper from ECCV last year, where basically we showed that you can go 100 layers deep with GCNs. Maybe for 3D point cloud applications, this wasn't applied to video yet, but we showed that it's possible to train 100 layer plus deep GCN, which was not possible before. And we, this is possible through producing residual dense connections, dilated convolutions, multi-scale blocks, dropout, batch norm, but all for graph processing. Okay, so right now it's integrated in PyTorch Geometric, a very well-known graph-based deep learning platform. And it's being used in a lot of applications. We have more than 1,000 stars on GitHub with this, and people are really using it for a variety of purposes. Now, most of these purposes have been 3D point cloud processing because point clouds are graphs, but also people have been using for generic graphs like protein-protein interaction graphs, citation graphs, and so forth. So if you're interested, go to deepgcns.org and then look at any of the repos there to maybe see if it fits your application. But one application that we wanted to have it incorporated is with video. And the reason why is that you could actually interpret video in a different way now as a graph. And one way that we visualize a video now is that every dot here is a clip in the video, and the time axis is counterclockwise. And so every red dot is the start of an action, and every blue dot is the end of an action. So this here, from here to here, all these green clips constitute one activity, grounded activity. The yellow are background activities, background clips. And then there's another activity that's shorter over here, right? So this is kind of a newer way of representing a video as a graph of clips. So this node over here that's red, it's connected to the subsequent clip that goes in front of it in the time domain, but it also is connected to something that's yellow over here. And these gray connections are from our so-called semantic graph connections, which are based on a k-nearest neighborhood based on the feature of the clip itself, right? So you have temporal connections, which follows the temporal domain, and you have these long-reaching, possibly long-reaching semantic connections that have to do with the features of the clip itself. And by doing that, you're actually expanding the context that these clips have without having to connect every node to every other node. All right, so this is a kind of new way of representing these videos. And so before I get to here, so temporal action localization becomes the task of finding this start and end point within the overall graph, meaning finding a subgraph within the overall graph itself. Okay, so and to be able to do that, well, we followed a faster CNN-like pipeline where we will use something called a GC next block, which actually creates two types of graphs for the video. Because there could be two types of context. There could be a temporal context, which means the clips that are coming before and after you, and there could be these semantic connections or neighbors where they are neighbors that are related to you in the feature space. And so if you create these two types of graphs and you combine them in a GCN kind of way, and you can stack these GC next blocks in composition, you create a multi-connected graph. And then your task of detection becomes the task of finding subgraphs within the graph that align, that have certain attributes. And so similar to what ResNet, faster SNN does, you have an ROI align operation. Here we have a SGR, subgraph align operation, where we align and interpolate each subgraph into a particular fixed size. And then we do regression of the bounding box, the interval, temporal interval, and we output a classification score for it. So the localization module, I mean, you could think of it as just the analogy of faster RCNN, but for graphs. While the kind of innovation is in this feature representation. So these GCNext layers, the reason why we called it that is because they are GCN operators using a ResNext-like formulation. So they do GCN operations, but in a way that looks like ResNext in the following way. So in the semantic graph connectivity, so where you connect yourself to your k-nearest neighbors, you produce a 256-dimensional output for every node. That it can be broken up into many 4-dimensional pieces, and each piece can be convolved in more efficiently in that lower dimensional space. This is very similar to ResNext. And this temporal graph is something different because it connects the nodes in a temporal way. That means if you're consecutive to me or close to me in time, you're connected to me. Otherwise, you're not connected at all. So this shows you two types of contexts that could be used, and they're aggregated at the output of every GCNext layer. And given the fact what all the tricks that we've implemented for deep GCNs, you can actually compose as many GCNext blocks as you want, really. I think in the paper we only used like a few because that's all what we needed on the data sets that we had. But in essence, you could use as many as you want because we have mechanisms to go deep. And just to, as in a nutshell, without doing any like fancy stuff that's related to the data set or whatnot, we can, with GTAD, with this mechanism that I just showed you, we can actually get state-of-the-art results on both TUMOS and on ActivityNet, again, without much extra work. And the majority of this improvement is coming from these GCNext blocks that actually enrich the feature representation of the different clips. Like I said before, if you took the XDC pre-trained features and freeze them and use them instead of the, I think, TSM or TSN features used by GTAD and BMN and so forth, you can actually improve upon these results by another 1% by just using a different type of encoder. So, but irrespective of the actual numbers and how well it does, but I mean, are there any indications that it's learning something useful? And the answer we think is yes, because if you take a particular video whose representation as a graph is like this circle, so you see connectivity. This is after training and at the last layer, you see connectivity between yellow clips that are background and green clips that are foreground. That means there is some learning of interactions between foreground and background to produce the final result. So if you took that video and you took another video, which had as a different background to foreground kind of diversity, and they're from two different classes altogether, and you merged them, meaning that you took the background from this right-hand side video and you merged it with the foreground, which is the activity of this video. And then you recomputed so you made a fake video basically, and you recomputed the connections because again, like I told you in GCNext modules, when you're creating these dynamic connections, you're basing it on the current features of the nodes of the clips. And you see now that there is no connectivity between the background and the foreground. There's only connectivity between the foreground clips and the background clips themselves, which means that, I mean, there are contexts that help you in determining your label, and there are contexts that don't help you. And this is a good indication that this context is adaptive with dynamic GCNs that we have in our GCNext blocks. I know I'm over time already, but I want to get to some questions. But let me just say that also a very recent result that we have, it's not even a result, we're still working on it, is that this GCNext kind of idea and these modules that we have can also be used in other tasks that have to do with localizing certain properties in video. So for example, here's a video grounding task where you have a text that you want to ground temporally in a video. So you're given a query in text and then you want to ground it in video. And so text can also be seen as a graph by using some parsing of the language and by encoding both the video and the language with this GCNext block, and then using a GCN-based graph matching technique, you can actually do this grounding without any really, I mean, we haven't really explored all the various ways of doing this, but with just this simple kind of encoding, we can, on the ActivityNet captions dataset for grounding, we can use the VLGSRs, we can easily get better results than the state-of-the-art methods, including one from this ECCV. So I really think that this idea of graph-based context enriching representations that we have here could help in efficiently encoding context and therefore enriching the clip-based features for downstream video tasks, including video grounding, action localization, and so forth. And with that, I'll leave the floor for any questions that there might be. And thank you for attending, and I'm looking forward to your questions.
Great, thank you very much. That was really interesting. So we have a few questions. So we'll start off with some questions on the self-supervised part. So Dima is asking, most self-supervised methods on video tend to report fine-tuning on UCF and HMDB. And we know both of those are fairly saturated data sets by now. And it seems to be a trend between multiple self-supervised learning works. So why do you think that's the case? And do you think the self-supervised features would be suitable for action detection in something like ActivityNet, Kinetics, or even maybe Epic Kitchens?
Right. So I think with UCF, that's right. I mean, with high 90s, I mean, one can reach high 90s now with self-supervision. I'm showing on the slide of this evaluation. HMDB is a different. I don't think we've saturated yet. But the reason why we use these data sets is because these are small. These are small enough data sets where training something from scratch on them doesn't give you the best results. So of course, we would like to expand upon XTC's ability to learn strong encoding on bigger data sets. And ActivityNet for sure, we want to, I mean, because it's our own also, we want to see how much improvement we can get on that. But I think by just looking at these results right now, they're pretty strong. And the reason, I'm guessing, just like everybody else, the reason why we picked these two data sets specifically is because you have comparative numbers on them to be able to compare against them fairly. But I think now, I mean, one can take XTC and train it on Instagram or bigger data sets, and then use it for a variety of other tasks. And this is we're reaching out to the community to help us with that, actually, and we will be releasing the XTC pre-trained models and the features for particular data sets soon.
Okay, so there's another question about the MDC method. So someone's saying that it gives richer information than an XDC because MDC has pseudo labels from both RGB and audio. So why is MDC much worse than CDC and XDC?
Yeah, so I mentioned that earlier. Let me go back to it. Yeah, so the rich information is that you have access to. So you still have. Let me just go to the. Yeah, here we go. So this is MDC. The information that you have access to is the video encoding. So let's say you're looking at this task over here. You have the video feature. You're asked to take the video feature and classify two things. Basically, the video category and the audio category generated by clustering of the two different modalities. Our intuition of why this doesn't work as well as XTC is the fact that training becomes harder, especially at scale. Because in the loss that you have here, this is a multi-headed output. Therefore, you have a task loss, where you have a classification loss for the video side, for the video pseudo labels, and a loss for the audio ones. And so people have shown before that blending these modalities is not an easy way to do it, especially if you do it, and it's not as easy as having just one type of loss or two losses that actually can be learned at the same speed. What we've seen empirically is that the audio side tends to be faster in learning than the video side, and that leads to mismatches. And we believe that this is the reason why the MDC doesn't work as well. Again, so I mean, if somebody were to come in and figure out a better way of reliably training with this joint loss at a large scale, I think this opens up the work for even more progress.
Great, thanks. And another question from the audience. So self-supervised learning on for self-supervised learning on video, do you have any ideas or suggestions for researchers that can't use like huge data sets like the Instagram data set? And how can they make comparisons to work such as XDC?
Well, so let me go back to the list of authors, and there's a reason why this work was done at Facebook AI, and this happened while a student of mine was interning there. Unfortunately, at those scales, I think it's going to be hard for academic institutions, including CAUS, to be able to do such, CAUS by itself, to be able to do such experimentation, unfortunately. However, I think there is some interest in figuring out whether you need all those 65 million Instagram videos. So if you think about it, if you take an active learning approach to it, do I need all 65 million videos to be able to reach the same point or a similar point as we did here? I think that's kind of one line of research that could be interesting. So merging active learning, picking which of the 65 million or which of the million videos to use in your XCC training could be something interesting. But in general, I mean, I think it's for the majority of academic institutions out there, this work wouldn't be able to be possible at such scales. Especially, I mean, at least at CAUS, it wasn't possible.
Great. And then a question about the graph convolutions. So how do you know that the link between foreground and background is helpful? The fact that they're connected could be because features are very similar and it might actually be harmful.
That's a good question. If it were harmful, then it would have led to performance degradation. That's number one. So what the GCNext layer is doing is trying to figure out what the connectivity should be to best improve the loss, right? So if the loss is going down and the performance is improving, it means it's finding some kind of a correlation that's helpful. And the nice thing with this is that, like I said, it's adaptive. So that means given a video with the same foreground but different background, the results are not going to be the same. But if you don't do this kind of adaptive context enriching, you will suffer in terms of performance because it's not adaptive. So the results show us that performance is improving. Therefore, we assume that the correlations are increasing. And we've tried it on video where the context is completely unuseful to so it's basically multiple shots glued next to each other. And we've seen that it learns that there should be no connections between foreground and background in that case. So I think we have intuitions that this is actually helping the localization effort.
Great. Well, I think that's all the questions. So thank you again for the talk.
Okay.
It was very interesting. And now I think we're just going for a 10-minute coffee break before the next keynote. So we'll be back in 10 minutes. And Federico, if you want to test your setup, please go ahead.
Yes, let me try to see the video. Okay, you should see my screen now.
Yeah, we can see your screen.
Okay, let me just see how the video plays. How does it look?
Yeah, it seems to be working fine.
Okay.
Mike's saying the video is a bit choppy on the YouTube rebroadcast. Can you just check that you've got the, you know, when you share screen, you ticked optimize for video? Should be an option somewhere.
In
Zoom, I think when you start sharing, I think you can tick optimize for video.
okay, let me try again.
It's just a little tick box at the bottom, I think.
Is it better?
Yes, I think that's better.
It's great to have you here, Federica. We look forward to the talk.
Thank you.
It's time to get a coffee break. Is always helpful at the start of the conference.
So I guess we can begin with the second half of the morning, maybe 1 minute more to be on the clock. Okay, so I guess we can start with the second half of the morning session. So we're gonna have, in the second half, we're gonna have the invited keynote by Federica Bogo, and then we're gonna have paper presentations, and then there's gonna be the lunch break. So let me briefly introduce Federica. She got her PhD in computer vision from the University of Padova, and she has been, after that, a postdoctoral researcher at the Max Planck Institute for Intelligent Systems. And in 2016, she joined Microsoft, and now she is a senior scientist at the Microsoft Mixed Reality and AI Lab in Zurich. Her research has been focusing on human body modeling early in her career, and more recently on hand-object interaction, reconstruction, and recognition. And from the title of the talk, I guess she's going to talk about the exciting progresses on HoloLens and understanding hands, object, and actions. So we're looking forward to her talk, and thank you for the keynote.
Okay, thank you very much for the introduction. And I would just thank you also the organizer for giving me the opportunity to be here. During my keynote, I present some work I contributed to, but I also come up with a few research questions, so I would be very happy to discuss them with you today. So today, I'm going to talk about the importance of reasoning about hands, object, and their interaction in mixed reality scenarios. So the talk will consist of 3 main parts. I start by giving an overview of the work behind the fully articulated hand tracking for HoloLens 2. This was a great experience for me since it showed me the long journey it takes to go from a paper to shipping a product. The HoloLens 2 hand tracker enables great interactions with virtual objects in mixed reality, but it's not meant. But it's not meant to work with real object. And this is an aspect we talk about in the second part of the talk, where we'll discuss the problem of understanding hands in action that is dealing with real objects. In tackling these problems, a big advantage of a mixed reality headset like the HoloLens is that it uses multiple input streams, like depth and RGB, and process them to give you higher level signals like hand tracking and eye tracking. So I'd like to discuss with you the importance of leveraging these streams and introduce HoloLens to research mode, which is a library that gives you access to all the raw input streams on device. Okay, so let's start by discussing the journey behind the hand tracker you can currently use on the HoloLens. So let me just, first of all, spend a few words about the device itself. HoloLens was launched last year, and it is an untethered mixed reality device which enables immersive experiences. In these mixed reality experiences, you can interact with virtual holographic objects in 3D in a natural way, thanks to the capabilities offered by the device. Oh, it's a bit weird that it jumps. Like environment understanding, eye gaze tracking, and as we mentioned, hand tracking. The device itself is really self-contained, so all the compute happens on device. So first of all, let's look at the hand tracking running live on the HoloLens. So this is an app which is publicly available on the HoloLens store, and I would invite you to try that out if you have a chance to. It showcases many novel, interesting interaction scenarios made possible by HoloLens. As you can see, the HoloLens hand tracker gives a really instinctual way to interact with virtual objects in mixed reality. So you can grab objects, push buttons, even play the piano as you would do in a real environment. Here you can see another example where we had fun writing in 3D in mixed reality. To ensure a good user experience, the tracker needs to be accurate and run robustly in real time without jitter. So obtaining this, especially on a resource-constrained device like the HoloLens, pose a number of challenges. Just to mention a few. Hands are articulated and can assume a variety of poses. Since we're dealing with a head-mounted device, often large areas of the hands are not visible due to self-occlusions. Also, as mentioned, the experience should be seamless for the user. So we need to guarantee high frame rates and at the same time, low latency. Solving this challenge is important since hand tracking plays a key role in human-computer interaction. It's therefore not surprising that the problem received a lot of interest in the literature. And we have examples from both academia and industry. And not we are just really showing a few examples over an interval of 20 years. So our journey for the HoloLens 2 starts with a paper 2. Namely, it starts with a paper which was presented 4 years ago at SIGGRAPH by some colleagues of mine at Microsoft. Here you see some results. The hand tracker proposed in the paper takes as input depth frames captured with a consumer camera and runs in real time on a desktop machine. And this enables a number of experiences in virtual reality scenarios. From the technical point of view, the tracker adopts a model-based approach. We have a parametric model of the human head, which is represented as a surface in 3D, controlled by a set of pose parameters. Given depth frames as input, we fit this model to data. That is, we look for a set of optimal pose parameters, theta star, that best explain the data. And we do so by minimizing energy function via derivative-based optimization, as you see here on the right. This idea remains at the core of the hand tracker we developed for HoloLens 2. However, going from an academic paper to shipping the technology on the HoloLens 2 was a long journey, which took us longer than 2 years and required a number of technical innovations. First of all, we need to move from a frontal-facing camera, like the one used in the paper, to an egocentric camera. HoloLens 2 comes with a depth camera, highlighted here on the left, based on time-of-flight imaging technology, the same technology used for Azure Kinect. Example frames can be seen here on the bottom right corner. Here we show depth images and active brightness images, basically IR, used by the depth algorithm. As mentioned, we still rely on a model fitting approach. So we take depth as input and fit a parametric hand model to data in each frame. For robustness, in order to recover when tracking is lost, we rely on pose reinitialization. That is, at each frame, we minimize our energy function, starting from multiple different poses. In the plots, the starting points are shown in green and in purple. When we then take, as a result, the pose with the lowest energy, in this case, the purple one. As you might imagine, bringing this architecture to a product, which must be ready to be used by a number of users, implies a number of requirements. So in terms of user experience, we want to keep latency and jitter low while ensuring high frame rates and accuracy. We want the tracker to work robustly across different users in different environments. Finally, we are working on a self-contained head-mounted device. So we really need to take into account all the constraints given by the hardware and work on very limited computational budget. So let's focus for now on the computational efficiency needed to run this hand tracker on a device like the HoloLens. So when we took the tracker implementation from the SIGGRAPH paper and ported the code to make it run on device, we saw that we were something like more than 200 times lower than you. We started at 2 iterations per second. We needed something like 300. The plot here shows how we improved our performance over time. One thing to consider is that on device, the CPU must be free for applications. The tracker needs to run on the holographic processing unit, the HPU, which handles sensor streams. The HPU is located on the frontal part of the device, near the forehead of the user, so it should not get too hot. This means we need to consider both consumption and speed. Reaching the goal of 300 iterations per second while also improving accuracy and robustness require a combination of algorithm innovation and low-level engineering. In this talk, I'm going to discuss two significant examples. One is related to the introduction of a new hand surface model, and the other is related to the use of deep neural networks, DNNs. So at the beginning, for the tracker, we rely on a smooth surface model, a subdivision surface, which is shown here on the left. At fitting time, using this smooth surface ensure faster convergence with fewer data points with respect to a polygon model, like a triangulated mesh, which is shown here on the right. However, this comes at a cost. Evaluating points on a smooth surface model is computationally more expensive, and this was a price we couldn't afford really to pay on the HoloLens. So a key innovation was the introduction of a new model, the so-called phone surface. We described the phone surface model in more detail in a paper, which is going to be presented as an oral here at ECCV. So I would definitely encourage you to check that out if you're interested. Here I'm going to really just describe the main idea of the paper. So the inspiration for the phone surface comes from the phone shading technique, which is used in computer graphics. The idea is to use the polygon surface model, but interpolating the surface normals. So you can compare the different surfaces in this close-up. The phone surface is somehow in the middle between smooth and polygon models. It allows us to keep the benefits of the former in terms of convergence while not paying a high computational cost. Besides this surface model, another important aspect we mentioned is the use of DNN. So as you might already know, HoloLens 2 comes with a dedicated DNN accelerator. And we leverage it to run tiny CNNs, which are trained to detect hands in the scene and estimate hand segmentation and key points. Here you see an example result with hand segmentation and key points mostly corresponding to fingertips. Results are good, but there are two things that remain unclear that we didn't explain here. So first, how do we actually use this estimate? How do they fit into our hand tracker big picture? And second, how did we train this model? So regarding the first question, we can go back to our hand tracker diagram. So here we can add segmentation and key points estimates here within the white circle as additional information and therefore additional constraints for our energy function. So our algorithm takes as input depth data plus DNN estimates. So it becomes a hybrid architecture that combines a bottom-up discriminative approach given by the DNN with a top-down model-based one. Again, the advantage is better convergence when we minimize our function, as shown here by the plot, where the function becomes smoother. Now, let's briefly see how we trained this network. So remember that we want to address a variety of users and environments here. So building the right training set plays a crucial role. So what we found most effective was the work to work with synthetics. Synthetic images bring a number of advantages. We get label data for free, and these labels are clean without annotation noise. They can also be much richer and more dense than what we can expect from human annotators. And finally, one aspect we care about a lot here, we can easily control the variation in the data set. So given this advantage, synthetics have been used quite often in the literature. Here, we picked just really two examples. A problem is that these images don't look quite realistic. So when moving to real images, one has to address the domain gap. Instead, we took a different approach. So what we chose to do was to target realism from the beginning. Here is an example sequence from the training data we generated. On the left, RGB, just for reference here. In the middle, the depth data used as input. And on the right, the ground truth we can obtain. In order to obtain robustness for our networks, we needed to be able to create a lot of variation in a cheap way. For example, we had to find ways to place accessories like rings and watches automatically on hands. We observed in general that without this accessory, the DNN was not able to work in a satisfactory way on this data. Another important aspect is the background. So we try to obtain realistic backgrounds by placing hands automatically inside 3D rooms created by artists. In general, we found this aspect to be important, and it made a difference with respect to other approaches that choose to add random backgrounds. The nice thing here is that we were able to train our DNNs purely on this synthetics data and obtain accurate results when we went to test on real sequences, as you can see here from this example. Okay, so at this point, let me briefly summarize what we've seen so far and perhaps the main lessons learned. So with respect to the original paper, we had to introduce a lot of technical innovation to get a tracker that can get shipped really as a product. In the end, what worked best was a combination of parametric 3D modeling that express something about our knowledge of the world and DNNs. And this is a paradigm which I saw working well often, even during my PhD and postdoc experience. Now looking a bit ahead. So first, we saw that the tracker enables interaction with virtual objects in mixed reality, but what about real objects? And second, we found the use of synthetics very effective, but what if generative synthetics becomes difficult, for example, when we deal with motion sequences? So for answering this question, or at least trying to, let's start looking at hands in action, interacting with real objects. So as we said, the hand tracker is meant to make you manipulate holograms in 3D. So it is supported until a few centimeters from real surfaces. But we are always immersed in a real environment, so we manipulate real objects, and in mixed reality, the real world remains always visible and accessible. So the problem of understanding people in context within their environment is important and is receiving more and more attention. Indeed, there is an increasing number of papers in the literature that look at people interacting with the scene, and more specifically with objects. Here I just picked a few recent examples, but the list would be long. So understanding where the subject wants to go, what they want to do, which object they are dealing with, is extremely important also in mixed reality scenarios. Here is an application available on the HoloLens 2 dynamic guides, whose goal is to support first-time workers when they learn a new task. And this is a very powerful tool since it makes the experience much more straightforward with respect to, for example, reading a manual of instructions. So you can keep your hands free and look at instruction at the right location, so you don't have to constantly, for example, turn your head back and forth. However, currently, creating a so-called guides require lots of manual intervention. For example, you need to create the text, put it in the scene at the right location. And a lot of this could be automated. For example, we could save time if we could just ask an experienced user to perform the task once and create a guide automatically. Or if we could provide feedback, for example, to the user about how they performed an action. Similar consideration can be done also for another application available for HoloLens, which is Remote Assist. Think of it as a richer Skype call where an expert can assist you from remote, see what you see through the HoloLens, and highlight objects in the scene. Especially in this period, where gathering together in a workplace is difficult, this kind of application can have a big impact. So even here, I think many aspects could be automated to improve the user experience. So far, together with my colleagues at Microsoft, I start moving a few steps in this direction. And last year, at CVPR, we presented a work focusing on understanding hand-object interactions from egocentric RGB videos. The goal here is to provide a complete understanding of the scene. Estimate 6 of object pose and 3D hand pose per frame, plus object class and action class over the entire sequence. The approach is based on a fully convolutional neural network architecture, which basically builds on top of YOLO. So in the first stage, we predict hand and object poses in 3D, running this network on each frame independently. In the second stage, we integrate these per frame estimates over the entire sequence. We feed the predictions into a recursive neural network, RNN, which predicts an action for the entire sequence. One of the advantages of this architecture is that it's efficient, since we need only one feed-forward pass through the network. Here is a video with a few results. In general, as you can see, estimates are accurate. However, the method suffers from a number of limitations. First of all, the method is fully supervised. It requires ground truth for hand pose and object pose in 3D. Acquiring this 3D ground truth in these scenarios is challenging. Here, for example, the author used mockup markers, which are visible on the hands. So they are effective in helping acquire ground truth, but end up polluting the RGB images. So the first problem is the requirement for full supervision. Second, we just regress skeleton joint locations for the hands without imposing any prior knowledge we have about the human hand. So in general, it is good to exploit this prior knowledge to reduce the amount of work we require from the DNN. And going beyond skeleton, modeling, for example, the hand surface can also help us reason about, sorry again, I guess there is just this timing in the slides. Going beyond skeleton, modeling, for example, the hand surface can also help us reason about hand-object intersection and contact points. Finally, the method requires us to input a 3D bounding box for the object, so it will not work on unseen objects. We try to address some of these problems in follow-up work, which were presented this year, at CVPR. Here, we reconstruct 3D surface of hands and objects from RGB monocular videos. We try to reduce the amount of supervision required by leveraging photometric constraints over multiple frames. If you look at this image from the top row to the bottom one, you can see that when we use only 1% of the training data, estimates are inaccurate. While when we use 100% of the data, As expected, we obtain an accurate result. However, when we use as little as 1% and add a photometric consistency error term, results improve significantly. You can see here in the comparing the top row with the bottom one. So looking a bit in more detail at this photometric consistency error term. So given a frame, TREF, for which we have ground truth labels, we exploit this to improve the predictions for another unlabeled frame at TREF plus K here. One important aspect is that we're estimating 3D surfaces, not skeleton anymore. So we can compute in a differentiable way the optical flow between the ground truth vertices of hand and object and the estimated ones. Then we can basically generate in a differentiable way the optical flow between ground truth vertices and estimated one. In general, this allows you to get two images, a real one and a generated one, and we can compare them, enforcing consistency in pixel space. The idea here is that since surface at different frames share the same topology, the same surface point should correspond to the same pixel color. Regarding the prediction per frame, which is here in green, we obtain it with an encoder-decoder architecture where we regress shape and pose parameters of a parametric model of the hand and the translation and rotation of the object, for which we assume we have a rough 3D model. Here is a video with a few results. You see that in general, exploiting this sparse supervision, we can reduce the amount of training data required. These are first step towards a better understanding of hand-object interactions. Looking forward, I think there are a few different directions that will allow us to progress here. The ones I found perhaps most exciting are looking for better ways of gathering, annotating, and exploiting data. For example, we have a lot of data we were discussing before, which is available on the web. Can we find ways to leverage it while ensuring privacy? And related to this is the topic of multimodality. For example, I started seeing example where we use, and we discussed again this before, where we use video and audio. So how can we exploit this multimodal stream to build more accurate and robust model? And finally, and this is a topic I discussed already in this talk, I think it's crucial to find ways to combine the power of DNNs with our prior knowledge of the world. This could also help us keep the size of our network small, which is a crucial problem, especially when we work on a head-mounted device. So related to the second point here, I'd like to move now on to the third and final part of the talk and briefly introduce HoloLens 2 research mode. So what is research mode? Why should be interested in it? So for example, you might want to get access not only to the hand tracking results, but also to the raw depth input streams used by our algorithm. For example, here you see my hands in motion as point clouds computed from the HoloLens 2 depth frames. And this raw input stream is now accessible to anybody who wants to build their own computer vision algorithm. So exactly in these days, we are releasing HoloLens 2 research mode, which is a C++ library providing access to all the raw sensor streams on device, including depth, the grayscale cameras used by the head tracking, and IMU. And here is the visualization running live on device of depth plus to grayscale camera stream. We are also releasing code and a set of tools to combine sensor streams with hand tracking, eye gaze tracking, and the HoloLens RGB camera input. These are released in a public GitHub repository, which you can find at this link here. It should be available early next week. We'll talk in more detail about research mode in a tutorial this Friday, so that I would encourage you to attend the tutorial if you're interested in more details. Here, you see an example up. I just wanted really to show you quickly. So we provide a recorder. You launch it from the HoloLens and use these two buttons to start and stop the capture. And here in this app, we will see how to capture hands and eye gaze tracking, depth, and RGB. When the capture is finished, in general, you can then see the location in 3D where the hands were tracked and have a first debug of the scene. By post-processing these streams, we can in general correlate them in time and space. Here, for example, we projected tracked hand joints in green and eye gaze in blue over frames captured with the RGB camera. And one aspect I like to stress is that the current hand tracker does not support hands touching surface, so it could get disabled or give inaccurate results sometimes if you try to do so. So by moving with the HoloLens around the scene, we can reconstruct it in 3D, as we did here, using depth and RGB frames. On the left, you can see a point cloud reconstructed from a single depth frame projected onto an RGB frame. And since all these point clouds can be put in a common coordinate system, thanks to the HoloLens head tracker, we can also merge multiple frames, as we did here on the right. At this point, we can also add the subject who was capturing these frames moving in the scene, which we represent with head and end motion. Here, head is visualized with the 3 coordinate axes, hands in red, and eye gaze with the little blue sphere. So I hope research mods can be in general a useful tool for research in computer vision scenarios. We'd be really happy to receive your contribution and also feedback to improve it. In general, we really welcome contributions, code ideas from the community about this. Okay, so I'm reaching the end of my talk. So I'd like to summarize a few thoughts and then propose a few questions I would be happy to discuss with you. First, to build computer vision algorithm for head-mounted device, we need to pay attention to a lot of details and constraints given by the hardware. We then discuss about the importance of understanding how people interact with their environments. For this, given also my research background, I tend to look a lot in 3D, so at a 3D understanding of the scene. And I think that in general, reasoning in 3D is important, especially for mixed reality applications. And finally, I try to show you that a device like the HoloLens can be used as a powerful tool for computer vision research. A few questions that for me remain open are how important is to have a fine-grained understanding of the scene. For example, we talk about estimating hand pose, object pose. Do we need this if we want to understand what actions people are performing? For instance, thinking of our guide scenarios, we might or might not need to do it if we want to understand only if a user complete an action and if they did it correctly. Related to this, how important is to reason in 3D? Does this help reduce the amount of information the DNNs need to deal with and figure out? Does it help reduce the amount of training data we need? This again could be important, especially in industrial scenarios where customers want to apply the same model to different tasks without collecting huge amounts of data. Finally, given also the variety of streams that head-mounted device give us, how to effectively leverage this multimodality, for example, combining lower level streams, depth, RGB, audio, as we saw before, with higher level ones. For example, in the case of the HoloLens, hands tracking, eye gaze tracking, and head tracking. And the last bullet point indicates I would expect many more questions would raise from this talk in general in this workshop today. So given this, I'd like to thank you for your attention. I'm sorry for the timing slide technical problem, and I would be happy now to discuss with you and take your questions.
Hey, thank you very much for the interesting talk. So I would say we have some questions which are also related to your questions. So maybe we start with those, and then if we see fit, we can turn this into final discussion if this is interesting for all the attendees. So one question we have from Dima is, can you give us more insights on when depth is absolutely necessary and cannot be bridged. And there are also lots of works that can estimate depth from a single camera. So what's your insights on the utility of these works?
Mm-hmm. In general, I think really from my experience on the HoloLens, we couldn't use much the RGB stream, for example, because of well, a part of privacy concern and also power consumption in general. It would be easy, for example, to work with to grayscale cameras, do some stereo, and then reason on top of that. In terms of gain or advantage of using depth plus RGB, for example, for the paper, we presented a CP21 regressing handed like skeleton joints, basically, and objects. We also experiment quite a bit with multiple stream, RGB, and depth without, this is the paper, without really seeing strong gain when we also had depth information with respect to RGB. So in general, I think for our case, some really hardware constraints impose us a choice of some algorithm. For example, it would be difficult to work at some resolution, some frame rate for RGB. But this is, of course, something that can be worked on. I think one thing that I find interesting, more like than this in depth, I'm very curious about how much having 3D, in the sense that, for example, by relying on the HoloLens head tracker, you can have all these options in a common coordinate system. And this is something, a sort of information that is additional with respect to what you have only, for example, from a monocular RGB video. For example, you can see rezone in terms of location. Do the hands are in the same location? Do they move? Is much easier when you have these 3D insights. And this is something I think that in general reduce the amount of information that the DNNs needs to figure out.
Okay, so I think so. The other bit of question was if you think that methods which can estimate depth from a single camera can be useful, but maybe on the case of HoloLens, this would be an extra computational budget. So I don't know if there's a correct answer to the question.
Mm-hmm. Yes, at the moment we rely on a depth camera for HoloLens. I could see, for example, cheaper scenarios where we use a stereo pair, for example.
Okay, so another question is, do you make any distinction between objects that are manipulated by a single hand versus two hands? And do you think we need to model this differently?
This is related to project in particular, or?
I think it's a general question. It's probably related to the part on modeling hands, probably the slide you're showing. I think it's a general question on, do you think we need to make this distinction between single hand versus two hands interaction when we model interactions with objects?
Well, for example, thinking about our hand tracking scenarios, again, you have problem of both computational efficiency, I would say, and accuracy. So when you go to two-hand scenarios, you know that you need more compute power in general, because you have just more degree of freedom to deal with. And this also, I mean, at the moment, for example, the hand tracker for HoloLens supports two hand. But obviously, you need also to take into account all the constraints between hands, let's say touching each other, or so it makes things more complicated, both from a computational and from an accuracy point of view. For example, this project here, understanding Halbech and object interaction. So we had, I think the Bura, who was the first author in the paper, tried also to have networks which regress both hands together. In this case, I think it was a quite straightforward extension. We didn't experiment really a lot in how to maybe exploit constraints between the two hands, which I assume we might do. Again, you have probably some more computational efficiency coming. We in general saw good results, for example, on this data set also, and other most recent data set we also provide ground truth for both hands, just reusing the same idea, so the same CNN-based network we use in this paper.
Mm-hmm. So another related question is if HoloLens can be used to capture multiple people interacting with the same object.
Well, at the moment, it would be a bit problematic. So it assumes, I would say, two hands in the scene. In some cases, it might just ignore, and so for example, the DNS will detect the region of interest and the hand pose. They are trained from an egocentric point of view. So if you have other ends in the scene, but which don't look really like the one from the user, they might be ignored. Mm-hmm. So the hope is that we are robust to that. It's not supported basically to track. Still, if you have two users, both using HoloLens, you can reconstruct two hands of one from one device and the other from the other, and still you can put them in relation because you have the location of the two HoloLens at each time.
So put them in relation means that we can put them in the same coordinate system.
Yeah, let's say you have, I could imagine, let's say you have a QR code or something in the scene. I guess this would be something you could do. This would give you a shared coordinate system for both. I would be not super sure about time synchronization. I would need to think a bit about that. Might not, since you would have to do something in software, not in hardware.
So another maybe more technical question is about research mode. So with HoloLens, with the first edition HoloLens, if I'm not wrong, research mode used to drain the battery. Is this something that happens with HoloLens 2 as well? Like, is the battery life reduced when using research mode?
It might happen, yes.
Okay, because I guess we are capturing a lot more information and streaming it.
Yeah, it requires, if I'm not wrong, we still have, when you enable it, we still have this warning message. That's more battery. Might be, I wouldn't be able now to give you really exact details. But.
I see. And also when you were referring to research modes, you say that 3D point clouds stay on a common coordinate frame. So is this persistent when we turn the device off and on again, or is a new coordinate system initialized every time?
So in general, depending on when you where you launch the app. So let's say you do multiple capture in sequence without, so always within staying in while the app is running, they will be consistent. If you stop the app, so you turn it off and then turn it on again, the coordinate system will be different because it depends in general on the where your head was when you start the app. Again, you can use, for example, I experimented a bit with using this QR code. There is also code now in this samples app where you basically rely on them to have share a common coordinate system across different captures.
I see. Since, I mean, this is something I'm interested in because in our lab we're working on this. Did you experiment with anchors to retrieve, I mean, to have, instead of QR codes, to have a common reference system? Because we did some experiments, but at first it looks like it's not very reliable. Do you have experience on that?
To use what, sorry?
Like the Microsoft HoloLens anchors, because you can place the anchor and retrieve the position of the anchor later. Like,
okay, yes. Are you referring to the cloud-based version, or?
No, I think it's not the cloud-based. I think it's the HoloLens API.
Mm-hmm. Okay. I experimented with an old version in the past. I haven't experimented with the newer version yet. This is actually something we could look into or add as soon as new features. Again, we are releasing everything like this week. There are, I think, still a few missing pieces we want to add. We're thinking about adding audio. We can also try to look into this, for example.
Okay, so if there are not other questions, I believe there are not other questions. Thank you again for your talk, and this concludes the session, and we move on to the papers. So thank you again, Federica.
Thank you.
Okay. So we now move on to the paper session, where we have 4 papers. 2 of them are full papers, and the other 2 are extended abstracts. So we begin with the first accepted paper. Is the speaker in the audience and enabled to talk? So the first paper is data augmentation techniques for the video question answering task.
Hello, can you see me?
Okay, hello.
Okay.
So can you share the screen? Are you enabled to?
Yeah, you should be able to see it now, I think.
Yes, we can. So I'll introduce the paper again very shortly. The paper title is Data Augmentation Techniques for the Video Question Answering Task by Alex Falcon, who he's presenting, Oswald Lanz, and Giuseppe Serra.
Okay, thank you so much. And my name is Alex Falcon, and I'm a PhD student from University of Udine and Fondazione Bruno Kessler in Italy. In this paper, as I said, we present 3 data augmentation techniques for the video question answering task. So first of all, what is video question answering, or simply video QA? Video QA is a task which requires the model to watch a video, read a contents-related question, and provide a coherent and meaningful answer to it. In particular, 2 experimental settings are usually proposed. The first one is called open-ended and consists in selecting the correct answer from a huge list of several hundreds of possible candidate answers. And in particular, as an example, Zhu et al. In reference number 1 proposed to use the top 1,000 most frequent answers from both the training and validation datasets to use as this fixed list. Then we have the multiple choice task, which is slightly different because, as I wrote here, the input also comprises a small pool of candidate answers. And in particular, we have that only one is correct, obviously. And then we have that the pool is different for all the questions. Because if you think about it, let's say we have a question asking to identify an action and another question asking to recognize an object. Obviously, you need to have different pools of candidate answers. Then about the data sets, we have that until last year, all the data sets released for video QA were comprising videos taken from a third-person perspective. In particular, here in the upper part, I've put 2 examples from TGIF QA, which is a data set released in 2017. Last year, during EPIC at ECCV2020, FAN released the EGO-VQA dataset, which focuses, on the other hand, on egocentric videos. And it is the first dataset using egocentric videos for the video QA task. And here in the lower part, I've put 2 examples from it. And as you can see, there are several differences with respect to the third-person videos. For example, you have a lot of motion blur. You have the fact that you have some objects which are covering most of the recording space. And this can be a problem because they could be occluding the target of the question, for example. Moreover, since we are dealing with video QA, it must also be noted that there are some questions which cannot even be answered to. Because, for example, if you have a question which requires the model to identify what the camera wearer is wearing, obviously we can't respond to it because the camera wearer itself never appears in his own videos. Then another part of our work is related to data augmentation techniques. In particular, these techniques are used to artificially increment the size of the training dataset. They are commonly used in several computer vision related fields, for example, because as we know, deep learning models love having a lot of examples to learn from. And in particular, this can be a lot helpful because you have that labeled examples can be hard or costly to get. So obviously data augmentation techniques play a huge role in this. And in particular, in the literature for video QA, we haven't found any ad hoc data augmentation techniques for it. Yet in the visual QA, which deals with static images instead of videos, we have found a few techniques which can be separated in template-based methods and generative methods. In particular, the former ones deal with extracting information from the question, such as objects or relations between the objects. And then using pre-made templates, they create new questions. Then we have generative methods, which on the other hand usually are based on recurrent networks, such as LSTM networks. And they are focusing on creating new questions, word by word, by receiving input the visual features. Yet, as you can imagine, these techniques can also generate questions which are not related to the visual features. And they also can create questions which are, let's say, following a poor grammar and so on. As the authors report in their paper, in particular in reference number 8 by Caffol et al., they also propose a procedure to mitigate these problems, yet they are not completely error-free. On the other hand, we propose 3 simple, really simple, but effective techniques which exploit both textual and visual information. So let's dive into these techniques. The first one is called mirroring, and it is really extremely simple. And it is a purely linguistic technique, and it is based on the idea of keeping the same question, in a sense, keeping the same candidate answers, yet they are proposed to the model in the inverse order. While looking extremely simple, this can deal with situations where there is a strong bias towards a particular position, so a particular ordering position in the candidate answers, in the pool of the candidate answers. Then we have the resampling technique. In this case, the idea is to replace the wrong candidate answers with new candidate answers from the same question type. This means that, first of all, we need to identify what is the question type of the given question. So in this case, for example, we are looking at a question composed of what is the man in green shirt holding. We can say that the question type obviously asks us to identify an object, and it has to identify an object which is dealt with by a different actor than the camera wearer. And in particular, if we gather all the possible answers for this question type from the dataset, we find a huge set of possibilities. And then from it, we can extract 4 new candidate answers to replace the old ones. Then we have the horizontal flip technique. This is heavily based and heavily inspired by horizontal flip, which is commonly used in computer vision related fields. Yet for the video QA task, one must put a lot of care into the questions and the answers. Because if you look at the example on the lower part, you can see that in this frame, we have that the target of the question is on the left with respect to the camera wearer. Yet when we flip the frames of the video, we have that the target of the question is moving to the right, in a sense. So also the question must be updated accordingly in this case, but also eventually also the answers must be updated. As a benchmark dataset for these techniques, we use the EGO-VQA dataset, both because it is the first and only egocentric dataset for video QA, and because of the importance of this task, and also because it is a really small dataset, counting around 600 clips, 600 QA pairs. So it is a perfect target for data augmentation techniques as well. In particular, we are focusing on the multiple choice setting as the dataset, and there are 5 possible candidate answers. On the right here, I've put also a table covering the 8 question types with which we are categorizing the questions in the dataset. So as you can see, we are focusing on questions asking to recognize actions, objects, or person, and to eventually count objects or people, and to identify a color, for example. Moreover, we are also separating the first 3 types into first and third, based on whether they focus on, let's say, on whether the target is the camera wearer or it is a different actor. Then about the results, let's start from the mirroring technique. As we expected from the design of this technique, we can see that it is particularly helpful when there is a bias towards a particular position. So for example, on the right, I've put the distribution of the correct answer position both before and after mirroring. And as you can see, for example, in who first, the third row, you can see there is a strong bias towards the first position. So in this case, the model is likely to simply select the first answer without even looking at the question or the visual data. As you can see also on the right, we have that after mirroring, in some cases we have, let's say, removed almost all the bias, whereas there are also situations in which we created multiple peaks. So there is still a lot of work to do on this technique. Then we have the resampling technique. As you can see on the right, let's start from the bottom. You have that. You can see that the main question types where the resampling technique is helpful is when the target of the question is an object. So whether we are asked to recognize an object or to count how many occurrences of a given object we can see in the video. On the right, we can also see that before resampling, we have less than 10 examples, few examples per object. And after samples, we are creating a lot of examples using the previously mentioned technique. Moreover, there are also, in the original dataset, there are also some objects such as desk and cup and pillows, which only appear once as the correct answer. Moreover, we can see also that the counting questions, we obtain a decent boost. And this is interesting because when we are performing resampling, we do not perform augmentation for this question type because there are only 5 possible candidate answers from ranging from 1 to 5. And so this is likely, this boost we observe is likely related to the improvement we observe in the other question type, which also deals with objects, as we said. And finally, we can observe here the results for the horizontal flip technique. It can be noted that, first of all, on the right, I've put the distribution of the questions containing left and right based on the question type. And you can see that basically only 2 question types have a decent number of examples from containing either left or right. And summing up these two peaks, we can say that around 20 to 30% of the data available for these 2 question types is containing either left or right, so this positional information. And we observe also that using horizontal flip alone technique, we can see that we obtain a boost, so an improvement in these 2 question types. And this is likely related to this, to the availability of more visual data, but also more textual data. We can also observe that we obtain an improvement in the first and the last question type, the action first and coloring. And in this case, you can see on the right that there are almost no examples containing left or right for this question type. So it is not directly related to the availability of more positional information. Yet by flipping the frames, we are still providing more visual data to the model. So it is likely that this helps the model in understanding what is on, whether the object target or whether the action target of the question is on the left or on the right. Finally, here we can also show the results per split, so per data split. In this case, it is a really concise way to show whether we observe improvements or not. We are comparing with the STVQA baseline from the EGO-VQA paper, both because it is the same baseline we used to perform the experiments, and because in its simplicity, it still obtains great results, since the best result reported in the EGO-VQA paper is a 33%. So here we obtained 32 with the baseline, so we are still obtaining a great result. And we can see that using all the three techniques together, we observe a 5.5% improvement in the accuracy. To sum up, we presented 3 simple data augmentation techniques for this task. We showed that the first one, the mirroring technique, is particularly helpful when there is a bias towards a specific position in the candidate's pool. And we showed also that the mirroring technique can help in reducing this bias. Then we showed that the resampling technique provides the model with both more positive and more negative examples, so more data to learn from, and this is particularly helpful when dealing with the questions targeting objects. Then we showed that the horizontal flip technique provides obviously more visual data by flipping, and eventually if there are also questions exploiting positional information, so this left and right contained in the questions text, we can still obtain an improvement as well using the horizontal flip technique. Finally, we showed that we basically exploited the EGO-VQA setting because we think it is really important, thanks to several fields which can use egocentric video QA programs, such as those in industrial settings, for example, when training, in supporting the training of a worker, and also in socially assistive fields related to elderly people being able to watch and ask questions about their life logs, which is shown to be, let's say not a cure, but it can help in reducing effects of dementia and aging-related issues. And yet we also, obviously these techniques can also be generalized to the video QA setting as well. So we are looking forward to it. And thanks for the attention.
Okay, thank you for the talk. We have a few questions from the audience. So the first question is, can resampling introduce problems for ambiguous questions? So for instance, if a person has 2 objects in their hands, if we resample, maybe we could pick the second object and this would be an incorrect answer. Mm-hmm. Does this create problems?
This can create problems because before, let's say that it really depends on how you implement the resampling. Mm-hmm. Obviously, to avoid this problem, which is a serious problem, you should be able to look for all the objects which are in the video and eventually remove them from the candidate answer pool.
Okay, so this should be done by hand or exactly. In an automated way? Okay, I see. And another question is, did you try shuffling the answers as well as mirroring for that augmentation?
No, we haven't tried yet, but in fact, that was what I was referring to previously when I said that using mirroring, sometimes you can remove the bias depending on how the correct answers are distributed before mirroring, but you can also create multiple picks. And in fact, using a shuffling technique or a permutation-based technique, you should be able to deal with this problem in a more fair way, removing all the bias.
Okay. So another question, can you explain again what's the difference between horizontal flipping and mirroring, and also the performance when mirroring is added seems to differ a lot.
Okay, so the difference between the two techniques, you have that in the case of mirroring, as I said, the idea is that we are focusing on a multiple choice task, which I spoke of at the beginning. In this case, we have, for example, 5 candidate answers. The idea is that instead of providing the model with these 5 answers in the pre-established order, we provide them with the inverse order, and this can help in reducing the bias. Whereas in the horizontal flip technique here, the idea is that you can, let's say, easily horizontal flip the frames of the video, but if you do not pose a lot of care about what's contained in the text of the question or of the answers, you may create some problems, because if, for example, in this case, if you flip the videos without updating the questions, in the right part, you would say what is on the desk on the left side, but on the left side of the camera wearer, there is nothing. Well, there is a person, not a desk. So obviously, some care must be put in this.
Sure. Okay. Yeah, if you want to add something.
No, I was thinking about the second part of the question, which I missed.
The second part. Yeah, the second part was referring to the fact that the performance when you apply these two techniques varies a lot. But this is explained by the fact that in one case you are applying a transformation to the input video, in another case not. So they are. Yeah. Okay. So I think that answers the question. Okay. So thank you again for your talk, and we can now move on to the second one. Thanks again.
Thank you.
Okay, so, I see the speaker is ready, so you can already share the screen while I introduce the paper. So the next paper is an investigation of deep visual architectures on pre-process using the retinal transform by Alvaro Samagallo and Jean-Paul Sibert.
Hello, are you seeing my screen?
Yes.
Okay, perfect. So my name is Alvaro, and I will talk to you about the work that I have been developing with the computer vision and autonomous systems at the School of Computing Science at the University of Glasgow. And as you said, it deals with an investigation of deep visual architectures based on pre-process using the retinal transform. So in previous research, this group developed a biologically motivated software retina to pre-process images and generates different images in a cortical space. And this enables some key aspects. The first one is a reduction in image data that can be used for efficient deep learning in, for example, low power mobile applications like smartphones. It enables the processing of 1080p, meaning full HD images through a neural network in a single pass. So this is quite a massive data reduction. Also, it affords partial scale and rotation invariance due to the transformation that is applied to the images. And it can be seen as an attention focusing mechanism for egocentric vision robotics, as you can locate the center of the retina in specific regions. So in this work, we'd like to determine if this retina preprocessor is viable under a practical use case scenario to support robotics and egocentric visual perception. So for this, we had to collect a viable size data set with a viable number of classes. And we recorded some objects in an unconstrained scenario, allowing for variation in object scale, rotation, lighting, and view sphere sampling. The images are from video clips, so we can also use spatial temporal information in training and classification to see whether or not retina can be applied to video as well. Therefore, we want to determine the appropriate network architectures for processing the cortical images and the performance for handheld capture around the object view. Moreover, we will also like to determine if, in fact, there is a certain degree of scale and rotation invariance achieved through the retina pre-processing, and assess the overall system robustness and viability in such a practical use case scenario. So this work, as I've said before, is based on the software retina developed by Siebert and Balasuria, and this retina was then used into fairly constrained scenarios where the images were captured and the retina was focusing on distinct points. Then they were pre-processed and a deep learning pipeline was applied. As we can see on the right side in the table 1, there is a great data reduction that is then causing a reduction also in training time and in prediction time, while the accuracy is maintained at high values. So talking a bit more about the software retina, it is a biologically inspired sampling mechanism for images, and basically what it does, it overlaps Gaussian receptive fields with a self-similar retina tessellation to match the retinas that are observed in nature, biological retinas. This means that this retina has two different regions that transition smoothly from one to another. In the center, we have the fovea, where the receptive fields are very densely packed and the distance is smaller between each receptive field. And this provides high acuity vision for high frequency details. Then we have the peripheral retina, where the packing decreases, and here is where the actual data reduction happens. For this work, we use the 50K node retina that is able to perform almost 17 times of data reduction, and the fovea of this retina corresponds to 10% of the total number of retina samples. The Gaussian receptive fields are then mapped through a log polar function in order to create the image in the cortical space. The image is then split into two hemispheres, which is a result of the log polar mapping, and this is actually where the scale and rotation invariance is achieved, meaning by this transformation. So as I've said before, we had to collect a data set, and for this we opted to record objects on the tabletop, and the objects were recorded with a round motion over the observable view sphere of the object. The camera was handheld with the only constraint of trying to keep the object in the center of the field of view. And we also tried to change the distance to the object as well as the angle, meaning that we have some frames with different scales and rotation. So this resulted in a data set of 20 classes, and for each class we have 6 videos, 2 of them for training with good and low lighting, and then 4 of them for testing, from which 2 are similar to the training set with good and low lighting. One has some rotated views of the object, and the last one has scale changes by changing the distance of recording. The frames are then extracted and pre-processed using the retina and the cortical transformations, and we end up with several sets of data that we can use to compare them. All of these videos were taken using an X-ray camera due to the facility of going around the object. Here we have some examples of the images. As you can see here on the right side, we have the retinal image, In the center, there is more detail than in the periphery. And down and to your left-hand side, we have the cortical image with the two hemispheres. This is the set where we change the distance to the object. And this is where the set that we have the rotated views of each object. So for a classification task, we tried several different architectures as well as several different frame configurations and color spaces. The first one is the immediate approach to image classification. So an architecture with convolutional layers and then fully connected for the classification task. Then we want to really leverage the spatial temporal information that we have by using video frames instead of the still images. So we added some recurrent layers, namely LSTMs, at the end. In the third architecture, we opted for residual layers in order to create a deeper network with better results. And the fourth one, we tried to mix the two changes. So we ended up with using residual convolutional layers with recurrent layers at the end. For the configurations that end with fully connected layers, we tried 4 different frame combinations or configurations. So we tried one grayscale frame, one RGB frame, one color opponency frame, and this is the color space where humans see. So it has 3 channels. One is an intensity channel, another is a blue minus yellow channel, and the other is a red minus green channel. And then we also tried with 3 sequential grayscale frames. For the architectures that end with the LSTM, we tried 2 different configurations, one with 3 sequential frames so that we can compare to the 3 sequential used in the fully connected. And one where we give more information by using 5 sequential frames. So here are the architectures. As you can see here, we have the convolutional layers and then fully connected layers. Then we substitute the fully connected for the LSTM. We then use the residual convolutional layers, and you can see the network goes from 6 layers to 12. And in the last iteration, we use the LSTM with the residual convolutional layers. Talking now about the results. At a first glance, we can see that the color opponency color space was the one that provided the best results. And another thing that I would like to highlight is that the RGB actually was the worst one by far. And this is a pattern that will repeat in the next architecture. So this might show that these architectures are not optimized for RGB, and we can use, for example, 3D dimensional convolutional layers to deal with these images, with these configurations. Also, the test set for the scale variance is actually the hardest task for these architectures. As we can see here, when using also residual layers with the fully connected ending. And once again, the color opponency was the one that gave the best results. Going now to the LSTM, meaning the recurrent architectures, we can see that the configuration that uses more frames achieved better results. However, these results are not better than when using 1 frame with color opponency. We cannot compare this directly, but this is an indication that the network is the color opponency is actually providing some extra information regarding color and texture that is helping the network to classify the objects correctly. Another thing that I would like to highlight is that using 3 frames and the LSTM architectures actually increases the results from using only the fully connected, as you can see here. Going to the last architecture with the residual CNN and the LSTM, the pattern is exactly the same as on the previous slide. And once again, the results are not better than using the 1 frame with color opponency. However, once again, using 5 frames proved to be better than 3 frames, except for the scale tests, where it actually gave the best results overall. So we also tried a few alternative testings where we, in the first one, we trained with an extra class, which is a background class, meaning that there is no object on top of the table. The premise here is that the network would be able to learn what's common between all classes and then use this to leverage the performance. The second alternative test is inverse training. So training on the rotated and scale variance sets and then testing on the normal ones. And the third one is using the fixation crop images, the ones that I've showed before, resized to match the number of pixels in the cortical images, so that we can compare, namely, the rotated and scale scores. So in the first alternative test, we can see that the results are not better than when training without a background class. So actually, the network is not learning what's common for every class and using that to help the classification. In the second alternative test, the results are far worse than using the normal training pipeline. So this means that the network struggles to classify the objects when only seeing them from far or from rotated view. So it actually gives a hint that the network prefers to learn the normal views of the object before dealing with rotation or scaling variation. And the third alternative test, the results for the rotation and scale are worse than when using the cortical images, which can show that there's a certain degree of rotation and scale invariance achieved by the retinal and cortical transformation. So in conclusion, we have demonstrated that the retinal pre-processing is viable under such unconstrained image capture conditions. The performance classification was excellent for a viable number of object classes and a number of images. And this can be, the network training can be accomplished using a practical handheld camera scenario. Furthermore, we were able to establish that both spatial temporal and pure feed-forward nets give excellent results, but the one with the opponent color model yields the best results. And if we consider this an ablation test, we can claim that in fact the retina gives a certain degree of rotation and scale invariance to the classification test. And by separating the color and the intensity channels allows for better classification, since there is added color and texture information to complement the intensity channels. Some future lines of research, I propose that the scale and rotation scores can be improved using other methods, such as Laplacian or Gaussian retina pyramids, or multi-stream networks that deal with the two parts of the retina separately. And implementation of an attention mechanism that can focus the gaze and focus the fovea on distinct points, which can help improve the performance. Experimenting with other color spaces, namely the double opponency, which allows for better texture and color representation, and changing the loss function for the video classification, since it is probably considering the pose change instead of the visual cues of the object. So I'd like to thank my supervisor, Paul Siebert, for guiding me through the whole work, and thank you for your attention.
Thank you for the talk. So we have a couple of questions from the audience. So the first question is, can you quantify the gain in computational efficiency obtained with the retinal transform? Because it looks like this is one of the most important benefits of this transform. And how does, since one benefit is data reduction, how does this compare with respect to just resizing the image and passing a low resolution image?
Okay, so the first question was to quantify the, okay. So some previous results from the work developed by other members of the group show that there is an actual difference in training time as well as in prediction time. And this is achieved by using smaller images and images that are easier to classify. As you can see here, we have more or less 17 times of data reduction, going from 1080p images to 490 to 157 images. So images are quite small. And the advantage of using this transformation instead of passing a lower resolution image is by using the fovea, we can focus, by using the retina, we can focus the fovea on some distinct points. So we can keep the high frequency details of the image while on the periphery there is the data reduction. This means that when you resize the whole image, you're losing high frequency details that can be very important for classification or for robotics test. And by using the retina, you can actually move the retina around the image and then sample with high acuity some distinct points that can be important for the task that you are performing.
I see. I think the question was also about if there is a systematic evaluation, or what are the differences, for instance, in accuracy when you train with just resized images, and or if there is a plan to carry out these investigations.
There was the work that was done before had actually made this comparison, and also here you can see that I've tried to use the fixation crop. The fixation crop are just this images, but without the retinal transformation. So it's a cropped image, and then it was resized to have the same number of pixels as the cortical image. And as you may see here, the results are worse than when using the cortical images. So I hope that answers.
I see. Okay. Thank you. I think we are running out of time. So thank you again for your talk, and let's move to the next one.
Okay.
Thanks again. So the next paper is an extended abstract, and the title of the paper is the speaker in the audience. Yes, there is. So you can share your screen, and the title of the paper is Semantic Visual Navigation by Watching YouTube Videos by Matthew Chung, Arjun Gupta, and Saurabh Gupta.
I see. Thank you. You can see my screen, I'm guessing?
Yes, yes.
Okay. I'll go ahead and get started. Thank you all for having me. I'm here to present this paper that I worked on with Arjun Gupta and Saurabh Gupta at the University of Illinois, Urbana-Champaign, Semantic Visualization by Watching YouTube Videos. I want you to imagine you're looking for a restroom in one of the restaurants pictured here. Even though you don't see a restroom or a sign pointing to one in either of these images, I think you'll agree that going straight ahead in the left image is more likely to lead to a restroom than going straight ahead in the right image. I mean, this is certainly my intuition, and it's mostly based off implicit semantic cues in the scene. In this paper, we seek to learn and leverage these cues for finding everyday objects like beds, chairs, couches, and tables in novel environments. A common approach for learning these sorts of navigation policies employs learning via direct interaction using reinforcement learning. These approaches have a lot of merits, but they often suffer from high sample complexity and the sim to real gap. In this paper, we pursue an alternative approach where we mine for spatial co-occurrences in real estate tour videos from YouTube. This data is passively available on the internet and visually diverse. Furthermore, using real data allows us to avoid the sim to real gap, as we're training already on images from the real world. However, using these sorts of videos presents three unique challenges that don't arise in standard learning from demonstration. Unlike robotic demonstrations, videos on the internet don't come with any action labels. This precludes us from using learning from demonstration or imitation learning. Furthermore, goals and intents depicted in these videos are not known, so we might not know what each trajectory is a demonstration for. Even if we were to label this somehow, the depicted trajectories might not be optimal, which is a critical assumption in learning from demonstration or inverse reinforcement learning. But we tackle these challenges by using an inverse model for action grounding, using an off-the-shelf object detector to label frames, and using Q-learning, which under the right conditions can learn optimal behavior from suboptimal data. So altogether, our approach, value learning from videos, starts with these real estate tours from YouTube. We use an inverse model that has been trained on random actions executed by the robot to pseudo-label image frame pairs with the intervening actions. We next label goal frames using an off-the-shelf object detector trained on the MS COCO dataset. These pseudo-labeled image pairs, along with the reward frames, are used to form Q-learning quadruples. This allows us to use Q-learning to learn a value function that can implicitly capture our desired semantic cues for seeking objects in novel indoor environments. So as a quick reminder, in Q-learning, we seek to find a function which satisfies this equality, the Bellman equation. It states that the maximum reward of any state, which our states are images in our case, is the reward of taking the best action plus the discounted reward of the next state. This is differentiable and readily optimized with standard neural network techniques. So at convergence, our learned value function takes an image and object class and predicts a value, which is a proxy for the nearness to goal of a goal object in the agent's action space. This is to say it predicts a higher value for images oriented towards a goal object and a lower value for images oriented away from a goal object. So we can see this effect by visualizing the value predicted by our network at the same location in different directions. And so that's what we have pictured here. We show the value from predicted by our network for the 5 different classes in each direction in this panorama. So we can see the value for chairs, couches, and tables is the highest in this direction, which sort of looks like it might be pointing towards the kitchen or dining area, which matches our intuition. And the value for beds and toilets is highest towards this hallway area, which might have a bathroom. So to further visualize what we learn in our network, we show the value at different locations, taking the max over all directions. And so the brighter the color here, the higher the value. And we're showing the value predicted for dining tables at a variety of locations. And we've outlined the dining tables in red, and we can see there's high value close to the dining tables, and it smoothly tapers down as the distance from the dining table increases, which again matches our intuition. So given that we have this value function learned, we still need to use it to perform the actual navigation. So to do this, we use a hierarchical navigation policy. It consists of a high-level policy, which decides where to go next and emits a short-term goal, and a low-level policy, which execute actions to achieve these short-term goals. The high-level policy builds a topological map that stores values predicted by our value function at different locations in different directions, and samples the most promising direction and passes a delta pose to the low-level policy. The low-level policy incrementally builds an occupancy map from a depth camera and uses the fast marching method for path planning to get which actions to execute. Eventually, the low-level policy either achieves the short-term goal or fails to reach the goal and returns control back to the high-level policy. So for our experiments, we collected a data set of these house tours from YouTube, and we test in the AI habitat simulator using the Gibson environments. We use a discrete action space for our robot, and we test the 5 classes of finding beds, chairs, couches, tables, and toilets. We use SPL and success rate as metrics. So to briefly talk about the data set, here's an example video of the kind of videos that we've found in our data set. You can see it's of a real house and contains a decent amount of visual diversity. Here's some more examples from the data set. In total, it contains 1,387 videos for a total of 119 hours of real estate tours like the ones you see here. Most of them are one continuous shot, which show the sort of object co-occurrence that we hope to see. So using this data set, we trained with a protocol I described earlier, and here are the results. So we evaluate in two settings. One we call Oracle stop, where the episode ends automatically when it reaches a goal object. And the other is policy stop, where the agent has to emit a stop action to declare that it's reached the goal object. So our method attains an SPL of 0.5, which is better than strong exploration baselines, a variety of RL baselines, even when the reinforcement learning is given access to many more environments, and it outperforms behavior cloning on the same YouTube dataset. So here we show the performance of the various methods with the initial distance to the nearest goal object on the x-axis and the SPL on the y-axis. What I want to highlight here is that our method excels in difficult episodes where the goal is likely not to be visible initially, and the agent has to make decisions about where to go using the learned implicit semantic cues. To analyze some of the design choices, we perform oblations with ground truth substituted in for some of our modules. Here we show the difficulty split out into three categories: 1.5 to 3 meters, 3 to 5 meters, and 5 to 15 meters. So the base setting we find is competitive with models trained with the ground truth actions, detections, and rewards. And there's a significant increase in performance when you use optimal trajectories and incorporate the score from a detector and train on 360-degree videos. What I want to point out here is that, sort of in line with our intuition, using the detector is most beneficial for easy episodes where the goal object is likely to be in sight initially and you just have to detect it and go straight towards it. While using 360-degree videos is most beneficial for hard episodes where you'll need to use more context from your environment to decide where to go when you can't see the actual goal object. So to visualize our performance, I have some example trajectories. We're going to show the RGB camera input in the top left, the depth input, the most recent set of images used to decide where to go from the high-level policy here at the bottom, along with the scores output by the value network, and a map in the top right, which shows the current agent position in black, the next short-term goal in red, the potential short-term goals in blue, and the goal objects outlined in red. And I just want to reiterate that the locations of these goal objects is not known. It's outlined in red purely for visualization purposes. And so here's an example where the agent is seeking beds. I want to stop at this point and highlight that here it's sort of at a hallway decision point. It could go down this hallway or it could go sort of into the kitchen area. And we see the highest value is in the direction of the hallway where it's likely for there to be a bedroom, even though there's no bed visible. And eventually the agent chooses to take this path and goes down the hallway and finds the goal. Here's another example where the agent is seeking toilets. Again, it gets to a decision point, and even though there is no toilet visible, it finds that the highest value is towards this doorway that might have a toilet behind it, and it goes in that direction and finds the goal. Here's an example where it's seeking beds again. So it erroneously goes into this study area, and this highlights the fact that we're using a topological map. It's able to backtrack efficiently and eventually find the goal. Here are some failure cases. So our method performed most poorly in very large environments and also in environments where there are artifacts of simulation. All right, so to summarize, we presented a technique to enable learning of semantic cues for finding objects in novel environments from in the wild YouTube videos. A proposed technique employs cue learning on pseudo-labeled transition quadruples. This allows us to learn effective semantic cues even in the absence of action grounding and goal-oriented optimal behavior. When coupled with a hierarchical navigation policy, these cues convey the agent to desired objects more efficiently than competitive exploration baselines and RL methods with a fraction of the interaction cost. So our code, data, and models will be made available online. Thank you, and I'll take any questions.
Okay, so thank you for the talk. We have time for a couple of questions. So the first question is, since labeling is based on the COCO on a detector trained on COCO, how does the accuracy of the object detector affects the method performance?
So if the object detect, so yeah, the question is how much does the quality of the detection matter? And so in our ablations, so we didn't test what would happen if the detection were like worse than sort of an off-the-shelf detector. So here we highlight that we so we perform within 1 point of true rewards. So here true rewards is with the ground truth annotations from the simulator. We perform 1 point better, but true detections uses the semantic masks that come out of the simulator, and using an MS COCO detector performs on par with that. So I guess the lesson here is the current detection is good enough for the tests that we had. Again, yeah, performance might benefit from improvements in detection eventually, but we're already doing pretty well.
Okay, thank you. And another question is, since you train on these real panoramas, real, let's say, virtual tour, and of real images, and then you test in simulation, do you have the inverse virtual to real problem? Do you lose some accuracy with that?
Yes, we suspect that we do, although it's slightly hard to confirm unless we can compare our performance on, either on a real robot or a simulator that has higher visual fidelity, which is sort of future work that we're actively pursuing to either do this in the real world or on sort of a higher fidelity simulator. It's a good point, and maybe we're looking into it.
Okay, so thank you again for your talk and your answers, and we can now move to the last talk of the session.
Okay, thank you.
Thank you again. Okay. So the next speaker can share the screen. Okay. So the title of the last paper of the session is Spatiotemporal Action Detection with Multi-Object Interaction. Okay.
Hi, can I start?
Yes, sure.
Can you see my screen?
Yes, we can see your screen.
Okay. I'm Huizhen Xu. I'm currently a postdoc at UC Berkeley. So I'm going to introduce our work about spatial temporal action detection with multi-object interaction. So first, spatial temporal action detection task that requires to localize action both spatially and temporally in the form of action tube. So if we check existing dataset and existing models, you will find in current dataset, the action tube usually contains a single person performing the action. So the interactive objects is almost occluded by the person subject. So in this work, we take the action definition of interaction between multiple objects. So we started the spatial temporal action detection work with general multi-object interaction without relying on the off-the-shelf person or object detector. So another problem with existing model is they usually take the person and the tracking pipeline for localization, which means that their localization relies on one off-the-shelf person or object detector. So in this work, we try to build our models without relying on the off-the-shelf person or object detector. So we list our contributions as follows. The first, we introduced a new dataset, which is annotated with action tubes containing multi-object interactions. So instead of taking the human as subject, we take the video source from something dataset, which use hand as subject. So this alleviates the subject and object occlusion problem to a certain extent. And our dataset contains 47 classes with 300 videos each, which is in a large scale. And we also propose an end-to-end spatial temporal action detection model, which performs spatial and temporal regression simultaneously without relying on off-the-shelf person or object detector. So here are two example videos from our dataset. So you can see the annotated action tube containing multi-object interactions. So each bounding box contains the subject hand and interact object, and these both the subject and objects, they are not totally occluded with each other. So and another important characteristic for this dataset is since in the original something dataset, it contains a diverse set of objects. So this means that the object distribution is in a long tail fashion. So you cannot rely on off-the-shelf object detector to detect all the objects exhaustively. So in this work, we propose a model called end-to-end spatial temporal action detection model, called the spatial temporal regression model. So first, we didn't rely on off-the-shelf object detectors. So we do spatial regression on the fly during the training time, based on your bounding box definition. Here, our bounding box containing multi-object interactions, which are not occluded with each other. A second thing is in current spatial temporal action detection model, they take various temporal solutions to improve the temporal localization. So for example, they add the optimization during the final linking process, which is very time consuming. But actually directly temporal coordinate regression already shows a good performance in existing temporal action detection model. So in this work, we try to directly incorporate the temporal coordinate regression during training time into a spatial temporal action detection model. And our preliminary results shows that it gives a very good performance. So I will briefly go through the whole model. So first, given input video, it will first extract the 3D convolutional features to get this video feature encoding. Then on top of it, it will go to the spatial proposal subnet and temporal proposal subnet. So in the spatial proposal subnet, in each feature map, it will conduct a spatial regression independently. And in the temporal proposal subnet, it will conduct temporal regression to detect the candidate activity segment. Then during during training time, the activity classification, both currently these two branches is just for regression purpose. The final activity classification is achieved in the temporal branch, which means that the activity classification is based on the features within the temporal segment, which is actually whole scene features. So this shows to work quite well in our experiment. Then during test time, I show the process in red. So during test time, it will just first take a predicted temporal segment, then connect the bounding box within the predicted temporal segment to construct an action tube. Yeah, that's the whole process. So we report results of our proposed model on our proposed dataset with multi-object interaction. So we take the existing spatial temporal action detection evaluation metric, video MIP, frame MIP, and temporal MIP at various thresholds. So we got two baseline results shown in this table. So the first result is starting from the spot one pre-trained C3D classification weights. And the second model is start from another classification. It's still the same classification backbone, but that backbone is fine-tuned on the something classification dataset, which means that it has a better classification accuracy. So compare these two results. If we start from a fine-tuned backbone with better classification accuracy, the whole spatial temporal action detection performance, either in a video MIP, frame MIP, or temporal MIP, it increases consistently. So this means that during our end-to-end training, our model can potentially benefit from a better classification backbone. So we also experiment on the standard spatial temporal action detection benchmark, UCF1124. So the results are shown in this table. We also report the video MIP, frame MIP, and compare with some most recent spatial temporal action detection models. Our model actually got a very competitive results, 53. So one thing is that our model actually work on only IGB input without the flow input. And we also didn't rely on some external off-the-shelf person or object detector. So our spatial regression is got during our training time from the spatial regression branch. So finally, I will show some demo videos for our prediction. So this is two videos for our prediction from our proposed dataset. So the yellow one is our prediction. The green one is ground truth. This is two prediction videos from UCF1124 dataset. I think that's all for my talk. Any questions?
Yeah, thank you for your talk. So let's get to questions. So there's a question on spatial regression. So you mentioned that you are regressing the spatial temporal coordinates of the box directly. But so at least for object detection, there is past literature that shows that using anchors can allow to obtain better results. Did you try that approach?
So our spatial regression branch is actually region proposal subnet. Okay. So it uses anchors. Okay. But the point is that now because we define action as multi-object interaction. So if you see the example videos, you will see the bounding box actually contains the subject and multiple interactive objects without occlusion. So the goal for our spatial regression branch is try to capture these multi-object interaction areas, which are related to our spatial for our action detection. Instead of like the object detection, you try to focus on the object-centric anchor, object-centric spatial regression with respect to anchor. Now we are doing the spatial regression, try to capture the interactive spatial area related to the action.
Okay, thank you. So another question is, so there are some samples that you show have this uniform background. I believe they come from something, but so there is this uniform background. Do you think that can be a bias? Because I think like baseline subtracting the background and trying to obtain foreground region might, obtain something, while instead the same does not apply to the more complex videos where you actually have a background. So do you think this data can introduce a bias for training?
Yeah, so our preliminary experiments is conduct on this two data set, the UCF101 and our data set. So yeah, something is more static background. So, but UCF101 actually for some of the videos, the background is not static.
Yeah.
So I think it's true that if you change to be some videos with background which are not static, the situation might become more difficult. So, but I think since some of the videos on UCF1124, their background are actually not static, so it still can work in such kind of data set.
Yeah. Okay. Okay. Thank you for your talk, and thank you for your answers. And this concludes the session. And we now have. Okay, so we now have the lunch break, and we're gonna get back at 2:15 p.m. Okay, thank you again.
Okay, we are going to start in 3 minutes. I see the first speaker and the last speaker of this session are here, and Mr. Chang is here already. Yeah, it's muted, but is here. Couple of minutes more, and then we will start. I think we can start, and welcome to this afternoon session of the EPIC workshop. This afternoon we have 6 invited talks divided in 2 sessions, and these invited papers are works accepted already to the main ECCP conference, but are strongly related to the EPIC workshop, and so we are going to discuss those work here. After those invited papers, there will be 2 keynotes. One will be given by Richard Newcomb, and the second one will be given by Jitendra Malik, which will close our workshop. So let's start with the first talk of this afternoon session, which is Object and Action Aware Model for Visual Language Navigation. Mr. He, can you share the screen?
Okay. Yeah. And can you hear me?
Yeah. If you have any questions, guys, please put on the chat, and we will discuss later.
Okay. Can you see my screen?
Yes.
Okay. Hello, everyone. I'm Yuan Kaiqi. Today, I will introduce our latest work on the visual language navigation. First, let's have a look at the VLN task. As shown by the animation, in a photorealistic simulator, a robot agent is initialized at a random location, then given a natural language instruction as shown below at the bottom. The agent is required to navigate to the target room by following the instruction. Okay, to make the task focus on following instructions, the navigation is simplified to select the next step from a set of navigable locations according to a connection graph as shown by the left image. Please note that at each step, the agent can only access one hop navigable locations from its current location, as visualized by the right image, instead of the whole navigable graph. Okay, Let's have a brief review of existing VRA methods. Current approaches follow a scheme of encoder-decoder architecture. Encoder is used to encode words into embeddings. Decoder takes the embedding as input, as well as the visual perceptions to estimate where the agent is and which part of the instruction should be used for navigation and predict the next action. VRA methods mainly differ in the decoder part. For example, even drop proposes a data augmentation via dropping visual perception features to mimic random objects removal, so as to improve the decoder's generalization ability. Self-monitor proposes a progress monitor to ensure the grounded instruction correctly reflects the navigation progress. And the fast model proposes to make a compromise between the graded search and beam search to balance the search efficiency against accuracy. Okay, different from existing methods, we propose to decompose the instructions. We notice that instructions are consisted of object descriptions and action specifications, such as here, the exist, stop, go up are action specifications, and the doors, stairs, TVs are the object descriptions. Object description should be matched to visual perceptions of a navigable candidate. For example, here the first doorway should be matched to the visual perception number 5. By contrast, action description should be matched to the orientation of a candidate. The orientation is the rotation angle from the front direction to the candidate viewpoint. To this end, we propose the object and action aware model. It contains 3 modules: an object aware module, an action aware module, and a combination module. The object aware module learns to attend on object chunks and predict action using visual perceptions as the input. By contrast, the action aware module learns to attend on the action chunks and predict action using candidate's orientation as the input. As the relation between the actions and the objects is complicated. For example, sometimes the navigation can be determined totally by the action chunks, such as turn left, turn right. But sometimes the action happens depending on a landmark, such as turn right at the round table. So here we use a combination module to learn how to combine predictions from the 2 modules. Here are the main architecture of these modules. It looks very simple. One side issue caused by the above solution is that an object might be observed in multiple candidates. Thus, the model might not select the one on the shortest path. To address this problem, we designed a new path loss as shown by the figure B. The loss is calculated as the distance to the nearest viewpoint on the ground truth path. So if the model selects the correct viewpoint, the distance will be 0. Otherwise, the loss will penalize the model. Okay, that's our method part. We conduct experiments on the room-to-room and the room-for-room datasets. Both of them have training set, validation set, validation sync set, and unsync set. And the room-to-room dataset has a test set, but the room-for-room dataset does not have the test set. Okay, there are 4 metrics for the room-for-room dataset: success rate, Oracle success rate, trajectory length, and the success rate weighted by path length. Here, success means the distance between the stop location and the goal location is less than 3 meters. The oracle success means that any past location is within 3 meters to the target location. Here, the unseen means that the visual perceptions has not appeared in the training set. Okay, the last two metrics are for the room-for-room data set. They are used to estimate how well the agent follows an instruction. Here are the ablation started results. We use even drop as our baseline. As we can see here, the proposed object and action aware module achieves better performance than the baseline in both seen and unseen environments. The proposed nearest point loss improves the baseline on the seen set. The full model achieves about 3 improvements according to the SPL on the unseen split. We also evaluated the effectiveness of each module. We found that cutting off each module leads to significant performance drop, and the performance drops more often without the action-aware module. This indicates action-aware module contributes more. Here we compare our module with several state-of-the-art methods, and the table shows our model achieves the best performance. On the room-for-room dataset, our model also achieves the best results under the unseen split. In conclusion, we propose an object and aware module for the vision and language navigation. We also propose a nearest point loss. And finally, our model performs the best on the 2 datasets. Thanks for your time. That's all.
Thank you for the talk. We have 10 minutes of time for questions at the end of this session. So we can go ahead with the next invited talk with titled Procedure Planning in Instructional Videos. It's Mr. Chang. Okay.
Can you guys hear me?
Yeah, we can see your screen and we can hear you.
Okay, cool.
Great.
Yeah, hello everyone. Thanks for having me over. I'm Chenny, a PhD student at Stanford Vision Learning Lab. Today, I will talk about our ECCV paper, Procedure Planning in Instructional Video by Chen Yunchang, Dan Huang, Dan Feixu, Esang Adley, Li Feifei, and Juan Carlos Neves. So let's think about the process of making a mushroom omelet. Here's an instructional video depicting such process where the operator starts with a bowl of raw eggs. Then she uses a fork to whisk the eggs into mixture and then pour the mixture into a pan. And then add some mushrooms into the pan. And finally, she uses a spatula to cook the mixtures into a mushroom omelet. So in this example video, we see that the operator performs a sequence of actions that leads to a desired goal. Inspired by this process, we study a problem. We call it procedural planning. So in procedural planning, given the current observation, OT, the video on the left, and the goal observation OG, the one on the right. Our goal is to output a sequence of actions that brings the underlying state of OT to that of OG. So here we abstract the actions away from the actors, which means that we view the actions as transformations between the states. For example, the action whisk eggs is the transition from the preconditioned state of a row of raw eggs to the effect state of egg mixtures. And furthermore, we show how to extend the walkthrough planning problem first proposed in the paper of Kurutag et al. And like we show how to extend this problem to the domain of instructional videos. That means that at inference time, the model retrieves a walkthrough sequence of intermediate observations or steps that takes the start of the observations to the goal. The key technical challenge of this proposed procedural planning problem is how to learn structured and plannable state and action spaces directly from these unstructured real videos. Since instructional videos are visually complex and the tasks are often described at high levels of abstractions, one can imagine indefinitely growing semantic space and action spaces from these visually complex scenes and high-level descriptions. So this all prevents the direct applications of classical symbolic planning approaches, because these approaches usually require a given set of predicates for very well-defined state space. So in this paper, we present Dual Dynamics Network, or DDN. This is a framework that learns plannable representations from instructional videos for both procedural planning and walkthrough planning. DDN addressed this aforementioned technical challenge by explicitly leveraging the conjugate relationships between the states and the actions to in order to impose this structural priors on the learned latent representations. Our key insight here is that in addition to modeling the action as the transformation between states, as we discussed in previous slide, we can also treat the state as a precondition for the next available action. Because in instructional video and these meaningful tasks, the state usually contains the history of previous actions. So following this intuition, the DDN consists of two modules: a forward dynamics model that captures the transitional probabilities between the states, and then a conjugate dynamic model that utilizes the conjugate constraints for better optimization. We jointly train these two dynamic models using real-world instructional videos as expert demonstrations. So, and at inference time, our full model rolls out by sampling the actions from the conjugate dynamics model P, and then the next state from the forward dynamics model T. The conjugate dynamic model essentially captures the applicable actions and improves planning performance. In the experiments, we evaluate our approach by comparing it with a wide range of baselines and ablations. For procedural planning, there are 5 baselines. They are for example, we have this random policy that serves as an empirical lower bound of performance. And we also have this retrieval-based baseline that essentially finds the nearest neighbor of the star and goal observation pair in the training data and directly output the associated ground truth plan. We also have this WLTDO, a recurrent model for egocentric planning tasks. And we have UAAA in an RNN, HNN, and autoregressive hybrid model that predicts the future action labels directly from the observed frames. And finally, we have this UPN universal planning networks, which assumes a continuous and differentiable action space in order to enable this gradient-based planning. We implement the UPN and adapt it to output discretized actions by adding a softmax layer. We also compare our model to our full model to two ablations, where our model is trained with only this forward dynamics model or with only the conjugate dynamics model. As shown in this table, our full approach significantly outperforms baselines across all metrics. So we further conduct experiments for walkthrough planning. So here, the causal infogram baseline learns plannable representations and by maximizing the mutual information between the representation and the visual observation. It is designed to perform walkthrough planning using minimal supervision, and by maximizing the mutual information within adversarial loss, causal info GAN is able to learn reasonable models beyond this like random policy without using action supervision. However, the complexity of this instructional video require explicit modeling of the forward dynamics conditioned on the semantic action space. So as shown in the table, our full model is able to like learn for this like procedural planning problem can be successfully transferred to walkthrough planning, and also significantly outperforms all of these baselines on all metrics. And here we show a qualitative result. So consider a sequence of 9 snapshot observations in a testing video of making French toast. The observations 03 and observation 07 are separated by 4 actions in the ground truth plan. Our model successfully plans a sequence of 4 actions that brings the 03 to 07. We further test our model's robustness. So while fixing the start observation at 03, we changed the goal observation to 09, and that our model to plan 4 actions from 03 to 09. In this case, the start and the goal are actually separated by 6 actions in the expert trajectory. So while the model has never seen such data during training, it successfully plans the 4 essential actions by merging the repeated actions and further adding the pivotal actions of like flipping the bread and plating. Similarly, we test our model's robustness to different like star observations. So now while fixing the goal at 07, we change the star observation to 01, and that our model plan 4 actions that brings the underlying state of 01 to 09. Our model again is able to output a reasonable plan to achieve the same goal even when conditioned on different star observations. Yeah, thank you.
Thank you very much. Very nice talk. And the last talk is given by Miao and forecasting human-object interaction, joint prediction of motor attention and actions in first-person video.
Can you see my screen or hear me fine?
Yeah, it's fine.
So, hi everyone, I'm Miao Liu from Georgia Tech. Today I'm going to present forecasting human-object interaction in first-person video. This is a joint work of Georgia Tech, University of Wisconsin-Madison, and ETH Zurich. Human has this innate ability of looking into the near future. Consider the example in this slide. By looking at the video shortly before the action begins, we can easily predict the future interaction. Let's take the canister. So in this work, we seek to address this challenging task of action anticipation. Let's take a closer look at the same example. Not only can we predict the future interaction label, but we can also vividly imagine how hands approaches to the object. So this intentional body movement is often referred as motor attention. And in first-person context, motor attention can be represented as future hand trajectory. In fact, motor attention reveals very important information of future interaction region, and of course, the future interaction class. So in this work, we seek to design a joint model that uses motor attention for forecasting human-object interaction. So our joint model takes multiple RGB frames as input and output action labels, motor attention, and interaction hotspots. The motor attention is used to selectively aggregate spatial temporal features for interaction hotspots estimation. And then both motor attention and interaction hotspots are used for action anticipation. Therefore, we have the following conditional probability. So this joint model seems intuitive at the first glance, but the problem is future anticipation is fundamentally ambiguous, which means the future observation only represents one of the many possibilities characterized by an underlying distribution. In the following slide, I'm going to show how we address this stochastic patterns of future representation. We proposed a stochastic units with sampling mechanism to account for the uncertainty of future representation. So for motor attention, we used a linear mapping function followed by a softmax function for attention generation. And then we sample from the attention distribution and used sampled motor attention as a feature indicator for interaction hotspot estimation and action anticipation. During training, we assume the prior distribution of motor attention is given a supervisory signal. Note that this prior distribution is derived from additional annotation. We then adopted this Gamble softmax trick to make the sampling process differentiable. For the interaction hotspots module, we also adopted the same stochastic units. So therefore, we have the following full model. We adopt a 3D convolutional network as the backbone. Then the motor attention module takes a network feature from the second convolutional block as input. And then we use the aforementioned stochastic units to generate sampled motor attention. Then this sampled attention is used to guide the interaction hotspots estimation. A similar stochastic unit then generates sampled interaction hotspots. Finally, for sampled motor attention and sampled interaction hotspots are used to selectively aggregate visual features for action anticipation. We now present the training and inference schema of our joint model. During training, we assume the prior distribution of motor attention and interaction hotspots are given a supervisory signal. Our model therefore optimizes this latent variable model by maximizing the shown evidence lower bound. The corresponding training loss has 3 terms. The first term is the classification loss, and the 2 KR divergence term match motor attention and interaction hotspots to corresponding prior distribution. During training, we actually draw multiple samples of the same input at different iterations. So theoretically, we should also draw many samples of the same input and take average at inference time. But the sampling process is very computationally expensive. Instead, we choose to directly plug in the deterministic attention. We notice that the prediction function is composed of a linear function and a softmax function, and therefore is convex. So by Jason inequality, this approximation does provide a valid lower bound of the sampling. Now let's take a look at the qualitative results of our method. As we can see from the successful cases, the motor attention almost always attends to the foreground objects and the corresponding interaction region. Our model also yields to certain limitations. Take the failure cases for example. The model is likely to fail when the future object is not visible or partially occluded by other foreground objects. So here are our action anticipation results on the application dataset. The results are reported as top 1 accuracy. Our model performs on par with previous best method RU-LSTM on syndication side. Note that RU-LSTM use optical flow and object features as 2 additional modalities. So when fusing with the same object stream as in RU-LSTM, the resulting model achieves state-of-the-art results on syndication side. On unsyndication side, our model alone outperforms RU-LSTM by a notable margin. Fusing with the object stream can further improve the performance. To validate our model design, we conduct detailed ablation studies on both Georgia Tech Gaze Plus dataset and the Epic Kitchen dataset. As we can see from the results in the slide, our model outperforms the baseline S3D model by a significant margin. And the motor attention plays a more important role than interaction hotspots in terms of the performance gain. Another important take-home here is that joint modeling in a deterministic fashion can only marginally improve the model performance. This supports our claims on the proposed stochastic units can effectively account for the uncertainty of future representation like motor attention and future interaction hotspots. Going beyond action anticipation, our proposed approach provides additional results on interaction hotspots estimation. Here we report an F1 score on a downsampled heat map. Our method outperforms previous works on interaction hotspots estimation by a significant margin. This result suggests that our proposed approach is effective for localizing future interaction region. Our model also provides strong results on motor attention prediction. Here we report the average displacement error as all previous works on trajectory prediction. Note that all baseline methods require the exact coordinate of the hand for propagating the future hand trajectory. In contrast, our method does not need the hand coordinate for inference, and therefore our hand can imagine the possible hand trajectories even when the hands are not observed in previous frames. And therefore, even so, our model works on par with the best baseline method, LSTM. So in summary, we present the first probabilistic deep model that uses motor attention for forecasting human-object interaction. Our result, we achieved strong results on 2 egocentric video datasets. See more details in our paper, and thank you for listening.
Thank you for it all. And we can start. There is 10 minutes. We have 10 minutes for questions. If you have questions, you can put it in the question answer chat. I have a question for this last talk. Do you have combined the gaze attention with motor attention, and do you see if there are those information are complementary, or one is better than another?
So I didn't try to combine the gaze with motor attention and interaction hotspots, but we do have this additional result on using gaze as a silencing map for feature indicator. It's not as effective as motor attention, but it's roughly the same performance as the interaction hotspots. And in previous work, there are actually a study showing that the gaze and interaction hotspots are actually correlated.
Are correlated, yeah. Thank you very much. I have another question for the second talk, procedure planning. Did you think that changing the context, your method is robust for instructional videos? For instance, in industry context, or are you trying to test in other contexts?
Yes, so for the scope of this paper, we do not have, so all of the videos are taken directly from this instructional video data set. It's called cross-text. I'm not sure if you are aware. Yeah, so it's a data set curated by InReal. And we do have the ongoing works that's kind of like an extension of this work with everything in this like simulation environment. So yes, the short answer is yes.
Okay, and the number of instructions are variable, is not all the same from the beginning to the end, or the number of instruction is fixed?
Yes, we have over 100 like shared actions that is shared across like 18 different tasks. So it's not fixed. It's not like there's any like fixed grammar for given tasks.
Okay, thank you very much. And for the first talk, I have a questions about the noisy in the actuator. Are you using simulator, and is the method robust to actuator noise, or do you think this is something that is interesting to study, the noise you can have in actuating navigation, during navigation?
Sorry, do you mean the noise? Noise in the simulation?
Yeah, when you in the real world, and when you have to move a robot, you will have for sure some noise in performing performing the action, right? So you say your robot move 10 centimeters, but he goes 11. So do you think this problem is to take into account in your work, and do you have ideas on how to work on it?
Oh, got it. Actually, the current work is not that hard. This is a simplified simulator for the than the real world application. For example, there's no such noise in the simulator because even with such a simulator without noise, currently the success rate, the navigation success rate is only about 60% without noise. If it has noise like in the real world, the success rate will further lower. So I think currently we focus on the research on clean environment. And there's a direction for this study is that you see that in the simulator, the where the robot can go is on the navigation graph. He cannot go anywhere. He is limited. Where he can go is limited. There is a new direction is that they turn the created navigation graph into continuous graph. So like the real robot in the real world, but still there are not so much noise. Just so they can go anywhere. Yeah, I think.
Okay, thank you. Are there other questions? If not, so thank you all the speakers, and we have a little bit of break, and we will be back at 3:10. See you later.
Hi, everyone. So we'll get started in about a minute or two. All right, well, welcome to the, I guess, second afternoon session. I'm David Crandall from Indiana University, and I'm pleased to chair this session. And our first talk is called How Can I See My Future well, you'll tell us how to pronounce it, using first-person view for pedestrian trajectory prediction. And our speaker is Hui Kun Bi.
Yeah. So
Slide looks good.
can I say slides? Can you hear me?
Yep, we can. So go ahead and get started.
Okay. Thank you for introduction. Hello, everyone. Okay. Can you see? Okay.
Yep, everything's good.
Okay. Hello, everyone. My name is Hui Kun Bi, and I am an assistant professor at the Institute of Computing Technology, Chinese Academy of Sciences. Now I will briefly introduce our work using first-person view for pedestrian trajectory prediction. State-of-the-art methods used either real-time top-down view images or real-time first-person view images to predict pedestrian trajectories for robotic navigation, autonomous driving, etc. Many prior works chose to use top-down view images due to it is easy to access. For example, they can be captured by surveillance cameras and shared between pedestrians. However, due to the pixel precision, it provides limited dynamic sense context. The latest studies use the first-person view images that can provide detailed dynamic sense context like eagle motion to predict pedestrian trajectories. For applications like robotic navigation, where each robot equips an onboard camera, first-person view images are easy to access. For other scenarios, it might require to install at least a camera per pedestrian, which motivates us to create an in-house simulator to overcome these limitations. For the first time in trajectory prediction task, we propose to use simulated first-person view images to introduce detailed dynamic sense contexts like eagle motions, which requires no physical equipment. Therefore, our study can be applied to any application without additional cost. We named our in-house built first-person view simulator as Fusion. Given the observed ground level 2D trajectory for each pedestrian, Fusion uses Unity to generate a dynamic virtual environment with the camera settings that are shown in the upper right figure and renders the corresponding first-person view images for each pedestrian. This video shows the first-person view images for each of the 4 path streams based on their own observed trajectories. Using the simulated first-person view images and observed 2D trajectories as input, we proposed our deep learning model named Future to predict future 2D trajectories. As shown in the Future's pipeline, there are 5 major modules, including 2 encoders, one for observed path streams trajectories, and the other for first-person view images, followed by the 2 modules, social aware attention module and the view aware attention module, and finally connected to the trajectory decoder. We use the multi-head attention mechanisms for both social aware attention module and view aware attention module to capture social interactions and visual features respectively. To evaluate our final model Future, we use the most common evaluation metrics, average displacement error and final displacement error, to compare Future to these listed baseline models. We then performed an ablation study using various control settings to evaluate the contribution of each major component of Future. The results are shown in the table. For each dataset, we have highlighted the model with the best performance among all 8 models, including ours. As we can see, our model Future outperformed others, especially for dataset ETH, hotel, and university. The right figure showed the effect of the variety loss. Less change with respect to the number of simple NK means a better generalization. It showed our model is more generalized. Although for the dataset 01 and 02, our model does not perform as good as baselines, which leads us to further improve our model in the future study. To better evaluate Future, we first visualized the predicted trajectories and the corresponding ground truths in the first row of figures. The first sub-figures demonstrated that the scenarios like meeting, following, and avoiding. The predicted trajectories and their ground truths are overlapping for most of the showed cases. Due to the multimodality, the predicted trajectories sometimes do not agree to the ground truths. Comparing to ground truths, our predicted trajectories seem to be more conservative, especially in meeting scenes to avoid the potential and future clearance, which is of particular interest for some specific applications due to safety concerns. We then realized the predicted trajectory distribution in meeting and following scenes, shown in the second row of figures. We observed that the pedestrian collision is unlikely to occur because there is no overlapping among the predicted trajectory distribution at any step. And the variance of the distribution is reduced with the increased probability of clearance occurring between pedestrians. This shows that Future can well capture the fundamental factors, including multimodality, social interactions, and sense contexts. Last but not the least, we realized the learned attention weights from social aware attention module. We observed that the focused pedestrians will pay more attention to the pedestrians who are nearby or attempt to move towards themselves. This shows the social aware attention module can well capture spatial and temporal social interactions. We quantitatively and qualitatively evaluated the contribution of the first-person view information in the pedestrian trajectory prediction task. First, we found that adding first-person view information to Future leads to a decrease of 9.8% and 10.6% for average displacement error and final displacement error, respectively. This means that the model's performance has been improved. Then we realized the learned attention weights obtained in view-aware attention module. The figures show that the simulated first-person view images can well capture ego motions for the focused pedestrians. Ego motions, such as the focused pedestrians' visual perspective effect on the neighbors and moving intentions, are important in trajectory prediction. but difficult to capture using top-down view images or social patterns learned from the numerical inputs. Overall, it shows the first-person view images do play an important role in pedestrian trajectory prediction. To conclude our work, we first develop a simulator fusing to generate a 3D simulated scenario and render the first-person view images for each path string. Then we render the first-person view images for each path string. Then we build a first-person view-based trajectory prediction model future to capture social interactions and visual features with ego motions. By using multi-head attention mechanisms, our experimental results showed our model achieves state-of-the-art performance. For more details of our work, please read our paper. Thank you.
All right, thank you very much. And I forgot to say at the beginning about how we're handling questions. It'll be like the other sessions where there's sort of 10 minutes at the end of this session to ask all 4 speakers questions. So if you have questions, feel free to send them via chat or raise your hand when we get to the question answering time. Okay, thank you very much. And so then the next talk is, let's see, temporal aggregate representations for long-range video understanding. And I think Fatime, are you here? Oh, great, perfect.
I hope you can see my presentation.
We can, and we can hear you.
Perfect. So hi, I'm Fadime, and today I'm going to present our joint work with Deepika Singhania and Angela Yao. Our work's title is Temporal Aggregate Representations for Long-Range Video Understanding. In this work, we designed a model to tackle understanding long-range videos, and we specifically worked on action anticipation. Next action anticipation predicts the action that occurs several seconds from the current time t. And dense anticipation predicts actions and their durations multiple steps into the future. And future prediction requires reasoning from current and past observations, and also raises several fundamental questions like, how should temporal relationships be modeled? What temporal extent of context needs to be processed? At what temporal scale should they be derived? And how much semantic abstraction is required? We address these questions with a flexible, multi-granular temporal aggregation framework. Here we present an overview of our model and our model components, which we build in a bottom-up manner. We begin by introducing our representations, which are the inputs to the building blocks of our framework. We first split video streams into snippets of equal length, and then max pool the frame features within these snippets. Based on different start and end frames and the number of snippets, we define 2 types of snippet features. The spanning features S are drawn from the entire long-range video, and the recent features R are drawn from recent observations. In our work, we use ensembles of multiple scales and granularities. To represent the recent and spanning past at various granularities, we pool snippets over multiple scales. For spanning snippets, the start and end points are fixed and the number of snippets changes. And for recent snippets, the end points and the number of snippets are fixed and only the starting points change. One of our main components is our coupling blocks, which relate recent observations to the long-range past. And we apply non-local operations to capture relationships between the spanning and recent snippets. Using non-local blocks, we define attention-related spanning and recent outputs in our coupling blocks. And the final representations for the recent and spanning past are computed by aggregating outputs from multiple coupling blocks in our temporal aggregation blocks, TABs. And the strength of these building blocks, that TABs, comes from using ensembles of coupling blocks as input. TAB outputs are multi-granular video representations that encode both the recent and long-range past, and we name these temporal aggregate representations. Temporal aggregate representations are generic and can be applied to various video understanding tasks. Here we show an example of TABs chained together for next action anticipation and dense anticipation. For next action anticipation, the temporal aggregate representations can be directly used with the classification layer. And when the individual actions compose a complex activity, like making cereals here, we can add an additional loss based on the complex activity label. For dense anticipation, we perform multi-step estimates. We first predict the current action and the remaining duration for the current action. For predicting future actions, we concatenate all recent and spanning aggregates and the classification layer outputs from the current action predictions. And then we pass the concatenation through a linear layer before feeding the output to an LSTM. And the LSTM at each step M predicts an action and its duration. We experimented on 2 instructional activities dataset, breakfast and 50 salads. And we also experimented on a daily activities datasets, Epic Kitchens. One notable difference between these datasets is the label granularity. It's very fine-grained for Epic and coarser for breakfast and 50 salads. Next action anticipation for breakfast and 50 salads predicts the action that occurs 1 second from the current time t. And our aggregates model is flexible and can take as input either visual features or frame-wise action labels. As visual features, we use I3D or Fisher vectors for breakfast and 50 salads. And as frame-wise action labels, we either use the ground truth action labels or the outputs of a temporal video segmentation algorithm. Using directly Fisher vectors, we are comparable to the state of the art in breakfast, and we outperform it in 50 salads. And our results improve when we replace the weaker Fisher vectors with I3D features for both data sets. And we test our temporal aggregates model. Basically, we train our temporal aggregates model for temporal video segmentation, and then use the segmentation outputs as input to our anticipation framework. And our accuracy improves when using the segmentation outputs. This indicates that using higher levels of abstractions is better for anticipation. Our model can take also the concatenation of visual features and the frame-wise action labels as input. Merging our segmentation labels and I3D features improves our model's performance. And finally, if we substitute the ground truth labels instead of the segmentation labels, we get the upper bound performance of our model. There is still a big accuracy gap between using the ground truth labels and segmentation labels, which suggests that the quality of the segmentation matters. Dense anticipation predicts frame-wise future actions. The task is predicting specific portions of the remaining video after observing a given percentage of the past. For breakfast, when using ground truth labels, we outperform the others for shorter prediction horizons. When using directly Fisher vectors, we outperform the state of the art. And when using the segmentation outputs trained on Fisher vectors, we are comparable. Similar to next action anticipation, we further merge visual features with action labels. We observe a huge performance increase compared to only using frame labels, and we outperform the state of the art. We observe further improvements once we substitute the Fisher vectors with I3D features. We confirm that higher levels of abstractions are more preferable for dense anticipation. And again, similar to next action anticipation, there is still a large performance gap between what can be anticipated with inputs from current segmentation algorithms in comparison to the ground truth labels, leaving room for segmentation algorithms to improve. The anticipation task for Epic Kitchens requires anticipating future actions 1 second before they start. We report our results on holdout test sets of Epic Kitchens for seen and unseen kitchens, S1 and S2. We use appearance, motion, and object-based features provided by Furnari and Farinella, which are also used by RuLSTM, and we outperform all competing methods, including the state-of-the-art RuLSTM. Here we show examples from our model for next action anticipation for multiple anticipation times. This is an example where our model is certain about the next action for all different times. And this is an example where our model's prediction gets more accurate when the anticipation time is closer. We vary the duration of spanning paths for Epic Kitchens and breakfast for next action anticipation. Using the entire path increases the accuracy for breakfast. But for Epic Kitchens, increasing the scope of the spanning path does not increase the performance. We believe that this has to do with the fine granularity of the labels in Epic. We think that there is not enough training data for our model to learn all the variants of long-range relationships beyond 30 seconds. For action recognition, we follow the protocol of Epic Kitchen's action recognition challenge to classify pre-trimmed action segments. For action recognition, we only make changes in the representation of our model by adjusting the scope of our spanning and recent snippets according to the action start and end times. We outperform the state-of-the-art slow fast networks, and together with our anticipation results, we conclude that our method generalizes to both anticipation and recognition tasks well. And finally, as I stated before, our model could also be used for temporal video segmentation. Here, the task is predicting frame-level action labels of complex activity videos. We use a sliding window of 2 seconds and generate multiple windows. We train our models to assign an action label to each window, and we test our model with 2-second and 5-second windows separately. We observe more fragmentation in our segmentation with segmentation for 20 seconds than for 5 seconds, but get better accuracies with 2-second windows. And we've performed comparable to the state-of-the-art on breakfast. And to conclude, we presented a multi-scale temporal aggregate framework for long-range video understanding. Our representations are generic and can be applied in various video understanding tasks. And we evaluated our model on 3 complex activity data sets. Our experiments show that max pooling is a simple but effective way of representing video snippets. We also show that attention mechanisms relating the present to the long-range context can successfully model and anticipate upcoming actions. And the context of the extent of context is beneficial, however, may depend on the nature of the activity and label granularity. We also found significant advantages of using ensembles of multiple scales. Thank you.
Great, thank you so much. So again, if you have questions, stick around till 3:50, because we'll have a combined session to answer questions from all these speakers. And the next talk is, let's see, temporal aggregate representations for long-range video. Oh, sorry, no, that's the one I just talked about. COBE, contextualized object embeddings from narrated instructional video. And Gatus, are you there?
Yeah, can you see the slides?
We can, yeah, we can hear you great.
Okay, great. Yeah, so I'm Gatus Bortasis from Facebook AI, and I will now present our latest work called Contextualized Object Embeddings from Narrated Instructional Video, which is a joint work with Lorenzo Torresani. So many objects in the real world undergo state changes which dramatically alter their appearance, such as in the case of tomatoes, which can be half chopped, liquid or solid, green or red. And in this work, our main goal is to design an object detector that can predict all such states and contexts of objects. And this is in contrast to standard object detectors, which are typically trained to predict objects at a very coarse level, where label spaces are typically expressed in terms of nouns such as cat, dog, apple, orange. And unfortunately, such noun-centric ontologies fail to represent dramatic variations in objects' appearance due to their changes in object state. So for example, if we applied standard object detector in this image, it would predict that there's an egg in this image. And instead, we want to design a visual model that would be able to predict not only that there's an egg in this image, but also some additional contextual information, such that maybe an egg is being cracked into a bowl. So that's basically our goal. And in a sense, this is similar to the modern contextualized language models, which have recently enabled very rapid progress for lots of natural language processing applications. And most of these models are based on the transformer architecture. And the key characteristic of these transformer models is that for every word in a given input sentence, they can compute a contextualized word embedding that captures information not only from the word itself, but also from the entire sentence. So for example, if we consider a sentence break an egg into a bowl, the feature vector associated with the word egg would capture information not only related to this word, but also to the contextual action of breaking, as well as contextual object of bowl. And so this basically raises the question whether we can learn contextualized representations for objects in the visual domain in the same way as language models do for words in a textual domain. And to do this, we leverage the recently introduced How to 100 Million dataset, which contains a large number of instructional videos where each video is also accompanied by automatically transcribed narration. And because this dataset contains lots of human-object interactions, and because it provides more detailed object descriptions in a form of textual narration, we believe that this is a great data set for our goal of learning contextualized object representations. And so with this goal in mind, we now present our system for learning contextualized object embeddings, which we refer to as COBE. So our system takes two inputs during training, a video frame and a textual narration associated with that video frame. And we first feed the textual narration through a pre-trained transformer-based language model, which computes a contextualized word embedding for every word in the narration. In parallel, we also feed the video frame through a visual detection model, which corresponds to a modified FastRCNN design. And in this case, the key difference is that instead of using standard classification branch, which predicts coarse object level categories as is usual, we replace it with a contextualized object embedding branch, which predicts continuous representations for every detected object instance. And in a sense, we're forcing this contextualized object embedding branch to basically predict a vector that matches contextualized word embedding associated with that particular object instance. And the model is guided to do so by using a contrastive loss function. And so as you can see, the model is quite simple. It can be trained end-to-end easily. And during training, we're basically using these textual narrations to supervise the visual detection model. But then during inference, we don't need the textual narrations anymore, and our model can operate on video frames alone. And so now we look at some of the results. So first, we apply our model on object-to-text retrieval task. So because COBE is trained to predict outputs in the same space as contextualized word embeddings, we can use this model to basically retrieve most similar text pairs to a given object instance. And in this case, we represent text in a form of object context tuples, where object represents a coarse object level category, and context can be any word describing some contextual details related to the object. And as you can see from the results, here basically the green bounding box depicts a predicted object instance that is used as a query to retrieve most similar text. And below we visualize some of the most similar text tuples. And as you can see, the model is able to capture a diverse set of contextual cues, which is exactly what we want, because now we can represent these objects not only in terms of their coarse level categories, but also in terms of some additional contextual details. We can also reverse this task, and instead of doing object-to-text retrieval, we can perform text-to-object retrieval. So in this case, given a text query of the same form, an object context tuple, we can retrieve most similar object instances in the COBE space. And here we visualize some of these results, where every column depicts a fixed object category, and every row depicts a different context word. And again, as you can see from these results, our model is able to capture a variety of different contextual cues, which includes objects' functional properties, their shape, their size, and even actions applied to them. For example, in column 2, for object category sauce, we can see that our model is able to retrieve different types of sauces, such as barbecue, hot, or soy sauce. For column 4, object category pepper, you can see that COBE is able to retrieve peppers of different color. So it's basically can represent a variety of different contextual cues. Lastly, we'll look at the idea of visual object analogies, which is inspired by some prior work on language representation learning, which has shown that it's possible to perform semantic analogies by applying very simple vector arithmetics on word embeddings. And so because COBE predicts a contextualized word embedding for every detected object instance, we want to leverage these composition language properties, but now in a visual domain. And here we try to visualize some of these visual object analogies. So in the first row, we showed that adding the difference between chopped onion and onion to an instance of a tomato results in a retrieved object instance of chopped tomato. In the second row, we showed that adding the difference between pot with water and pot to the instance of glass results in a retrieved object instance of glass with water. And what these examples demonstrate is that COBE is basically able to retain at least some of the compositional properties of the language model that was used to train it. And this becomes very beneficial when we start considering zero-shot or few-shot learning scenarios, which we have experiments for in our paper. And so to briefly conclude, so in this work, unlike prior work, which mostly focuses on noun-centric object detection, Here we presented a framework for learning contextualized object representations that are able to capture fine-grained contextual cues related to object states and actions applied to them. Unlike prior work in this area, our framework doesn't require any manually labeled text descriptions. Instead, we leverage these noisy and automatically transcribed narrations of how to 100 million data set, which is beneficial because we're able to leverage this extremely large scale database without worrying about costly and time consuming annotation process. And lastly, as I already hinted, we showed that because our model is able to retain compositional properties of a language model that was used to train it, it's actually quite effective in the settings of zero-shot and few-shot learning, which is something that traditional object detectors were shown to struggle with. So that's pretty much all I had, and please check out our paper for more details, and I'd be happy to answer any questions at the end of the session. Thank you.
Great, thank you so much. Yeah, so then, yeah, hold your questions until one more talk, and then we'll have an open question answering time. So the final talk in this session is generating videos of zero-shot compositions of actions and objects. And Mega, yeah. So we can see your slide.
Okay, am I audible?
You are, sounds great.
Okay. Okay, I think my Zoom is giving me some problem. Just a minute.
Sure, no problem.
How about now?
Yep, we can see the slide.
All right, great. Yes, so hello everyone, I'm Megha Nohal, and in this talk, I'll give a brief overview of our work on zero-shot compositional generation of human-object interactions. This is a joint work with my collaborators, Mangyao Zhai, Andreas Lehrman, Leonard Sigal, and Greg Murray at Borealis AI and SFU. So in this work, we generate human-object interaction videos by modeling these videos as compositions of actions and objects. Specifically, we propose the task of generating human-object interaction videos depicting unseen compositions of actions and objects having seen certain action-object compositions during training. For instance, given training examples, wash aubergine and put tomato, an intelligent agent should be able to imagine action sequences for unseen action object compositions, wash tomato and put aubergine. So why is this problem useful? Well, it is very expensive to acquire videos for all possible compositions of given sets of actions and objects. And being able to generate realistic videos in zero-shot compositional setting obviates the need to observe every possible combination during training, and therefore avoiding the combinatorial explosion involved in modeling complex scenes. In this work, to handle zero-shot aspect, we disentangle the action and the object. However, there are certain challenges specific to HOI video generation. For an AI framework that can generate realistic HOI videos, the generated output must contain the object designated by a semantic label, optionally should occur in a specified scene, which might be given as input to the framework, while maintaining feasible visual relations with other objects in the scene and exhibit temporally consistent action on that object. Based on these observations, we propose a novel framework, HOI GAN, that generates a video corresponding to a given target action on the target object using an image with an object mask as the background. And as we can see, our model is able to synthesize a realistic video depicting the desired interaction. In this example, the composition take spoon is unseen during training. I'll now describe our proposed model. So HOI-GAN encodes the image to a visual embedding using a convolutional encoder, and the action and object labels to semantic embeddings, which in our case were glove embeddings. These embeddings are used as conditional inputs to the convolutional generator network. And the generator network is trained with the help of 4 discriminators, all involved in a zero-sum game. The frame discriminator learns to distinguish between real and generated frames corresponding to the real video and generated video respectively. The gradient discriminator enforces temporal smoothness by learning to differentiate between pixel level difference between consecutive frames of the real video and the generated video. The video discriminator learns to distinguish between the real videos and generated videos by comparing their global spatiotemporal contexts. In addition to these 3 pixel-centric discriminators, we also propose a novel object-centric relational discriminator. Driven by a spatiotemporal scene graph, this relational discriminator learns to distinguish between scene layouts of real videos and generated videos. And all of these discriminators and generator are trained simultaneously. Specifically, the relational discriminator develops a spatiotemporal scene graph based on mask RCN and object detections. So each object per frame forms a node in the graph. The node representations are formed using a visual feature of the image region corresponding to the object, augmented with the position and the aspect ratio of the bounding box detected. The weights of these spatial edges, shown as black solid lines in the figure, are given by inverse Euclidean distances between the centers of these bounding boxes corresponding to the objects which appear in the frame. The objects that appear in the overall video but not in the frame have no connections, as marked in gray lines. Now, these nodes are connected spatiotemporally by setting the temporal edges to 1, shown by black dashed lines in the figure. And the objects that do not appear in the consecutive frames are disabled by setting the temporal edges to be 0, as shown in the gray dashed lines. Once we obtain the spatiotemporal scene graph, graph convolutions are applied on this graph obtained from the videos. And the output of the GCN is aggregated by stacking and pooling along the time axis, and eventually the adversarial loss is computed on the aggregated output. We conducted experiments on 2 large-scale video datasets, Epic Kitchens and 20BN something something. We evaluate our model against 3 baselines on both the datasets with different input settings described in detail in our paper. And we use inception scores for evaluation, which indicate higher values, and higher values indicating better performance. So we can see HOI-GAN in brown outperforming all the baselines by a wide margin. The qualitative results show that our model is able to generate objects of diverse shapes and sizes, as well as diverse set of actions. Here, the context frame comes from an unseen set. So since our model has seen book with other actions and move with other objects during training, when asked to generate a composition of move and book, HOI-GAN generates pixels for book based on the information pertaining to the label book learned during training, and similarly for the action move. Here are results showing our model is also able to create the right object, even if the mask is of different shape. For example, in Lift Apple video, we see that even when the mask is of the shape of a banana, HOI-GAN is able to generate the object apple at the position of the mask and modifies the background accordingly. HOI-GAN is also able to create diverse set of objects for the same target action category in the same context scene. The results here show that it adapts the generated object roughly to the size of the mask, such as handbag, which could be larger in size in training videos, and banana, which could be smaller in size in training videos. HOI-GAN also generates different hand motions and hand appearance in the same context frame. For instance, compare lift handbag and lift banana videos. It is also able to modify the background given in the form of the context frame according to the desired interaction. For example, in lift mouse video, we can see infilling type of effect in the background. Moreover, our model is also able to create diverse set of actions with different visual instances of the object corresponding to the same label in the same context scene. So here in the videos generated by HOI-GAN, the object ball looks different in every generated video. And our model also generates different hand appearances such as in remove ball and push ball video, and is also able to modify the background in according to fit the shape of the ball and generate realistic interactions. So to summarize, we propose the task of zero-shot compositional generation of human-object interaction videos. For this task, we propose a novel framework HOI-GAN that is based on pixel-level information as well as object-centric scene layout information in HOI videos. And finally, we show that HOI-GAN is able to generate realistic videos depicting diverse actions on objects. For more details and additional results, please visit our webpage, and I'm happy to take questions during the Q&A session. Thank you very much.
All right, great. Thank you so much. So now we are at the Q&A session. And so if you have any questions, feel free to either raise your hand and we can call on you, or feel free to answer or ask via the chat. And so we can bring all the authors back on and see what questions we have. It looks like Dima had a question. Dima, do you want to ask your question, or do you want me to read it?
I can ask it. Thanks, David.
Sure.
So it's about the last paper. I'm just confused whether you have like one deterministic video generation per case, per mask, because you show a diversity, but on different inputs. Is there like a deterministic generation? And if there isn't, where is the variability coming from?
To get the question right, are you asking about deterministic behavior of the mask?
You have one video frame, one mask, right?
Right.
Can you generate multiple possible pickup apples? Or is there like one apple that will come on that particular mask?
No, so we can generate different apples in the same scene at the same mask.
And so, where does the variability come from? Is there like a noise vector that you pass to the GAN that decides that?
The generator is stochastic, and it gets a noise vector which is also as the conditional, which is also as the input besides the conditional inputs.
Okay, thanks.
Yeah.
I also had a question to the last author.
Yeah, sure, go ahead.
Yes, I was just curious how important all the discriminated, these GAN losses are, like which ones are more important than others. Yeah, can you comment on that?
Sure. So in our experiments, we observed that the gradient discriminator, which ensures the temporal smoothness at a pixel level, and the scene layout based discriminator, these two were very important to the generation process. Specifically, the relational discriminator led to a huge boost in the inception score. But besides that, in the qualitative results also, we saw that the generator was able to create more feasible interactions when it was trained along with the relational discriminator. So in our paper, we have an ablation study that can that basically builds on each of the discriminators. Does that answer your question?
Yeah, thank you.
Thanks.
Thank you. Any other questions for any of the speakers?
Yeah, I have a question for Fadime for the second talk. Did you look into the importance between the recent past or the spanning past? Like, did you do any experiments determining which is more important?
So it's actually like if you only use the spanning past or recent past, the performance is not as good as using the combination. You can actually see these ablations in the paper.
Okay. Did you find? Yeah. Okay.
I mean, there is a performance change of between 2 to 4%, basically.
Okay. Thank you.
Welcome.
And then I have a couple of questions for the third talk for Geras.
Sure.
Did you find, so when you showed the qualitative image of say the pepper and you had the red, green, and yellow images, so do you find in the space and that it's kind of learning or projecting into, that it's kind of portioning off for a single object such as pepper, do you find that it's portioning that space off into red, green, and yellow, or is it doing the opposite where it's kind of got a red group of objects where it's kind of, and then a green group of objects?
Yeah, it's for sure more biased towards objects because yeah, I guess still like you don't want to lose the capability of predicting these coarse object level categories. So yeah, basically the model is still able, even if we apply it for a standard object detection task, it's still able to perform quite well, and in some settings actually even better than the standard object detector. So yeah, like it's I would say it's a former where basically it's a ladder where basically it's more yeah, it's dividing basically the coarse object category into, I guess, these finer grained categories as opposed to just like finding everything that's red. But yeah, we do see that there's basically it's able to transfer like these contextual properties across different objects as well. Like we have zero shot experiments, and we do see that even if it hasn't seen certain states for a few for some object categories, it's still able to perform reasonably well on those.
Okay, great, thanks.
Any other questions for our speakers? So I have a question for the first talk, Hui Kun. Sorry, probably not saying your name right, but I was curious, you said something about generalizability. I was wondering if you could talk a little bit more about that. And I was wondering specifically if there were interesting failure cases that you came across that indicated that there was some overfitting or some sort of something going on indicating what had been learned.
You mean because actually because we just provide a simulator, it will always still have something different from the ground truth. And actually for the dataset 0 and 02, we have not the best performance than the baseline model, because if you are familiar with these two datasets, you will find that there are some parking vehicles and some situational obstacles like buildings in the scenario, because we don't have the correct positions and some other labeled data of these obstacles. So we did not transform this obstacles in our simulator. Maybe this will make our results not that bad, not that better. So, but in the future, we will try to improve this part in our results.
Okay, great, thank you. Any other last minute questions before we conclude this session?
I guess I have one more question to the last speaker. Basically, sure. I was very impressed sort of by the quality of hands and objects generated in the video. And I guess like from what I understood, it didn't seem like you explicitly used, I don't know, some sort of additional constraints for like object or hands generation, or even like these like mask segmentation. So I was just curious, like, can you comment on, yeah, how did you, like, what's sort of the main reason why you were able to obtain such good results? Or was it just like kind of the network, because of those 4 losses, it implicitly learned these?
Yeah, thanks for the question. So we believe that we were able to generate like diverse hands and different skin tones as well, because of the relational discriminator, because the mask CNN image regions that were obtained were able to detect hands very well. And also because of the temporal constraints. So the trajectories of hands were well captured using the gradient discriminator loss. But we didn't have any additional constraint pertaining to the hands.
I see.
All right, great, thank you. So our timing is perfect. We're exactly at the stop time. So it looks like we have a 15-minute coffee break. So go make yourself coffee. And then we'll be back at 4:15 for the invited keynote. So thanks so much to all the presenters, and thanks so much for asking questions, and see you in a little bit.
Hi, everyone. We'll be restarting in a couple of minutes. Richard, I don't know if you want to try sharing your screen just to check that everything's working okay.
Morning, afternoon, Michael. Yeah, I'll just give that a go. Can you see that okay, Michael?
Yeah, I can see it fine. Do you have any videos that you want to check, or is it all good?
I think I realized that anything with audio in might not be able to be heard, right? If I'm on my headphones, is that right?
You can, in the share screen options, there's a box which allows you to send audio through, I believe.
Okay.
You might need to restart the screen share though to see it.
Okay. I don't hear that. Okay, I'm just going to try and see if I can get that audio to work. Hi there, Michael. Can you hear me?
Yeah, I can hear you fine.
That was just really broken up.
Like, yeah. Can you hear that?
Yeah, we can hear the videos now.
Awesome. Wow. Okay. And then is it normal to keep this on the side here, or do I hide thumbnail, I guess?
I think it's whatever. I think we'll see your video.
Okay.
But I guess we'll start. So welcome back everyone to the final session for the EPIC workshop, which will now have our two final keynote speakers. First, we have Richard Newcomb from Facebook Reality Labs. And Richard did his PhD in Imperial College London and now works at Facebook Reality Labs and Oculus VR as a Director of Research Science. And we're very excited to hear a talk from Richard talking about augmented reality and robotics in the future of embodied AI research. So over to you, Richard.
Great. Thanks very much, Michael. And thanks, Dima, Michael, and the organizers, Ontario, for inviting me here. Great to be at a conference again. Okay. So I'm going to get started actually and introduce what I think is fascinating about EPIC. And it's really slowly dawned on me as after actually first meeting Dima, who had introduced me to this incredible data set, the kitchens, a year or so ago, and realizing that there were a lot more similarities in what was starting to go on in folks who are working with EPIC-like data sets with the areas that I was coming from and our teams historically in robot vision were coming from. So I thought, let's have a look at the similarities and differences across these different application areas, which are in sense are application areas of EPIC in the sense that they all use some form of egocentric data, trying to achieve perception, some form of interaction, and certainly the challenges with computing within the egocentric frame. So there's these four broad what I think of as application areas. I mean, they're vastly different in various ways, but they all touch on or have touched on egocentric data and its challenges. And the first to do that was internet scale computer vision and the related topics of AI. I guess CV is a subtopic within AI. Today, we're happy to talk about that at large. And of course, this massive scale photographs came from folks taking from their mobile phones specific perspectives that were moving from the curated data of a photo is a cherished individual thing that is quite rare to you can take them at any point in time and publish them to, for example, social networks. And in that respect, they produced the first kind of mass scale pseudo egocentric data and introduced with that new challenges of how to take advantage of that data from a research perspective. And also for the first time obtaining images with often aligned text, videos with audio. And so opening the doors to various forms of supervision with that data to achieve the perception challenges, all within this pseudo egocentric frame, because the photos, of course, and the videos are not really the live view of the individual as such. It also introduced interesting challenges with data ownership, privacy, and data bias that had not been seen at scale before. Moving to what historically has been a very different area, robotics is perhaps the first research area of egocentric data. It must be egocentric if you're going to have a mobile autonomous robot. And we see that today in the research areas of driverless cars, picking, packing, even home robots with vacuum cleaners, drones that can follow their users, etc. Using all egocentric onboard processing and sensing. And this is certainly where my background is from, at least aspirationally, and in robot vision. And it introduced this area and it continues to be one of the richest sources for mixed data, mixing not just image and video, audio, but also IMU data, depth data. Importantly, there's explicit control signals with robotics. So any of the perception or interaction tasks with respect to the robot, or even robots interacting with their environments, robots interacting with other robots and humans, we have control signals, and that's pretty unique relative to some of the other areas. The form factors of robots to make them mobile introduce constraints, and they're very interesting and important with respect to the challenges that have to be faced for practical applications of the machine perception and AI in a mobile robot. And it's also useful to look at the perspective, I think, that robotics has shifted from actually a few paradigms, but they broadly break into traditional model predictive perception action loops, i.e. build a model, keep the model up to date, use that internal model with some sort of a control cycle, and ultimately produce control, which closes the loop on the perception action. And in recent times, we've seen the state-of-the-art approaches utilizing sim-to-real with full end-to-end machine learning from the sensor data through to the actuators, not explicitly building underlying models, but both are still very relevant today. In the third category, augmented reality and what I guess these days we're calling AI wearables. And for this, we really mean the future of these AI wearables, because they don't really exist today in the forms that I think we're interested in from an EPIC perspective, i.e. yes, we have with us Siri and other assistants, but they don't utilize the class of data that we're interested in EPIC research. And these have a massive overlap with robotics. The difference is they really are egocentric. So if we're talking about AR glasses, as I will do through the remainder of this talk, we're talking about the closest perspective to a human point of view as is possible. Importantly, and in contrast to robotics, there's no explicit control signal. And so the challenges that we face on enabling interaction via the data that it is observed and some models that are built, which actually is a new challenge in understanding human intention, within the always on egocentric frame of reference, there's no explicit control signal. So you can't necessarily look at what happens when you ask a human to do something and expect that that signal that's obtained actually is with respect to that request. Beyond the form factor constraints of robotics, to be able to achieve the types of form factors that we would like for augmented reality wearables and AI wearables in general, the constraints are phenomenal, and we're going to look at that in detail. There's also not just constraints on the hardware in terms of the form factors, but also in terms of the data, and not just from a point of view of a live device, but from a point of view of if we were to do research with this data, how could we even store it? I think it's also important to note that both robotics and augmented reality, because of the tasks that are trying to be solved, introduced this deep connection between physical metric scene understanding and semantic scene understanding, versus the internet scale CV, where the relevance of understanding metric geometry or how objects actually articulate, etc., is not so important from that field perspective. For robotics and for augmented reality, where it's important to be able to have a metric understanding and at the same time understand that scene from a human perspective by semantic understanding, these come together really for the first time in really clear-cut tasks. And finally, these are all related, of course, as somewhat abstract models for the sciences that are looking at how is it that animals, including humans, actually do what we do. And so EPIC research joins all of that via these different computer science and related research topics with understanding brain science and in general the cognitive sciences. So the perspective I'm coming at from a more recent era, the last 5 years, is understanding the potential of wearables to really unleash three major areas of application. The first one is to introduce virtual objects. And so from this perspective, this is the science fiction desire, although it's becoming very real very soon, to be able to have a pair of glasses that you can wear all day and be able to augment your reality with virtual objects. And there's different sorts of virtual objects. A virtual object might be purely virtual, i.e. a piece of art that couldn't have existed, and it's rendered and persists in your frame of reference as if it were real. There's a second class of virtual objects, which we can think of as the virtual extensions to physical objects, which actually enhance physical objects. And that's also very exciting. That second category relates very much to the future of contextualized AI and AI assistance, being able to understand your surroundings in great detail and from a personal perspective, so that the relevance of the current context of a given scene, not just in a moment, but over potentially a day, a year, your lifetime, becomes ever more relevant. The final category, which I'm not going to talk about a lot in this talk, is what we call social teleportation, which is the desire to be able to utilize the fact that if you have a headset on, there's no reason why the virtual objects can't be other people. And in fact, if there's certain classes of head-mounted display, that we can't transport our senses, so to speak, into the models or a virtual copy of reality. And so I'm not going to talk about that last category. I'm going to talk instead about the virtual objects and AI assistance with respect to the challenges that EPIC faces. So EPIC lives across live devices, ultimately, and infrastructure. And this is just a set of areas where I think if we're doing research with egocentric data and we're looking to the future applications in, for example, augmented reality, we have to appreciate the opportunity and also the challenges that are faced by real systems and where we can actually do optimization and research. And so from the sensor data itself through to how on earth that sensor data gets communicated with some state, either to the users, in between there is a good chunk of wearable computing, edge clients that somehow connect cloud infrastructure class, elastic compute and massive data stores with those clients. And so the question really is, when we're doing research, where is it relevant to think about that data living, the compute living, and how can we optimize the full stack to be efficient? And how do we then take those those challenges of the full live device and infrastructure and place better algorithms in the right place so they can achieve what they need to do with, for example, the lowest power to enable more always on, or with the smallest form factors to enable always on. And that's a major challenge for EPIC. So I want to pull out just one example of the kind of incredible constraints that we face, and just did some back of the envelope calculations here that certainly guide me when I'm thinking about these EPIC challenges. So here, just put together a basic spec for what, if we were to use today's sensing technologies, a full HMD for a glasses augmented reality device might look like. And so we see that there are SLAM cameras. This is for head tracking predominantly. Generally color cameras that are going to do a lot of the heavy lifting with respect to the egocentric view and the, whether it's body tracking, hand object interaction, scene understanding in general through visual means. There's going to be eye-facing cameras to understand the gaze of the user, but also to be able to solve problems associated with the world-locked rendering stack to be able to achieve the kind of world-locked objects for virtual object interfaces. We need to know where you're looking. IMUs, with respect to the inertial measurement unit, we need those together with the SLAM cameras to be able to solve the fundamental head tracking problem. Microphone arrays, and not just single microphone, not just stereo, but actually several, capturing near field, far field, and spatialized. And this enables future applications in beamforming and various other super powers where we would like to be able to increase one area of audio in a scene or decrease others. And then there's a lot of other sensors, and I'm calling them negligible from a specification and a sort of a data perspective, because really in comparison to these other data channels, they very much have small bandwidth. So with a SLAM system, you're probably looking at 2 cameras. They absolutely in the state of the art in the literature. Reasonably 0.3 of a megapixel is okay. Certainly we can look at the devices that have been shipped from companies like Microsoft HoloLens, and they use 640 by 480 there. RGB cameras here, 2 megapixels probably is not as much as a lot of researchers are starting to use, but certainly again, looking at the literature with big data, 2 megapixel is a reasonable size image. And really what I'm pointing out here is these specifications are all actually quite conservative. In general, we're looking at stereo pairs of cameras, and you certainly need 2 cameras for 2 eyes. And you can compute through with respect to bit depth, frames per second, and resolution, and get the bits per second. And you can also look in the literature and find the general compression that's reasonable. So from Engels 2015 and approximately similar papers, Orbslam at the time, they utilize JPEG compressed image data, which provides about 10x compression. Very similar for other RGB data, video, 10x and better is possible. However, it starts to depend on the application. If we really need high quality color for a given application in analyzing photon accurate reconstruction, then actually compressed RGB data can be detrimental. So we go through and we get a computation, which is that if you wanted to have a 8-hour day recording, that would be on the order of a terabyte of data. Now, from a perspective of, how could we store that data? How could we transmit that data? How could we even do research with the data? Just one person, one day. It gets even more challenging when we look at, well, but realistically, for the continuous context, for the opportunity that there is with EPIC, we would like more than a day, and in fact, more than one person. And so very quickly, you end up with on the order of 31 petabytes of data for a year of just 100 people interacting. And you can have a look on the internet to see just the sort of stores that are 31 petabytes. This is significant. And to look at it from a perspective of a research team in a university trying to utilize 31 petabyte data sets, it's actually clearly infeasible. And we might be off by 1 or 2 orders of magnitude. We're still looking at potentially petabytes or hundreds of terabytes of data for these year-long data sets if we really wanted to be able to utilize multi-person, multi-season EPIC opportunities. So really the question is, how can we train and test on such data sets, or how can we utilize them in research? And ultimately, how can we enable devices that do a lot of the job on the device across that stack from the device to the infrastructure, so that actually the data never gets stored and doesn't need to get stored. Okay, so I think I don't need my video on, right? Okay. So I've just added there just where some of the computations have come from for that. Do tell me if there's an error there. Moving on. Okay, a second set of constraints beyond the data are the physical constraints in these future all-day wearables. And so I've just added one here, just to look at the perspective of trying to build a pair of always-on glasses. The problem isn't that the sensors, for example, the beautiful GoPro class sensors, they certainly are utilized today in EPIC research. The thing is to get those types of sensors into glasses form factor, or reasonable always-on watches, brooches, etc., that don't weigh too much and don't have form factors that are not desirable. There's physical constraints on the limits of the optics for the image components there, and we can take a quick constraint example here. So if we want to field a view of about 150 degrees and we want to have a resolution per degree of 0.1 degrees per pixel, and the footprint is what we might care about, and this for a rectilinear frame here, so projecting out so that a meter, a pixel shouldn't be more than half a centimeter, and at 10 meters it shouldn't be more than 5 centimeters. The constraint that actually comes in is to do with the pixel size. So in principle, you could have a tiny pixel less than a micron, and so then the multiplication factor of that resolution and the required optics that sit on top of it could be very small. But if you want a signal to noise ratio that allows a certain photon count in low light conditions to be detectable, then actually you need to increase the area of that pixel. And in modern phones, the sort of limits that they're at now are 1 micron or so, to be able to achieve the kind of video data that you can get from a front or back facing camera. Higher quality footage from the kind of egocentric videos that we prefer to use from GoPro, etc., more on the order of 2 microns and even above with respect to higher end data capture. And that suddenly becomes a 4 millimeter base sensor width for a 1920 pixel, approximately horizontal, to fit that 150 degree field of view. And so straight away, you've got half a centimeter worth of silicon with an optical stack that needs to sit on top, which to achieve a wider field of view, again, understanding that a pure pinhole, although that would give you, for any given focal length, a very wide field of view, will not let the photons through. So you end up having a big piece of glass on top of that big piece of silicon, and you end up with a big camera, and that big camera therefore limits, the applicability to wearable devices like the future of glasses. So how can we solve those constraints? I also haven't talked about, but we'll just note that the other constraints to do with heat dissipation come from effectively looking at bandwidth, so resolution times the frames per second of a particular camera times the bit depth is all transmission of data, and that's what uses energy, produces heat, and needs to be dissipated on an all-day wearable device. And we really see the challenges in producing glasses form factor sitting very much in this type of trade-off space. To get high quality data, you need bigger sensors. In cars, that's fine. In some robots, that's fine. In always on wearables, that is a limit. So what we've been doing at Facebook Reality Labs is to look at a view that says, well, if we were to try and solve the underlying problems associated with always on data, we face immediately the reality that not only can we not handle and process the kinds of data that could be produced from these devices, i.e. we can't store them and do research on them in that way end to end. Actually, if you move from the egocentric for a second and ask, in any given frame, in any given scene, what is changing? The answer is, well, most of what is changing is a function of users in the scene changing the scene. the scene typically is not changing that much. And we can think about that from a pure information change point of view. And so you get back to, well, wouldn't it be useful to stabilize all of the egocentric data, whether it's from one user over time or across users? And we think the answer is yes. And so then you get back to a form of building a model of this scene and keeping it up to date and using sensor data, effectively the egocentric sensor data, to keep that model up to date. And that's fundamentally what we're doing in live maps. So it takes a form of a base layer of localization technologies, SLAM systems and other visual positioning systems, and then layers on top of that the egocentric data to produce what we call a real-world index. And it does that via various different technologies in reconstruction, object detection, tracking, etc. But it does so from the egocentric view via understanding that those views can all be connected via a head pose, and therefore things like aggregation of data over time becomes consistent. All of this is here to enable essentially this real-world index in a common and shareable frame of reference to allow us to anchor virtual content. And that virtual content can be the virtual objects we talked about, or can be semantic knowledge that links places with knowledge graphs that we've been producing across humanity for the past 2 decades or more. So first, we're going to talk about the location technologies, and just remind everybody that location today in research is really not an act of looking at an image and asking where it is. Today, the cutting edge systems really make use of GPS, even make use of Wi-Fi or other wireless positioning technologies, introduce the new class of visual positioning, which allows you to relocalize via image and video into a coarse frame of reference on the planet, and then solves the fine-grained real-time localization using SLAM and VIO technologies. And this is all common now. And indeed, it's connected across robotics, where a lot of this originated, and the early augmented reality research on SLAM and VIO. Today, SLAM systems that can utilize egocentric views are incredibly robust. They enable consistent frames of reference on the orders of hundreds of meters with very little drift, on the orders of centimeters over hundreds of meters. And loop closure technologies that have been developed across the field enable us to be able to relocalize back into frames of reference and close loops to get metric consistent frames of reference. And so this is all established via egocentric video with IMU data. Typically, the front end of such systems these days are visual inertial odometry systems that tightly integrate the understanding of calibration of the IMUs and the camera data, and then a loosely coupled SLAM backend that allows a consistent scalable map to be built. What I want to introduce is that having collected massive data sets, and various teams around the world have been working on this, when you've got what you can think of as pseudo ground truth from a visual inertial or a full SLAM system, you've basically got data sets that have incredible correspondence throughout them. It's typically sparse correspondence, but that data is very useful. It, of course, also comes with a pose per frame. So egocentric data, in this case, gets lifted from being just video data to being data where every single frame is connected via this thing, which, if you factor it out, you basically get to a stable view. Now, I want to show just one recent result that the team has produced and published at IROS, which is where we've gone a step further and looked at, well, can we use these data sets to train systems that don't even look at the image data to achieve trajectory estimation? And so the new work is called Tight Learned Inertial Odometry from Wenchin and Jacob Engel's team in our lab. And there, the team used 60 hours of data, egocentric data, and ground truth supervision from Tassos Marikis's VIO system, and was able to enhance the initial result that was produced by Professor Furukawa's lab a couple of years ago, called Ronin. And the result, and I'll just see if I can get this here to work, the result is quite astounding for anybody who has worked in the SLAM space before. So here what we're seeing is the ability to obtain near SLAM metric quality trajectories in 6 degrees of freedom with only the IMU data. And the 3D Ronin that's being shown there is a version of essentially the initial 2D Ronin that was shown from Phil Kaur's lab, just trained for 3D displacement, whereas the tight-learned inertial odometry places that displacement data back into an EKF to obtain a full 6-degree freedom and high quality pose. And you'll see we started with a displacement on these trajectories so that we can see them more clearly, but the local motion relative to the VIO, which is the ground truth in this system, is very tight. So this is an example of effectively getting egocentric pose data without using the image, which is important for the future context. Okay, how do I go forward? Let me just stop that there. Not sure if anybody just having a bit of trouble with the YouTube video. Let's see, see if it resolves. I'll just skip forward here. Okay, so having established the egocentric frame back into a coordinate system, we can start to aggregate data into a shared frame of reference. And this is then where the research opportunity for building index comes from. In previous years, our team has looked at the quite traditional approaches, based on things like Connect Fusion, and extending it into really high quality, large scale models. Realistically, the way that we're looking at this going forward, and I think a lot of teams around the world are starting to look at it, is that a lot of the objects that could be produced, for example, the geometry that otherwise would be reconstructed using 3D reconstruction and fusion approaches, actually, a lot of those are manufactured objects. So I'm going to demonstrate in this next section here that the state of the art that you can get to if you just ignore effectively that worlds are composed of objects. And then we're going to move to our modern frame where we're starting to utilize object models. Last year, we introduced Replica, and this was, again, an opportunity to look at what could you do if we build high quality data sets that have real world video associated with them, but an underlying 3D model so that every part of that video has a pose. And the release of that data set is public and is in use by other research teams at Facebook and outside to be able to train things like reinforcement learning approaches. These models have textures, they have geometry, and they have labels, and all of the above have noise because these are real world places and through real world reconstructions. I think what's important is the quality of the models has been shown to be sufficient for training agents in an offline setting and then deploying in the real world. And Jitendra will likely touch on this in his talk later from the FAIR team. The quality of Replica moved far beyond that then state of the art, but I think we still have to recognize that this scale of these data sets, even if high quality, are nowhere near what is likely to be necessary for achieving the kinds of internet scale advances that came from internet scale computer vision. And so that leads to a real challenge, which is like, how do we get to scale to apply those types of approaches that demonstrated such success on image data for egocentric data? Nevertheless, we think that this type of high quality model allows for simulation and testing in a limited capacity with the kind of richness that wasn't previously available. one of the surprising results when looking at these fully non-parametric reconstruction approaches is actually it starts to look feasible that actually you could have a 3D model that is photorealistic. Here there's a video that we've shown a few times in the past where on the left is the real video and on the right is the synthetic view from a replica model. And the thing that first appears is actually it's very difficult for humans to tell the difference unless you pause frames. On the other hand, this really is still just a mesh with textures painted on it. So there's no real dynamic interactability with this model. Even though there's semantic labels underneath it, which are useful for training, you can't actually interact with this and hence use it for real epic research. One of the advances to move in the direction of moving away from just non-parametric meshes was to start to look at deep shape embeddings, and the team introduced deep SDF in 2019 at CVPR, and then have extended that to deep local shapes at this ECV, and Rowan's presenting that this week. The opportunity there is to say that we can take data sets and train embeddings that allow us to produce codes that then can predict, in this case, a sign distance function representation. And then you can use that for reconstruction, but also for detection and other things via jointly encoding from an image space to that code, which can then be decoded and then form a loss function between the decoded shape and the initial input. For example, if you have 3D shape image pairs. In DeepLS, we demonstrated simply that we can have vastly improved efficiency if you break the scene into a grid of local deep SDF shapes. The final piece of work I want to show on object-based reconstruction is Frodo, and that was introduced at CVPR. Frodo is our first attempt to utilize what we've learned from building object data sets and shape embeddings, and really, as the title says, go from detections through to actual 3D objects, which then, from a perspective of live maps, are there to be kept up to date via tracking technologies versus per frame reconstruction or per frame detection. So the approach looks at taking RGB data from a video, egocentric video, and producing a full 3D model with actual object instances in. One of the insights from the team was that to be able to achieve the kind of deep SDF decoding, if we jointly embed with a point-based decoding, then we can obtain much improved efficiency with respect to an end-to-end learning pipeline that allows us to go from detections through to instantiations of codes. So Frodo takes an approach where we decompose the problem into, first of all, detecting object instances in an RGB frame where we know where that RGB frame is through the SLAM trajectory. We're then able to back project the bounding box into essentially a 3D bounding box by intersecting them and solving for a reasonable bounding shape. We then take the shape encoding from the encoder decoder that has been trained, and we fuse those just by averaging into a 64-dimension vector, which we then optimize using a variety of metrics to obtain an underlying posed 3D shape. So this again is getting at the point that rather than trying to solve for 3D reconstruction from a single frame, realistically, Epic data is going to have continuous video data, and that we can use that to form aggregations of the data over space and time if you have the head pose, which is what we assume here. So those 2D detections are back projected into 3D rays, which are intersected and lifted to 3D bounding boxes. The shape codes are predicted from the encoder-decode networks and averaged and then we refine those shape codes using a variety of cost terms. This includes the pose of the shape as well. What you're seeing here is when it goes from the points to the 3D dense shape is the fact that the joint embedding of point and deep SDF allows us to utilize a mixture of sparse and dense terms. The code optimization takes form with cost functions of photometric loss, where we project 3D points from the decoded point embedding network back into the 3D views given the head pose, where we can then look at color consistency between views, geometric loss, which for the sparse and dense decodings takes the form of a 3D chamfer loss to the 3D SLAM points that are available from the SLAM system. And then finally, a silhouette loss, which is penalizing discrepancies between the 2D silhouette from the back projected shape. And there's two different versions, one that's based on the PW3P from Oxford, and one that's based on chamfer distance, depending if we're using the sparse or the dense decoding. This is just an example of 3 reconstructions obtained from 35 input views. And you can see that Frodo is incredibly close to the ground truth scans, and certainly at the state of the art with respect to this type of aggregation technique. Colmap is a standard state of the art though reconstruction that's being run on all 35 views there. And here finally is just an example scene composing 5 different shapes. Great. So everything that's been shown so far really is the underlying technologies, the location technologies, the indexing technologies. But what I also want to introduce in this talk is the opportunity to move towards multi-person synchronized data. So under the assumption that we have technologies that allow head pose to be obtained and for the frames of reference to be shared, data sets can be produced that allow for multiple devices with multiple people interacting in the same scene, and to start to look at the opportunity to synchronize those data streams in space and time. And the first work in this area is from Curtis Northcutt, where we worked over a year ago in an internship to produce really what was at that time the first multi-person synchronized data set. And this is in submission in PAMI as we speak. So EgoCom is a first data set of natural conversations that contain the video and also a stereo audio recording. And critically, each data set has synchronized embodied stereo audio. So not just synchronized in that the audio and the video are synchronized between the multiple participants. It also comes with a word level transcription timestamped to the videos together with the speaker labels. And with over 38 hours of video, it's a very impressive data set that opens up some new challenges, but also some new opportunities.
That was just really broken up.
Like, yeah, what's it called when you
grind it out?
When you grind up the Phillips. I can't think of the word right now. But I thought
ruined.
It was just, there's a particular word.
So that's a short clip from the data set without the transcriptions on. And a lot of the data sets took the form of Curtis leading natural conversation topic around our mock apartment here in Redmond. The opportunity with this type of data is to increase context, not just in the form of the temporal aggregation as we saw in Frodo, but actually in terms of the perceptual context of multiple people in the same frame of reference. The power of multi-perspective alignment for transcription is also something that was a bit of a discovery for our team. So,
mine bigger than that orange pillow?
No.
Okay.
It could be.
Usually.
But usually no.
Yeah, usually no.
Okay.
So that's an example recording from a participant viewing the other two participants playing a game. The opportunity when you have aligned videos in the same frame of reference, in this case, time frame of reference, is to be able to say that each device from each person's perspective has access effectively to a high quality audio source, which together is better than any individual audio source. So it's the same video, but summing the aligned audio.
Is mine bigger than that orange pillow?
This
No.
one?
No.
Just again here.
Let's see. Is mine something I'm like?
Is mine bigger than that orange pillow?
So it's clearly superior in clarity, and this is the point that the opportunity to have synchronized devices in the same space means that actually, whether it's the data from those devices, the compute, or in fact just the general context of the scene, these things can be shared with great advantage. Here's an example of using that summed audio to be able to have better natural language processing, utilizing in this case Google Cloud Services.
Okay, so new words. We'll do the same game.
Okay.
But new words.
Okay.
And we can go the opposite direction if you want.
Oh, like make it harder, or oh, I see what you mean. Yeah, yeah.
Like,
and should we go more toward?
Okay. So new words.
Okay, so I'm not sure how clearly they came across, but okay, in the interest of time, onto the conclusions. I think what we've found in the last few years is that data sets like EPIC, and I think EPIC epitomizes the data set, but also the research area and the interest across robotics, AR, AI wearables, and traditional computer vision. The fact that EPIC really connects the metric and the semantics in understanding problems that have previously been somewhat separated, perhaps except in robotics. On the other hand, there's endless data from this EPIC view, and it's a great opportunity, but there's significant challenges in how the researchers can both have safe access and practically use the data. For example, the computation of petabytes worth of data if we wanted to have aligned multi-person, multi-season egocentric data sets. We really believe that the opportunity is to resolve some of these by starting to work as a research field in understanding that there really are stabilized views, and that this is the advantage that can be brought from the technologies from SLAM and VIO that have come from historically the metric scene understanding space, but they ultimately allow us to put the egocentric view back into a shared and stabilized frame of reference where a lot of research problems become easier. And finally, I'd want to conclude that a lot of what we've learned ourselves with regarding the potential for privacy risk increasing is something that I think we need more research on. And it's not trivial to say that, because of course the different teams today are faced with challenges which are perhaps unknown with respect to the future use of these data sets. So whether it's the data sets themselves or the future of how we're actually building technologies that will land in products, we have to think about the new approaches that allow egocentric data to remain safe, both for the researchers using it with respect to exposure, but also more obviously to the users and the bystanders that are captured in these data sets, especially when we move beyond the individual person interacting in a basic scene setting. So with that, I'll end my talk and thank you all for any questions.
Okay, great. Thanks, Richard. That was a really, really interesting talk. If anyone has any questions, feel free to write them in the chat or on the Q&A service in Zoom. If you're a panelist, also feel free to unmute if you have any questions. I guess I'll start. So with the EgoCom, the last data set that you showed off, how did you kind of get, or how did they get it to be kind of natural? Like what kind of scenarios did they come up with, or was it just, here's a camera, just see what happens kind of thing?
Yeah, it was actually quite a lot of fun and a lot of inventiveness on Curtis, the research scientist's part. But yeah, we took the form of looking in the psychology literature and understanding things like games. Curtis himself comes from an area of research in academic learning, and so utilized a lot of the tools that are there to obtain natural conversation, but directed conversation. And so the apartment itself was utilized in forms of question answering. And the opportunity that we were looking at there was to try and say, well, how, given that this is a first kind of data set and it can only be so natural, given that you do need to have consent, etc. And it's, people have got things on their heads. Can we utilize the fact that we could have aligned 3D data sets with aligned audio and aligned multiple version view data and answer things like, what is that? And elicit responses, which are natural in that respect, but they're targeted and directed towards questions and answers or games that are meaningful in that setting.
Okay, great. Does anyone have any other questions? Okay, well, I have another one. So you mentioned at the start of your talk, basically how we kind of create this, future wearable device with all the specifications. And of course, from what you're saying, we're not there yet. What do you think there'll be kind of trade-offs in the next round of wearable devices, or will there kind of just be kind of a hold off for a commercial device or publicly consumer device until that's kind of all sorted? Like, will it be kind of a research focused thing until it's all done, or can you see kind of trade-offs being added?
Yeah, I think it's pretty clear that trade-offs will be added because the opportunity for egocentric data, even in snapshot form from wearable devices, is clear to improve context for example, an assistant. And we've seen that with some products on the market that allow you to get egocentric recordings from glasses. I think the opportunity for us in research, on the other hand, is to not let go of that richness of data. And that is to say, there's sort of like two tracks that we could go down. We could let products drive what kind of research gets done, or we could, as I think is happening really in actually the new release of Epic Kitchens, etc., try and get the best quality data at any point in time and appreciate that the relevance of that data in current products is like out of scope, to actually show the breakthrough abilities that actually you will get from training and ultimately maybe miniaturization of those sensors. I think the parallel tracks that are then going on are, for example, in the areas of sparse sensing, event camera work, where we can start to take a lot of that data and under an assumption of some sort of model, you can start to utilize much sparser data flows and achieve the same underlying tasks. But at every point in time, you're basically assuming that there's some sort of prior, some sort of model. And that's what drove us to live maps as well. So I think the general answer is I think both will happen, and we should, in the research side of things, really not wait for miniaturization. We should attempt to try and get data sets which are as big and crazy as possible, crazy from a point of view of the data, the epicness of the data.
Yeah, no, exactly. Yeah. Again, does anyone have any other questions for Richard? Okay, I've got one. Yeah, so do you see all-day wearables possible in the near future, in terms of, not in terms of technology limitation, which I guess my previous question kind of covered a bit, but also whether society be willing to adopt these devices?
Yes, I guess that's the big question. And there's I definitely don't believe in an inevitability argument of like the value of these things overriding the potential risks if they're not implemented responsibly. But I think that's where the challenge actually in our research in EPIC across the different disciplines is actually starting to arrive. So we start to see, and Mark Polyphase really kicked this off for us in the relocalization and other multiple view stereo communities, really starting to take seriously that we have to take privacy as a first order constraint on the algorithms, not as something that somehow just gets dealt with via some secure socket between the data that's captured and some processing somewhere. And so I think the point is that a lot of our research has not yet, across the communities, not really looked at the joint optimization between privacy and security, and doing compute where it needs to be done, and hence putting constraints on potentially distributed algorithms so that future users can have confidence that the technology is fundamentally secure and doesn't surface information that shouldn't be surfaced. I think a great example of that can be, via the contrast of GPS technology, which is a broadcast-only technology, but as it's surfaced today on mobile devices, up through operating systems that you carry with you, applications have access to that and then can utilize it for reasons that are beyond the use of the actual application, for example, for navigation. And I think that's problematic. So how it is that we jointly optimize algorithms and do research in that space that enables the data to be used for that task and nothing else, I think is critical.
Okay, great. And then we have one question again from Gabor. And they ask, how are the maps of each headset aligned and synchronized in the multi-person setting? So I guess also for the EOCOM dataset.
Yeah, so that is where most of the challenge came technically, which was the devices that we were using, which are just off the shelf recording glasses that you can get off Amazon. They don't come with any real synchronization capability between the devices. And the first thing then is to build tools, and we described this in the paper, to be able to align the audio whilst accounting for the fact that you can have displacement shifts just because of the speed of sound, for example. And that is a challenge. With respect to the underlying localization into a consistent 3D frame of reference, not all of the data that we can obtain from those egocentric videos can be aligned, but some of them are aligned via basically relocalization tech into our 3D replica models, but they're very few and far between. The data sets that we're releasing are the raw data sets with the time-aligned video across users.
Okay, great, thanks. Are there any other questions for Richard? No? Okay, well, thank you ever so much, Richard, for giving the presentation. I really enjoyed it. I'm sure everyone else did as well. And then moving on next, we'll have a talk from Jitendra. I believe he might be a few minutes late, so we'll have a short 5-minute break just to get some coffee and go for the next talk. Okay, thanks everyone.
Okay, thanks, Michael.
Hi, this is Jitendra.
Hi, welcome. Do you want to try making sure the screen share works and everything?
Yeah, let's do that.
Okay, I'll just stop my share.
Okay, do you see something which says next steps in computer vision?
Yeah, I see it fine.
Excellent. Okay, and you can hear me. Excellent. Okay, I'm ready. Sorry, I got late.
Okay, yeah. So I think I guess we'll get ready to go. Obviously, we're thrilled to have Jitendra here to give a presentation as part of the EPIC workshop. And well, Jitendra doesn't need any introduction, I guess, to everyone, but I'll give a short one anyway. So he got his PhD from Stanford University before joining the University of California at Berkeley, and is now the Arthur J. Chick Professor there. And then recently, Jitendra also works at Facebook AI as a research director and a site lead. So we're really excited again to have Jitendra giving a talk here about the next steps in computer vision. So I'll hand over to you.
Thank you. Okay, so I want to give a more philosophical talk here, which is sort of a big picture about where the field is, where is it going, and in particular, I'm a strong believer in egocentric video understanding. I'm a great admirer of the work from Dima and Giovanni and all their groups, and but I want to situate this in the bigger picture of the field. So let's start with what I think currently is why the computer vision community is all excited, or why we are all regarded as successful. It's sort of the culmination of line of work over decades, really, which was the development of learning techniques, the building up of big data sets, availability of compute, and we can do things like this, right? So these are results from mask RCNN. We can detect objects, we can find those instances. I mean, these are spectacular results. And a decade ago, if somebody had asked me to take a bet, would we have results like this, I would have said no. Okay, so this is just very impressive. Okay, so that's the success. Now, what are we done? What is left to do? Okay, so that's kind of the theme that I want to pursue here, and I'm going to pick these 4 topics: limitations of supervision, static data set AI, perception disconnected from action, and the semantic gap. So, so we have had great success, but it has been a success with supervision. I mean, so basically we have these xi, yi pairs, and then we can train up neural networks are great function approximators. Bingo, done. Okay, but is this going to continue forever? And what's happened is that even though we are able to use crowdsourcing quite effectively, there are certain categories for which you will simply not have enough data. So there's always a long tail. So in action recognition, for example, there are always weird actions for which you're never going to have enough training examples. So that's a fundamental problem because you don't have anything to label. Secondly, there is stuff that humans are not good at providing supervision for. For example, 3D shape. So I think currently, to me, a big challenge is I want to make the entire world 3D. I want all the objects, humans, everything to be 3D. Now, humans are not good at annotating 3D shape. They're not good at estimating depth as 7.6 millimeters and surface normals as 37.8 degrees, that kind of stuff. So that's not possible. So that's a practical engineering critique. But of course, there's a scientific critique because we can think about how human babies learn, and they certainly do not need all this explicit supervision. I mean, the mother may take a child to the zoo and say zebra, and that's one example of a zebra, whereas our computer vision system needs 1,000 examples of zebras. Okay, the second big problem is one which I think the theme of this workshop is essentially handling, which is static data set AI versus embodied AI. So we made a lot of progress with supervised learning, but in fact, supervised learning based on the internet. Okay, and I mean, there's work from my group going back like 20 years now, the Berkeley segmentation data set, which was one of the early ones, Caltech 101, 256 from Pietro Perona's group, and so on and so forth. And these are all images from the web, and it was great if the objective was to retrieve images from the web or YouTube videos or whatever. And we have had great success, and this is why companies like Google and Facebook and so on are happy, because we have developed technology using these kinds of curated collections. But these are disembodied, well-curated moments in time. And this is what human perception actually is like. Okay, this is a slide from Kristen Grauman. And this is what we need, right? Ultimately, we want vision as perception to guide action. And this is going to be an egocentric perception, and it's going to suffer from all the issues that you're dealing with here in this example video. So if we are dealing with the scientific problem, we have to consider this. Okay, so this is the, again, in some groups, I probably have to sell this, but in this group, I don't need to sell this. So let me focus on the next theme, which is why do we care about embodiment? Okay, so this is because we have been studying perception disconnected from action. So I'm going to go into this slide, which is really a history of intelligence in one slide. So let's start from the big picture, which is that how vision arose. So this is something like 540 million years ago in the time of the Cambrian explosion. So this is the first multicellular animals. And what they could do is they could see and they could move, and the two work together. Because what's the advantage of movement? The advantage of movement is that now you can find food in different places. You're not stuck with the food that comes to you. So plants are stuck with the food that comes to them. So the carbon dioxide comes to them, the sunlight comes to them, etc. Animals can go and find food in various places. Okay, but I use the term find, which means that you need to have a mechanism for going and finding the food, right? And that implies perception. So there's this line from Gibson: we see in order to move, and we move in order to see, and you can understand that the two go together. Then when we move to the last 5 million years ago, which is where human hominids break off from the rest of the primates, that's when we have the development of the hand, the opposable thumb, and various kinds of manipulation abilities, tool use, etc., etc. And finally, when we get to the last 50,000 years or 100,000 years, when we get language and abstract thinking. So the core of intelligence really starts off with this interaction between perception and movement, moves on to the interaction between perception and manipulation, and then at the very end, we have the emergence of language and more abstract thinking. So I genuinely believe that in order to achieve intelligence, we will have to somehow replicate this path. So this is the path of evolution, but we can also consider the path of child development, and I'll refer more to that in a second. But I want to spend a couple of slides talking about the semantic gap. The semantic gap is a term which goes back like maybe 10 years ago to the early work on multimedia and retrieval and so forth, where there were image retrieval techniques which were based on color histograms, which could find like red sunsets, but they were really not good at finding objects. Now we tackled the semantic gap in the context of object understanding, because we really do have with techniques like mask-R-scan and pretty effective detectors of objects. However, I want to consider the semantic gap in the context of scenes or video or whatever. So look at this image. What can we do here? So just spend a few seconds thinking about this. So what computer vision today can do is we can understand the objects here, right? We can detect the objects. We can maybe even map them to 3D models. Maybe we can take the human, estimate the joint angles, etc., etc. But more interesting question to me is, let's go back here. When I look at the scene, I think of this person, this woman. I think she's a musician. I think she is clearly playing for money because at her feet there's this bag, and there you can see some money there, some dollar bills maybe. And this guy is, I think, listening to her, deciding, okay, should I listen to her? Maybe I should give her a tip. Maybe I need to catch my train, etc., etc. So there is all that which is being evoked. And what we are doing is just reducing it to this very boring aspect of here are the objects and these are the 3D models. So I feel that this is where we need to get to. So there's this semantic gap has not been bridged yet. Okay, we don't bridge it just by building 3D models of objects or people. It's really answering questions like this. And these questions are questions about dynamics. These are questions about predicting the future, right? That's at least one way to operationalize them. The next thing that I want to refer to is something which is really, in my view, a major critique of the work which has been going on in natural language. So we have had great success in natural language with the latest techniques, BERT, transformers, etc., etc. But and they're able to do a pretty effective job of, for example, translating from English to French and so on. But these systems do not understand language in any sense, because the symbols are not grounded. So this is a paper from 1990. So the dog, which has been translated into the word for dog in French, that system doesn't know how to find a dog in an image. So we really need to have these symbols of language be connected to grounded in the world. And grounded is in terms of perception, grounded is in terms of motor control. Okay, so how do we do this? So philosophically, I'm on this one shtick for now a couple of years, and this is essentially as a proposed agenda for the computer vision community, in fact, broadly for the AI community, which is very much inspired by Turing's 1950 paper. So Turing in his 1950 paper, the one which defined the Turing test, if you actually read that paper all the way, everybody quotes the paper, but they usually don't read it. If you read it all the way through section 6, then there is this paragraph. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. So that's a very interesting perspective. And Turing wrote in 1950, and of course, we are now in 2020, so 70 years later. And in these 70 years, our colleagues in psychology and child development have uncovered a lot about how children learn and how they evolve and how their understanding develops. So for example, this baby is playing in her crib, and she's got this multimodal information. She is touching those objects, she hears the sound, she sees the objects, she paddles at that object, and then it sort of flies away, and so therefore is learning about common sense physics, etc., etc. So because of all of this experience, when this child goes to the zoo with her mother, and the mother says, that's a zebra, that one example is enough, because the child is already a visual genius. Doesn't need the 1,000 examples that we need from ImageNet or Coco or what have you. So what I believe is that it is a totally legitimate and reasonable research enterprise for us in the field to try to achieve this sequence of visual development in our systems. So how are we going to do this? So we should look at the literature in child development. It will give us some inspiration. We'll after that have to do some work. So there's a rich literature. I've just picked one paper just for concreteness. And basically, I'll just read it out here. The embodiment hypothesis is the idea that intelligence emerges in the interaction of an agent with an environment and as a result of sensory motor activity. So, then can we get some lessons from that? So, so these are some lessons that they have. Multimodal, I think I already referred to that, the fact that the child is getting sounds and sight and touch and all of these signals. There's incremental learning, so learning builds on the next steps. And then it's physical, you're acting in the world. So that's why embodied perception and action, both are important. Exploration, be social, use language. Let me pick on one of these themes. So how do we explore? So I think that we have to move out of, so the classic static data sets, ImageNet, COCO, etc. We need to move out of them in a couple of different ways. One is this embodied data sets, right? That's what this workshop is about. So that's one direction. But there's a second direction, which is that even an embodied data set is not enough, because what you need to do is to interact with the world. You need to move, and then you need to have a different perception as a result. So how are we going to get that? So we can get that by being in a visual simulator. And the technology has got good enough now that we can have fairly rich simulation environments of real worlds. So here's sort of an example of what we can do now with 3D scanning technology. So these are real world environments which have now been captured into the computer. Okay, so now what do these environments give us? They give us that egocentric view, but in addition, if I perform an action A, such as move left 30 centimeters, I will get a changed view as a result of that. So I'm now an active observer. And so now, so I think that this permits us to do a lot of interesting kinds of research. And just to, I mean, of course, Habitat is not the first of these data sets or simulation environments. And there have been a number of these scans of real world environments that have been developed, and various simulators. I mean, I was associated with one of them before, Gibson, led by Amir Zamir. And then on top of these simulation environments, we can do various tasks. Embodied question answering, language grounding, etc., etc. In particular, the study of visual navigation has really taken off in this setting, because what we were able to do is to define benchmark tasks. So just like there were classic benchmark tasks for object detection, now we have benchmark tasks in this more active setting where there's a combination of perception and action. So my slogan here is that these classic static data sets were, they had their time, but the future is actually in simulation environments. So embodied perception actually fits in very nicely, because when we have a person moving through some environment, we can imagine replicating that trajectory exactly in a simulation environment. So embodied data, in fact, permits a replication of that in one of these simulation environments. Egocentric video. Okay, now what can we do with this? So I think that these ideas go together. So there's egocentric perception and the simulation environments. I think we want to work with them together. Because the egocentric video, the virtues of that are that we are always assured that it is real, that we are not fooling ourselves, because in a simulation environment, there can be various kinds of artifacts which we may not have thought of. Currently, the simulation environments don't really have much in the way of people. They just are, they have objects and scenes, but they don't really have other people in them, because we don't have good models of people that we can populate in these environments. I mean, there are models in game settings, but they're not, in my view, good enough. So that's where we are. So I think these two go together, simulation environments as well as egocentric perception. Now let me try to just show some of what we can do by learning in this setting. So, and I'm going to tie this to being social, because social often is in the sense of, we mean this in the context of emotional reaction, language, etc. But I mean this in the sense of imitation learning, where human societies have culture. We are significantly different from what our ancestors were 100,000 years ago as hunter-gatherers. Right now, we learn implicitly and explicitly. So how do we do this? So I want to take a comparison point. I mean, the hot thing these days has been reinforcement learning, thanks to the success of AlphaGo, et cetera, and some people have even valiantly tried this in the context of robotics. So this work from OpenAI. But this is zillions and zillions of trials, okay? I think that this is not how humans learn. And then after that, you need to have this transition from simulation to real. Imitation learning is an idea which has been around for a long time in robotics, but earlier it meant exact copy of what the human did. And we want to do better than that. So what are the challenges in imitation learning? So we really don't know what action the human was doing. We just know the state. And of course, there's going to be a problem of translating from the human's body to the robot's body and so on. So, so I'll give you two examples of work here. So one is stuff that we did where it was learning about human movements in free space. And a prerequisite for this is the ability to learn human dynamics. Okay. And so I'm going to, this is work which was presented last year at CVPR and ICCV. But the basic idea is that from a single frame, we can get to some representation of the 3D pose and shape. And we can create a spatiotemporal representation as well. And the way we train this is from various kinds of losses, that the 2D key points that are predicted are good, that the 3D is correct and consistent with the model of a human, et cetera, et cetera. And let me I have this little video clip which talks about how this technology enables us to predict human 3D movement. So we have some input video, and what we are going to do is to try to predict the future.
In this work, we present an approach that takes a video of a person as input and predicts the future 3D mesh sequence of the person. Here, we show the ground truth future video for reference, but the model only sees the input video. To do this, we propose a neural autoregressive prediction model on the latent representation of 3D human motion encoded from the video. This allows seamless transition between conditioning on the past image frames and conditioning on previously generated future predictions. Specifically, for each image frame, we first extract a per image feature vector. From these image features, we learn a latent representation of human dynamics, which we refer to as a movie strip. Each movie strip is causal, which means that it only contains information about the frames up to the current time step in consideration. We then train a 3D regressor that predicts the parameters of the 3D mesh model from the movie strip representation. This is trained with 3D supervision when available. And if not, the model can be trained with 2D key point reprojection loss, along with an adversarial prior to ensure the poses look realistic. In order to predict into the future, we train an autoregressive model, which is a temporal convolutional network that uses the past movie strip representations to predict the next movie strip. This newly predicted movie strip then becomes one of the inputs to the next frame prediction, which may continue repeatedly in succession. From the predicted future movie strip sequences, we can also read out the 3D mesh parameters. This autoregressive model is trained with the same losses, where the predicted 3D mesh model has to match the ground truth 3D or 2D joint labels, along with the prior. We also include an additional distillation loss, which guides the autoregressive model to predict the actual movie strip representation. Alternatively, we can also apply the autoregressive model directly on the predicted 3D mesh model. Here, we show some qualitative results. Our approach can predict the future 3D motion of non-periodic actions such as bowling. The yellow mesh is read out directly from the ground truth movie strips, while the blue mesh is the predicted output of our model. Due to computational constraints, we only train our model to predict up to 25 future frames. But in these sequences, we show the predictions are reasonable even past 25 frames.
Okay, so I'll skip more results, but you get the basic flavor here, which is that we have built a dynamical model and we are able to use this for prediction. Okay, so and now this shows some ways of how to use this. So what I'm saying is we need to now bring in actions. So in order to do imitation learning, we can see these observations of state, right? So we are seeing the state of the human body. And what we need to do is actually to know what the actions are. So that's the policy, right? So given a state, what actions should you take? And the actions are not known to us, right? Because we don't have access to the internal state of the human's head and the human's neural network, which is commanding various muscles, et cetera, et cetera. But knowing the sequence of states does provide us training data, useful data, because what we can do is we can say, okay, I should have a policy such that at various frames, the state is kind of like what the human was doing, right? And anyway, that's the theme of this work, and we show that this works reasonably well. And let me show you, so that was for movement in free space. And we have some recent results. So this is work led by my student, Ilya Radosovich. And what he shows is that we can, in fact, do this even for manipulation tasks, which are considerably more challenging. So, so let's see. So dexterous manipulation is just manipulation in of the hand or objects in the hand. And these are complex high-dimensional action spaces. And people have tried to learn from this in a very difficult setup: VR glasses, motion capture gloves, etc. What's our goal? I think our goal is really ultimately this kinds of egocentric video data. We want to use that for learning how to perform actions. So wouldn't it be nice if after the looking at the Epic Kitchen videos, there could be a robot which could then execute on a recipe of making pasta by performing the sequence of actions which was there in the egocentric video of somebody making pasta. So, so it's important to be able to manage with just knowing the state, because the actions of the human, which have to do with what motor commands that were issued by the human's brain, so those we will not have access to. We can only observe externally the states of the joints and so forth. So, so state-only imitation learning is about knowing only the states and not having access to the actions. Okay, so what do we do this? How do we do this? So the secret here is that we must build a dynamic model, and in the sense of control theory. We need to know, we are going to have a sequence of states, and we must learn what action was performed in order to go from state S0 to S1 to S2, etc. And this idea has been around in both control and in neural networks. And here are some of the references on that sort of stuff. And the basic theme here is that let us learn a model for actions. What actions took the human body from state S0 to S1. And now we can essentially train a reinforcement learning agent. And this agent is effectively getting one term, which is kind of like your classic reinforcement learning policy gradient kind of term. And this other term, which is saying, try to have a sequence of states which correspond to what a sequence of states was for the human demonstration. And then over time, what you can do is you can anneal that to 0, but it will get you into the right part of the search space. So the basic setup is collect trajectories from the policy, update the inverse model, predict actions, update the policy. And then it turns out that this, we have showed it for a variety of tasks. This is all in simulation, but object in-hand manipulation, opening a door, tool use. And the bottom line here is this. So we are talking about, so the y-axis here is the mean return, okay, and and then x-axis is time. So if you don't have any demos, then it takes you go through lots of iterations and your reward is low. You're not doing well. And the top two curves, the blue curve and the red curve. In the blue curve, you had access to the actions. In the red curve, which is our approach, we only had access to the state. And it turns out that they are reasonably close. So this is great. So this means that this egocentric video, without having access to electrode recordings of neuron firing in the brain, is useful because the egocentric video gives us the sequence of states. And okay, so these are just results which all show that this approach works. So state and various, we showed it on a variety of tasks. We show that in fact it works even though the dynamics is different, is because you're not just doing mimicry, you're doing imitation. You're inspired by what you see, but then the actual action takes into account your own morphology and dynamics and so on and so forth. So you can generalize, so you can have a heavier object or some other constraints on the hand which make it different from the human hand, and yet the technique will work. You can even remove some fingers from the hand, a cruel experiment, but can be done. Different objects, okay. So anyway, so the moral of the story is that we can actually learn from just observing states and not having access to state actions. So I think that this is very suggestive for how egocentric video of object interactions could be used in the future. I want to just conclude with these remarks. The philosophy that I've tried to articulate here is really a very, very old one. I mean, it goes back to Kenneth Craik, 1943. In this, he said this: if the organism carries a small-scale model of external reality and of its own possible actions within its head, it's able to try out various alternatives, conclude which is the best of them, react to future situations. So, and that's what we want to be, where we want to be going in this field that we are in. I have another slogan here, which is that common sense is not just facts, but it's a collection of models. It's a collection of dynamic models of what we do in various situations. I think the using child development as a source of inspiration is a great idea. I think it provides the right structure for viewing the various stages of inbuilt knowledge, supervised by observation, supervised by interaction, supervised by culture. Thank you very much.
Okay, thank you, Jitendra. Very, very interesting talk. If anyone has any questions, feel free to type them in the chat on the Q&A or ask them themselves if you're a panelist and you want to unmute yourself. So I'll start off with one of the questions that I had was, so when you're talking about the image of the person playing the instrument and wondering whether the other person will hand them the money, where do you think we'll be able to get those kind of like high-level semantics from? Because of course, like annotating that would be a considerable amount of work, and kind of anyone can say almost anything about images like that. Do we go for this annotation approach, or do you think we can learn this like from your last work?
No, I don't think so. This is why one of my points was that we may be hitting the limits of what annotation can do for us. So I think that it's not that we have got a good alternative, right? So I think right now, if you are a practical minded person, the right thing to do is annotation. Okay. But I don't believe that it's a long-term future. I think that we are, with every technique, you sort of start to hit the limits, right, at some point. So if you go back to the 2010s, we were doing quite well with sort of HOG and DPM, but at some point, there were tweaks which didn't get us much further. So I think that the richness of human activity is such that just annotation for everything is, I think, not a scalable solution. I mean, right now we are doing it, but affordances, so think about affordances. We are right now, our technology suggests that we mark all these affordances. But is this really the right way to go? No, I think we should, what we if we are able to parse the human actions, which I think we can, right? I think the technology that I'm talked about was really about that. And suppose we develop a certain 3D understanding capability generically. I think we are on step to doing that. Then we can understand the action, at least in terms of the human body in 3D interacting with this object in 3D. Okay, now, and then we have a long-range temporal structure, and there you can do self-supervision, because the way you train the model is, okay, I have a loss which is based on, I try to predict what will happen at some time t prime in the future, and then what actually happened. So now you have a loss between those, right? And this is what people do in the language setting. So my belief is that this style of work, going to 3D and this kind of self-supervision over long temporal sequences, I think that may be the ticket. I think currently our 3Dification technology is not rich enough, right? So when we are working directly from pixels, then we get a lot of help from having action labels. But I think eventually the future is in trying to build predictive models with self-supervision.
Okay, thank you. Any other questions that anyone has?
So can I ask a question? This is David. So I guess I'm wondering, right now the egocentric computer vision community is pretty small compared to the overall community. I'm wondering, like, what percentage of the work that you see we need to do in computer vision sort of is part and parcel of egocentric computer vision, and if it's really important. And it seems like from some of your sort of research directions, it is really important. Like, why is it so small compared to the rest of the community? Will everyone have, will there be any reason not to be doing egocentric computer vision in a couple of years?
Well, I think it has to do with practical applications. So if you look at practical applications right now, a lot of them have to do with analysis of images and videos on the internet, right? So from a commercial point of view, right? You want to find out, for example, the oldest example is if you're an internet company and you're putting up images and video, you need to detect pornography and delete it, right? Okay, so that requires just static image analysis. So you need to have techniques for that. So there are a lot of these practical applications which are just of classic third-person images trained with supervision, etc., etc. I think the value of egocentric video really comes in if you are going to train agents who act in the world. Okay, so it really is, to me, why I like this space is because it connects to sort of robots as well as intelligent assistants. So if I'm going around with, going back to like AR glasses or Google Glass or whatever, and this assistant is going to tell me various things, it's going to guide me through making an omelette or whatever. What am I going to need? I'm going to need egocentric perception, right? If I'm going to train a robot in the home, so again, robots can be in factory settings or warehouses, but in my mind, what I'm excited by is in the next 10 years, in the next 15, 20 years, whatever, there'll be robots in everybody's home, right? Which is going to cost $5,000, $10,000, and it can help you in lots of ways. It can take care of our elderly and so on. Okay, what is that robot? How do we train these robots? I think that these ideas like imitation learning and so forth, I think are going to play a major role. So I think that there has to be this application infrastructure, which could be, for example, VR assistants, which could be home robots, right? When those take off, then the underlying science and technology will be based a lot on the kinds of things that we are talking about here, like egocentric perception. Now, we don't have that yet, right? We are not there yet. So that's fine. As scientists and researchers, we do things in advance of practical applications. We don't just have to immediately do what is going to be used tomorrow. So so one has to persevere, and I really believe in this. So
thank you.
Okay, I got another question from Mega, which says, most of the current video understanding methods process the video at frame level, either at reduced sample rate or recursive modeling. What are your thoughts on processing long-range videos frame by frame on aspects such as scalability and effective temporal structure modeling?
Yes, good question. I think currently we have not solved the problem of long-range video understanding. So in my view, what we have developed are techniques which work at the 1 second level, right? So at the 1 second level, I mean, slow fast, this is work from Christoph Eichenthofer, and I was also associated with that work. That's a very good model for understanding video at the 1 second level. But 10 seconds, 100 seconds, 1,000 seconds, I think the technology is not there. What we find for that these long range models are doing is more or less static frame analysis, right? It's like a long range analysis will require new techniques. For example, I think it requires operating at the level of understanding people and objects and so forth, rather than just at the level of pixels. So it has to move from pattern level understanding to something which is more structural in nature. And we want to do it in a learning framework. So the learning frameworks which work at this entity level at a slightly higher level of abstraction, I think that's what we need. I think that I don't think we have really good examples of that right now. So to me, it's really, it's a beautiful problem. I mean, I think that example that I showed of that musician and trying to understand what will happen long term, I think that needs that kind of understanding. Or to take this very cliched example from AI, we are, suppose I'm in a restaurant, I go through a sequence of steps, right? Somebody sits me down, then someone comes with a menu, later on I order, then the food arrives, etc., etc. We understand those situations in terms of certain agents being, someone is a waiter, someone is a customer, the food is being delivered, etc., etc. We have this deeper understanding of this being like a play with various actors in their various roles. That is long-term understanding, right? I think we are not there yet. We don't have, and we want to do it in a learning framework, not like classic AI by building in a handcrafted solution. So we're not there yet. The techniques that I showed you, right? So we can do a decent job of predicting human dynamics, but at the scale of 1 second, right? The techniques that I showed you were about 1 second. They are about physical movement in immediately from like 10 frames, 100 frames, that sort of thing, right? So there is much more which needs to be done.
Okay, thank you. Any other questions for Jitendra? No, I'm not seeing any. Okay, well, thank you ever so much for your talk, Jitendra. It was very, very interesting.
My pleasure. Thank you, everybody.
Okay, thanks everyone. This concludes the EPIC at ECCV2020 workshop. I hope everyone had a really good day and watching all these interesting talks and keynotes that we had. I'd like to thank all of our speakers, all of our organizers, as well as all of the attendees for asking their interesting questions and contributing to the workshop. And yeah, hope to see you around in the upcoming ECCV main conference. Thanks everyone.